We have one more break now, and then the last block of sessions where we'll have speakers talking about AI consultancies, paying engineers like salespeople, and how to make your our last block of sessions before you all get to enjoy the Graphite after party. More coming on that in a few. And for this block, we're going to cover a lot. AI consulting in practice, paying engineers like salespeople, as I mentioned earlier, leadership in AI-assisted engineering, and how to build an AI-native company. You guys ready for this? Oh, come on, let's go. So with that, please join me in welcoming our next speaker and one of last year's MCs to talk about helping organizations transform with AI. Let's hear it for NLW.
All right. Great to be back here, guys. For those of you who are here in February, I had the privilege of emceeing, and today I'm excited to talk about something a little bit different. So right now, the last couple of months have been an interesting time in AI. There's been a sort of surge in the narrative of an AI bubble, a lot of it driven by dubious studies like the MIT report. And so what I wanted to do today is get into not so much the practice of consulting and transforming, but what organizations are actually finding value in right now. So for those of you who don't know me, there's kind of two contexts I bring to this conversation. The first is as the host of the AI Daily Brief, which is a daily news analysis podcast about AI. The second is as the CEO of Superintelligent, which is an AI planning platform. And so the different perspectives are sort of very high-level macro, thinking about the news that's happening, and then a much more kind of ground-level view where we're spending a ton of time interviewing executives about what's going on inside their organizations. And what we're going to talk about is sort of one, kind of briefly in the first part, just the status of enterprise adoption as it currently stands, and two, and the more interesting part is we've been live with a study in the market for about a month now, collecting self-reported information about ROI around different use cases. And this will be the first time, this week was the first time I did some analysis on it, and so I'm going to share what people have told us around the first kind of 2,500 or so use cases that they've shared. So it should be pretty interesting stuff. Talking about kind of enterprise AI adoption first, I'll go through this pretty quickly because it's pretty well-known stuff. The short of it is enterprises are adopting AI in a growing fashion. Pretty much everyone is using it at least a little bit, and increasingly they're using it a lot. This year, I will need to tell none of you that there is a major inflection around specifically adoption in the coding and software engineering, right? So a huge uptick in this. There's a lot that's interesting about that from an enterprise perspective because it wasn't just with the software engineering organizations. Other parts of the organization are also now thinking about how they can communicate with code, build things with code. But that's a huge theme of this year. Coming into 2025, one of the big sort of thoughts that many people had was that this would be the year of agents inside the enterprise, right? That big chunks of work would get automated away. And on the one hand, I think it's pretty clear that we didn't see some sort of mass shift towards automation writ large across different functions of the organization. But when you dig into the numbers, there has been actually pretty significant shifts in the patterns of agent adoption. So this is from KPMG's quarterly pulse survey, and it's a measure of how many enterprises that are a part of their survey, which is all companies over $1 billion in revenue, have actual sort of full production agents in deployment. So this isn't pilots, this isn't experiments, this is where they consider some agent that's actually doing kind of work in a full way. And it's jumped from 11% in Q1 of this year to 42% in their most recent study for Q3. So you actually are seeing pretty meaningful uptake of agents inside the enterprise. In fact, I would argue, based on our conversations, that it's moved more quickly through the pilot or experimental phase than people might have thought. So much so that you're actually seeing now a big shift in the emphasis around kind of the human side of agents and how humans are going to interact with agents. And it's involving a shift in upskilling and enablement work. You're seeing a decrease in the sort of resistance to agents as people start to actually dig in with them. You're seeing more experiments like these sandboxes where people can interact with agents. So this is a big theme, even if it wasn't necessarily the dominant theme that some thought it might be coming into this year. At the same time, it is absolutely the case that many, if not most enterprises are, broadly speaking, stuck inside sort of pilot and experimental phases. There is a lot of challenge around moving from some of those first exciting experiments to something that's more scaled. So this is from McKinsey's State of AI study, which came out, I think, a couple weeks ago now. And you can see only 7% of the organizations that they talk to claim or sort of see themselves as fully at scale with AI and agents. And something like 62% are either still experimenting or piloting. Interestingly, big organizations are, in general, a little bit ahead in terms of the organizations that are scaling as compared to small organizations. This has been a thing that we've noticed kind of throughout the trajectory of AI adoption over the last couple of years, that you would think that perhaps smaller, more nimble companies would be more kind of quick to adopt these things. But in fact, it's often been the opposite with the biggest organizations making the biggest efforts. You can also see from the chart on the bottom that there's very sort of jagged patterns of adoption, right? You're starting to see from last year, if you looked, there's very similar kind of rates of experimentation across lots of different departments. You're starting to see some pretty big breakouts now with, for example, IT operations kind of jumping out ahead of other functions. I won't spend too much time on this sort of high performer piece, but I think the thing to note, because it comes back in some of the stuff that we found with our ROI study, is that you are also starting to see a pretty significant bifurcation between leaders and laggers when it comes to AI adoption. And one of the things that tends to distinguish the companies that are leading is that they are just doing more of it, and they're thinking more comprehensively and systematically about AI and agent adoption. So they're not just sort of doing spot experiments, they're thinking about their strategy as a whole, they're doing multiple things at once, and importantly, they're not just thinking about sort of the very kind of first-tier time savings or productivity types of use cases, they're also thinking about how do we grow revenue, how do we create new capabilities, how do we create new product lines. overall, it's very clear that despite what is sort of the concerns in the media, that spend is going to do nothing but increase on this. So the bottom is the KPMG Pulse survey again, and this is an estimation of the amount of money that these organizations intend to spend on AI over the next 12 months. The beginning of the year was 114, which by the way was up from like 88 in Q4 of last year. It's now up to, in their last study, 130 million is what they expect to spend in the year ahead, which obviously the total magnitude doesn't matter as much as the change. You also see the green charts are from Deloitte, and you can see 90% plus of organizations intend to increase their spend on AI in the next 12 months. And as part of that, I think you're going to see a much more determined conversation around impact and ROI, which is a particularly thorny topic. But interestingly, there has been an increase in optimism over the course of this year around the realization of AI. So this is from a different KPMG study, their annual CEO survey, which interviews tons and tons of CEOs. And if you look at the 2024 numbers, 63% of those polled thought that it would take between 3 and 5 years to realize ROI from their AI investments. 20% said 1 to 3, and 16% said more than 5. This year, in that same survey, the number that said 1 to 3 years had gone up to 67%. There were now 19% who said 6 months to 1 year, and 3 to 5 years was down to just 12%. So huge kind of pull forward of expectations of ROI realization. The challenge is that ROI is really tough. So this is back to the Pulse survey. 78% of those polled in that survey said that they thought that ROI is going to basically become a bigger consideration in the year to come. But also 78% said that traditional impact metrics and measures were having a very hard time keeping up with the new reality that we're living in. And this is something that I've heard constantly over and over from CIOs and other people who are in charge of these investments, that the ways that we have measured impact of previous technologies and just previous initiatives are kind of falling flat with AI. And so that got us thinking about the overall need that we have to just have more information. I'm not even talking about good systematic information, just more information around what ROI looks like, what impact looks like. And I've got this great podcast audience, they're super engaged. And so we just decided, screw it, we're gonna ask them. We're just gonna ask them to report on what ROI they're finding from their use cases. So this went up at the very end of October. Like I said, as of this morning, or when I last looked, we've had over 1,000 submissions, 1,000 individual organizations rather submit, something like 3,500 use cases. And this is some of the first observations that we had around kind of the first 2,500. So the impact categories, the way that we divided things was into sort of 8 broad categories of impact, which will all, I think, be very intuitive to you guys. Time savings, increased output, improvement in quality, new capabilities, improved decision-making, cost savings, increased revenue, and risk reduction. So basically, we're trying to think of like kind of a broad, simple heuristic for kind of dividing or subdividing the different ways that people are thinking about ROI. And TLDR is that people are finding ROI right now. Now, again, the caveats are that this is a highly enfranchised audience. They're listening to a daily AI podcast, and they are voluntarily sharing this. So I think that there's some caveating there. But you have 44.3% saying that they're seeing modest ROI right now, and then you have another 37.6% seeing high ROI. For the purposes of a lot of these stats, high ROI will be significant plus transformational. Only 5% or so are seeing negative ROI. And keep in mind, negative ROI doesn't mean that they think programs are failing. That just means they've spent more than they've gained, or, in terms of how their perception is. More than that, expectations are absolutely sky high. 67% think over the next year they will see increased in high growth in their ROI. We have a really optimistic sense from the ground view of where ROI is going to be in AI. We even have the teams that are currently experiencing negative ROI, 53% say that they're going to see high growth. So very, very optimistic. As you might imagine, time savings is the default. It's the starting point for so many organizations. It represents about 35% of the use cases. After that, increasing output, quality improvement, basically all those things that you would imagine around productivity are sort of like the dominant categories when it comes to these use cases. When it comes to the specifics around time savings, you see a real cluster between 1 and 10 hours, especially right around 5 hours. And I think this is interesting to call out because it's so obvious to all of us who are inside building these things, whether you are a developer or an entrepreneur or just someone sort of in and around it, how the vast breadth of opportunity that AI represents, new capabilities, things unimagined yet. It's easy to forget that if you save 5 hours a week or 10 hours a week, you're talking about winning back 7 to 10 work weeks a year. And that's very, very powerful. And when it comes to a lot of these enterprises, that is a very meaningful thing, even if it's not what they're ultimately in it for. Interestingly, though, it's very clear that the story, although it might have a concentration in time savings, is about much more than time savings. So this is the ROI distribution category, ROI distribution by organization size. And this starts to get really interesting where you can see that there are some differences in where different size organizations are focused. So for example, the organization size between 200 and 1,000 people has a higher portion of their use cases concentrated in increasing output. Now, we haven't taken the time yet to really figure out exactly what this means or even speculate on what this means. But I think it's interesting that this is a category of organization that has often reached a certain scale, but is still very much striving for more, and so seems to be focused more on use cases that expand their capabilities. Same thing with when you start to divide things by role. You see a real kind of variance where, for example, C-suites and leaders are less focused on those time savings use cases and more focused on other things like increased output and new capabilities. in general, we're finding that C-leaders and just sort of C-suite and leaders in general are even more optimistic and excited and seeing transformational impact than people who are in more junior positions. Now, some of this might be sort of selection bias in terms of what types of use cases you are focused on. If you are in that C-suite, you're thinking about things that inherently, if they work, are more transformational. But it is notable that 17% of the use cases that people in those leadership positions have submitted, they say have transformational impact and ROI already. I'm going to skip this because we don't have time for too much. You're seeing, interestingly, a concentration where the smallest organizations are getting more of that transformational benefit early. One of the things that I want to do following this study is maybe do a sort of second round where we dig into what this 1 to 50 person size really looks like. I actually think that whereas there might be a lot of similarity between a 1,000 and a 2,000 person organization, there could be a wild difference between a 3-person small company and a 40-person company. And so I'd really like to dig into that more. But you are definitely seeing a lot of impact in those sort of more small, nimble, moving organizations. As you might expect, coding and software-related use cases have a higher ROI than average and a lower negative ROI than average. One really interesting kind of pulling on a specific category of use cases, risk reduction is our lowest category in terms of the percentage of use cases that was their primary benefit. So when you're filling out the survey, which is by the way at roisurvey.ai if you want to check it out, you basically only get to pick a primary ROI benefit. We didn't want it to be super sort of, we wanted you to pick and hone in on the thing that was seemed most important or most significant. And so only 3.4% have risk reduction as their primary benefit in terms of ROI categories. But it is by far, those use cases are by far the most likely to have transformational impact as their outcome. It's at 25%, so a full quarter of those have transformational ROI. And interestingly, I was having this conversation with a couple of my friends who work in sort of back office and compliance and risk functions, and this has been their experience as well, where there are a lot of the challenges for those organizations involve sheer volume and quantity in ways that AI can be really helpful for. We also are finding some interesting patterns among organizations. And again, this is where we get into some of the limits of this, just being a whoever walks through the door of my listeners. We have a pretty heavy concentration among technology, as you might expect, industries, and among professional services. But we still have fairly decent sample sizes for some others. And in both healthcare and manufacturing, the use cases are meaningfully higher impact on average than the average across all organizations, which I think is it was kind of worthy of further study. Last sort of part of this, as I wrap up, a lot of these use cases, as you saw, have to do with that sort of first tier that most enterprises are going to be in, increasing the amount of content that you output, increasing the quality of that content, just finding ways to win back your 5 hours a week. But increasingly, there are automation and agentic use cases, and we are absolutely seeing that where those are the focus, where those use cases mention certain types of automation or they mention agents, they wildly outperform in terms of the self-reported ROI from them. That's both on automation and it's on agents. And I think that that's sort of a trend towards where we're headed with sort of the next layer of more advanced use cases. The last thing that from this sort of first look of observations is there is clearly benefits, and this goes back to what we saw with that McKinsey study as well, of thinking about AI and agentic transformation in systematic, cross-organizational, cross-disciplinary types of terms. Effectively, pretty much directly, the more use cases that a person or an organization submitted, the better they tended to see ROI for. Now, there's lots of reasons for that, but I do think it speaks to that core idea that once you move beyond kind of your single spot experiments, there's a lot of opportunity to sort of grow the impact of the organization. So like I said, that is the first look. It's kind of the first 2/3 of these use cases. We'll be open for another week, and then we'll have the full study out at the beginning of December. I'm really excited, I think, heading into next year to see how we move from sort of generic conversations about impact and our gut senses about impact to a lot more random experiments like this to figure out where the impact really is and where we go next. So look at that. I'm going to end 27 seconds early and really throw off the time. But appreciate you guys all being here. And again, if you want to check this out, it's at roisurvey.ai.
As AI changes our business and engineering landscape, do we need to rethink how we incentivize and compensate engineers? Here to provide us with a case study for scaling output, not overhead, is the co-founder and managing partner at 10x, Arman Hezarkhani.
How's everybody feeling? It's been 7.5 hours. We doing okay? Yeah. Awesome. I'm Arman, like the voice of God, apparently. That's what they're called, voice of God, apparently. So my name's Arman, one of the co-founders and managing partners at a company called 10x. My co-founder is Alex, who's been kindly announcing everybody all day. We do a lot of cool work. We help companies with their AI transformation. We have incredible clients all over the world, but I'm not going to talk about any of that today. I'm going to talk about something much more niche. I'm going to talk about how we pay engineers. And we pay engineers like salespeople. Earlier, I was just in the green room with a bunch of distinguished engineers that I've grown to respect for my entire career. And we were talking, and I was telling them that we pay engineers based on the story points that they complete. And we had a lot of people roll their eyes and laugh. And they asked, what do you mean? And I said, clients pay us for the number of story points that we deliver, and we pay engineers based on the number of story points that they complete. And similar to the looks that I'm getting from some of you, there was skepticism. And I know this sounds crazy, but it's working. We've been able to hire incredible engineers, many of whom have started and exited companies before this. We have been able to hire world-class machine learning and AI researchers. We've hired rocket scientists from NASA. We are shipping code incredibly quickly, and it's maintainable and high-quality code. Of course, that is everyone's dream. Everybody wants to hire great people. Everyone wants to deliver really fast code. So my goal here is not to convince you all to adopt our model. My goal is to show you what compensation looks like in AI and hopefully provide a new perspective on the fact that things might change as we introduce this technology. Before I jump in, though, I want to talk about how we got here. So I'm a software engineer by training. I went to Carnegie Mellon, and then I taught there in their School of Computer Science. After that, I went to Google, and I helped them scale their AI, cloud, and mobile practices internationally before starting a few venture-backed startups. And in my last startup, I would work out of a WeWork. And I was sitting in this 33 Irving WeWork. If any of you are from New York, you might have worked out of that WeWork. And they have these big tables, and there were 12 of us kind of sitting around. No one's talking. Everyone has their headphones in. And I look to my left, and I see somebody with Visual Studio Code open. Right? I'm like, OK, I have a fellow engineer to my left. And I see that he was typing, but I didn't see a chat window. This person was typing into the code editor. They were typing F-O-R, like a caveman. This poor person was typing, like with their little chopstick fingers, individual characters. I couldn't believe it. On my computer, I had 45 agents, 3 were ordering me lunch, 2 were writing code, 1 was doing research. Just different worlds were happening on my computer versus this person's computer. And I felt bad. I thought maybe we should do a GoFundMe or something. But I tried to look deeply at what is actually causing this difference. Why am I using AI in the way that I am, and why is this person not? There are different ways that people try AI, and there are different reasons why people don't use it. We've all heard people who have tried it and have said it's not as good as me. We've all heard people who have not tried it because they don't want to. But regardless, my belief is that this is an incentive issue. For me, I was a founder, and I wanted to squeak out every bit of incremental value and efficiency that I could. And so I would sit on Twitter and LinkedIn and read blog posts and try to understand what is the cutting edge in software engineering and what's going to give me the ability to output more code, higher quality, faster. And because of that, I was using all these different agents. But this person probably worked at a startup, probably had a base salary with an annual bonus and some equity. And that was supposed to be the model that incentivized people to be innovative and to work smarter and faster and harder. But it wasn't working. And so in order to understand how we got to where we are, I'm going to do a brief history of compensation. And this is by no means accurate. I'm making a lot of things up here. It's all illustrative. Okay? So back in the day, we had some cavemen who were writing code. We were probably inscribing C in a tablet somewhere, and we were paying people hourly. Right? This makes sense. I look at somebody sitting in a chair, and I'm going to pay them some amount of dollars for some amount of time. That makes sense for me, and it makes sense for the engineer. But why is that broken? Actually, I want to hear from people. Why is hourly broken? It's slow. Output. There's no upside. There's no reason to work faster, right? And in fact, there's a disincentive to work faster. And so what if I notice this as the buyer of this technology and I say, OK, how long is it going to take you? It's going to take you 5 hours? OK, so I'll pay you $500, right? Hourly, $100, multiply that by 5. And then you as the engineer, if you work faster, great. You get to keep the $500. And if you work slower, that's on you. As engineers, we're really, really bad at estimating how long things are going to take. And so because of that, I'm not going to say it's going to take 5 hours. I'm going to say it's going to take 15 hours, 20 hours, so that I have no downside. And so again, as the buyer, I don't want to pay you based on the project. So what if we hire people on salary and give them a bonus, right? Well, we in the startup community know what happens in that when this is the case. People punch in at 5, at 9, leave at 5. And so I'm Larry Page. I notice this, and I see, why am I working so hard at Google? Why am I putting my blood, sweat, and tears into this? It's because I have some of the upside. I own the company, right? And so when we exit for many, many dollars, I'm going to see that. So what if I can share that with my employees? And that's when equity comes in. And this has worked. This has worked for many, many years to incentivize employees. This is the foundation of the startup community that we all know and are a part of. It's incredible. But not every company is Google. In fact, for every one Google, there are many, many failures, and software engineers know this, right? For those who want to take the risk, many will just go to YC or start their own company. And for the ones who don't want the risk, they're opting for cash over equity. Many of us who've hired engineers know that the cash is non-negotiable. Equity, yeah, sure, I'll take some upside. And so my contention is that this model needs to be reinvented in the age of AI. We need to directly incentivize people to use these tools and to use them well and to still maintain really high quality standards of code. And so here's how it works for us. So we basically, just to take a step back, we do 2 types of work at 10x. One is road mapping and one is execution. So companies come to us and they say, hey, we want AI. That's generally the request. Sometimes it's more specific. It's like, hey, I want my customer service team to have 10% more output using AI, right? But generally they come to us with a request. We do a bunch of studying and learning, and then we output a roadmap. And based on that roadmap, they can take it and work on it on their own, or we can do it. For a lot of things, we're taking off-the-shelf tools, but a lot of what we do is custom builds, and that's where the story point model comes in. So we will build a roadmap for a lot of our clients, but once they see that, then they're putting in requests on their own as well. And we have 2 roles in the company that are client-facing. One is the strategist, and the other is the AI engineer. The strategists are mostly technical. And so we have former PMs, we have former engineers. They are doing PM type work, consulting type work. They're the ones that are taking the product requirements and distilling that down with the client. Then they hand that over to the engineer, and the engineer puts together an architecture design document. They spend a lot of time doing that. In fact, that is where most of our engineering time goes. Then they write code and they start implementing. That architecture design document includes tickets, and each ticket is graded on some number of story points. This is a very traditional method of doing work, right? And when that ticket is accepted, the engineer gets paid a fee per story point that they complete. Our engineers have a flat base that they're paid, and then every quarter we round up based on the story points that they've completed. And again, this has led to us being able to hire incredible people, but we've also been able to do incredible work. So I'm going to walk through a couple of projects that we've done. So this is one. This is a billboard company. If you go to Times Square right now, you'll see some billboards that they've sold that inventory for. They sell in two ways. One is you can call them up, traditional sales, you can buy that inventory. But the other is they have like an Uber for billboards type of product where you can go online, you can upload a PNG, you can choose where you want this to run and for how long. Similar to like a Facebook or Google ad, it's very similar to that experience. And they came to us and they said, hey, we think that there's some opportunities for AI in our product. We did an analysis and we found a few. One of them is this. We found that when an image is uploaded to their system, it has to go through 2 rounds of moderation. One is internal to the company, and the other is with the billboard owner. Internal to their company, they're spending money on that to actually hire the people to do that, and there's a lot of inaccuracy, and it takes a lot of time. So that costs them money, and it costs them revenue, because every moment that the billboard is not running, they're not making money. And so we found, what if we could build an AI model that can actually do this moderation for them? We scoped that out, we built the architecture, design doc, we broke it down into tickets, we built this for them. We did it in 2 weeks, and we got to 96% accuracy when compared to the human moderator. We've done a lot of other projects with this company as well. This is another company. They work with retailers all around the world. And currently they have devices in these retailers. And they're low-power devices. And so because of this, they're able to run one AI model on device. And what this model does is does heat mapping. So imagine there's a camera in this room, looks down, and it can basically generate a heat map of where the traffic is throughout the day. And for retailers, of course, this is very, very useful. But there's other things you can do too, right? If we just sit here for a few minutes, we can probably come up with a lot of ideas of, if you have a camera with a chip, you can make a lot of money from that. You can show really useful information. And so that's what we did. We came up with, what are some of the things that we could do with this? If you put a little bit more power in that chip, if you make the models, if you quantize them so they can run in parallel, what could you do? And so we gave them this report, and then we built them 5 models that can run in parallel. It does everything from heat mapping to queue detection to theft detection and more. And again, we start with the product requirement stock. We break this down into architecture, then we build it, and then we pay engineers based on the output. This is the big question. What are the risks, right? I just talked about dandelions and rainbows, right? So I promised you that my goal is not to convince you to do this. And part of this is showing you what the potential risks are. These are a few that come up. One is, what if an engineer inflates the story points, right? What if an engineer says, okay, you want me to add a button? 45 story points, right? What if an engineer rushes and quality drops? You're saying that it took 2 weeks to do that? Well, was it good? Did it work? And what if engineers get sharp elbowed? I started this by saying that we compensate engineers like salespeople. it's not a culture that we necessarily want to emulate in software engineering, right? So how do we make sure that that's not happening? First of all, I mentioned that we have 2 different roles, and we compensate like a counterbalance. So strategists are compensated based on NRR, which really is like customer happiness. And every single ticket has to be approved internally with multiple rounds of QA, of which the strategist is involved, but also by the client. And so there's a counterbalance to every single ticket that is delivered. I skipped to the second one. For the first one, inflating story points, the strategists are the ones who scope it, and again, we have to review all of that. And for the third, how do you make sure that all of this is correct, and how do you make sure that there's no sharp elbows? How do you make sure that everybody is happy and the dandelions and rainbows are continue throughout this parade of joy? Well, you have to hire the right people. And this is what I tell everybody. We make hiring incredibly difficult for ourselves so that everything else is easy. And that is a principle that we all know and we all stand true to, and this is incredibly important with AI. My co-founder Alex always says AI makes people look like one of those crazy mirrors, where any one of your attributes, it makes it 10 times larger. If you're a great engineer, AI makes you great. If you're not, it makes you sloppier. And this is the case with all of these things. You have to start with hiring. Our belief is that AI gives people superpowers, and it makes all of us smarter, faster, and better at what we do. But my belief is that the current way that we compensate people is actually holding them back. And I would invite you to think about how can you compensate people on your team differently, whether it's software engineering or anything else. If you want to unlock your employees' potential, feel free to reach out to Armon at 10x.co. Thank you.
Our next presenter is Deputy CTO at DX, the engineering intelligence platform designed by leading researchers, speaking about effective leadership in AI-enhanced organizations. Please join me in welcoming to the stage, Justin Rioch.
Hello. Thanks for joining me in one of the later day sessions. Looked like we kept a lot of people here. This is a nice full room. Great to see it. We're going to go through a lot of content in a short amount of time, so I'm going to get right into it. If you want to get deeper into any of this stuff, we have published this AI strategy playbook for senior executives, and a lot of the content that I'm going to go through, I'm not going to have time to get quite as deep, but this is just a nice PDF copy that you can come and refer to later. If you missed this QR code, don't worry, I'll show it again at the end. So what is the current impact of Gen AI? Nobody knows, right? We've got Google on the one hand telling us that everyone's 10% more productive. That's interesting. Other Google, they were already pretty productive to begin with. But we have this sort of now infamous METR study, which has some flaws in the way that study was put together, that showed actually a 19% decrease in productivity using coding assistance. So there's a lot of volatility, a lot of variability. What was really interesting about this study, even though I mentioned there were some flaws, but every engineer that took part in this study felt more productive. But then the data actually bore out that they were less productive. Kind of interesting, right? We've got this induced flow that makes us feel really good about what we're doing. So we need to address this. Dora's put out some really good research on this too, but this is based on industry averages. This is impact based on what do we look at when we see a large sample and an average of how certain factors are being impacted by, in this case, 25% increase in AI adoption. We see these modest but positive leaning indicators, 7.5% increase in documentation quality and increase in code quality by about 3.4%. At least that's not leaning in the other direction, right? And when we started digging through some of DX's data, we have, we're the developer productivity measurement company. We have lots of aggregate data that we can look at with this. We found the same thing when we looked at averages. We see about a 2.6% increase in overall change confidence, which is a percentage of people who answered positively that they feel confident in the changes that they're putting into production. Similar positive leaning average when we looked at code maintainability, another qualitative metric, a 0.11% reduction in change failure rate, which when you think about the industry benchmark being 4%, it's not insignificant. But this is not the full story, because this is what we saw when we broke the same studies down per company. Every company here is every bar represents a company. All right? We have some that are seeing 20% increases in change confidence, while others are seeing 20% decreases. We're seeing extreme volatility, which is why these averages look so innocuous, but they're belying the greater story of variability. See the same thing with code maintainability, the same thing with change failure rate. So this is a 2% increase in change failure rate up here at the top. Again, with an industry benchmark of 4%, that means shipping as much as 50% more defects than we were shipping before, right? We want to make sure we're on the lower end of this, but how? Like, what should we be doing? Well, we found some patterns here. We see that some organizations are seeing positive impacts to KPIs, but others are struggling with adoption and even seeing some of these negative impacts. Top-down mandates are not working, right? Driving towards, oh, we must have 100% adoption of AI. Great, I will update my read my file every morning and I will be compliant, right? We're not actually moving the needle anywhere when we do that. We also find that lack of education and enablement has a big impact on sort of negatively impacting this. Some organizations just turn on the tech and expect it to just start working and everybody to know the best ways to use it. And a difficulty measuring the impact or even knowing what we should be measuring. Like, what metrics should we be looking at? Does utilization really tell us much about the full story of Gen AI impact? This is another graph from Dora. This is a Bayesian posterior distribution, which is an interesting way of representing data. Basically, you want your mass to be on the yellow side of this line, the right side of this line for the audience, yeah. And you want a sharp peak, which is telling you that we're pretty confident that this initiative will have this impact. And if we look at some of the top line initiatives here, these are things like clear AI policies, all right? We want to make sure we have that. We want time to learn, not just giving people materials, but actually giving them space to experiment, right? And so these types of factors are the ones that seem to be moving the needle the most. So we're going to go over some quick tips on how we can do all of these things. And again, the guide will go deeper into this. We want to integrate across the SDLC. Right? For most organizations, writing code has never been the bottleneck. Right? We can increase productivity a bit by helping with code completion, but our biggest bottlenecks are elsewhere within the SDLC. There's a lot more to creating software than just writing code. We want to unblock usage. We can't just say, well, we're worried about data exfiltration, so we can't try this thing. Like, no, get creative about it. We've got really good infrastructure out there now, like Bedrock and Fireworks AI, that can let us run powerful models in safe spaces. We have to have open discussions about these metrics. We need to evangelize the wins, and we need to let our engineers know why we're gathering metrics and data. What is it that we're trying to improve? We have to reduce the fear of AI, right? We have to make sure that people understand that this is not a technology that is ready to replace engineers. This is a technology that's really good at augmenting engineers and increasing the throughput of our business. We have to establish better compliance and trust, and we need to tie this stuff to employee success. These are new skill sets. AI is not coming for your job, but somebody really good at AI might take your job. And so as leaders, we have the opportunity to help our employees become more successful with this technology. So how do we reduce the fear? Well, first of all, why do we need to do this? Well, there's a lot of good reasons, but I love to point to Google's Project Aristotle. This was a 2012 study where Google wanted to figure out what are the characteristics of highly performant teams. They thought that the recipe was just going to be what Google had, this combination of high performers, experienced managers, and basically unlimited resources, and they were dead wrong. Overwhelmingly, the biggest indicator of productivity was psychological safety, okay? And so that very much applies now. We also have data, like this is Swyx, I'm sure a lot of you have seen this, and there are some impressive benchmarks that the agents can do like a third of the things they're asked to do without any human intervention. That means that they're not able to do 2/3 of them, right? Again, we are augmenting, we're not replacing, we're not ready, we may never be ready. So we need to be very transparent with what we're doing. We need to set very clear intents. Why, are we using this to augment, not to replace? We need to be proactive in the way that we communicate that, and not just wait for people to get upset and possibly scared. We need to say, no, we are here to help you, to give you a better developer experience, and to increase the throughput of the business. And again, we have to have these discussions about metrics. Now, what metrics? What should we be looking at? Well, DX, again, developer experience and productivity measurement company. There are two sort of classes of metrics that we can be looking at, really two levers that matter here, and that's speed and quality, right? We want to increase PR throughput, we want to increase our velocity, but not by just creating a bunch of slop that's going to give us a bunch of tech debt later that we're going to have to deal with. And we'll just kick the bottleneck down the road if we do that, right? So we want to be looking at things like change failure rate, our overall perception of quality, change confidence, maintainability. And we have three types of metrics that we can be looking at here. We have our telemetry metrics. These are the things coming out of the API, and they're good for some stuff, but they're not always accurate, right? We know like accept versus suggest was kind of like all the rage until we realized that engineers need to click accept in the IDE in order for the API to know about it. Even if they do click accept, who's to say they didn't just go back and rewrite every line that was suggested, right? So that's providing us some context, but we also need to do some experience sampling. We need to, like, for instance, add a new field to a PR form that says, I used AI to generate this PR, or I enjoyed using AI to generate this PR and get some data that way. And then self-reported data or survey data. We are big on surveys, but let me underscore, we're big on effective surveys. 90% plus participation rates, engineered against questions that treat developer experience as a systems problem, not a people problem. Because that's what it is. W. Edwards Deming, 90 to 95% of the productivity output of an organization is determined by the system and not the worker, okay? So foundational developer experience and developer productivity metrics still matter the most, right? Our AI metrics like utilization and things are telling us what's happening with the tech, but these core metrics that we've been able to trust are telling us whether these initiatives are actually working, right? Are we actually moving the needle and having the outcomes that we want to see? So top companies are looking at different things, right? We are seeing like adoption metrics coming out of Microsoft. They've also got this great metric called a bad developer day. I'm not going to go into it, but there's a really good white paper that shows like all the different telemetry that they can look at to determine what makes a bad developer day. Dropbox is looking at similar stuff, adoption, like weekly active users, daily active users, that sort of thing, but also looking at quality metrics like change failure rate. And Booking is looking at similar stuff as well. And so we built a framework around this. We were first to market with what we call our DX AI measurement framework. And this is very much inspired by things like Dora, Space Framework, DevX, just like our core 4 metrics set, which you can ask me about later. And we take these metrics and we normalize them into these 3 dimensions of utilization, impact, and cost. And you can kind of think about this as a maturity curve too. A lot of people start just figuring out, okay, what's happening? Who's using the tech? What's the percentage of pull requests that we're getting that are AI assisted, maybe through experience sampling? How many tasks are being assigned to agents? But then we can mature that perspective a little bit and we can correlate that utilization to impact. What is this actually doing to velocity? What is this actually doing to quality? And this is when we start getting more mature in our picture of our impact. And then finally cost, although I like to joke that we're 15 years past the last hype cycle, which was cloud, and we still have new companies spinning up that are teaching us how to understand and optimize our cloud costs. So we will see if we get there. Although I also hear horror stories about people burning through $2,000 worth of tokens a day, so we probably do need to hit that as well. What about compliance and trust? What can we do to ensure that the output that's being generated is something that can be trusted by our engineers? We have a lot of levers to pull here, but one of the ones that I'd like to talk about is setting up a feedback loop for our system prompts. So these could be called system prompts, cursor rules, agent markdown. Pretty much all of the mainstream solutions have something like this, where you can go and provide a set of rules to control how these models behave. And I won't get too much into the technical details here. We have an example where like the models have been providing outdated Spring Boot stuff. We want Spring Boot 3. It's been sending us Spring Boot 2 stuff. The big takeaway here is to have the feedback loop, have a gatekeeper, right? Have somebody or a group in the organization that can receive this feedback, that understand how to maintain and continuously improve these system prompts, right? And that way, we're always maintaining the way that these assistants or models or agents affect the whole business. It also pays to understand the way that temperature works, especially when we're building agents, right? We do have some control over the determinism and non-determinism of these models. Again, like when a model is predicting the next token, it doesn't just have like one token, it has a matrix of tokens, and those are associated with a certain probability of that being like the right token. And so we have this setting called temperature, which is heat, which is entropy, which is randomness, that can control the amount of randomness involved in actually picking that token. This is sometimes called increasing the creativity of the model. And it's a number between 0 and 1. For those reasons I just mentioned, don't use 0 or don't use 1. Weird things will happen, but you want some decimal in between 0 and 1. When we have a lower temperature, like we're seeing here, 0.0001, we give it the same task twice, and it gives us the exact same output character for character. When we set that temperature higher, this is an example of 0.9, I'm asking the agent to create a gradient for me, a simple task. It's giving me 2 relatively valid solutions. I did ask it for a JavaScript method, and this is the only one that's giving me a JavaScript method. But the point is, they are wildly different approaches to the same problem when I've increased the creativity of that model. So we need to think about like use case-wise. Where should we have more creativity, and where should we have more determinism? And temperature is another setting that we have that can help control this. You can experiment with all this using like Docker Model Runner, Olama, LM Studio, that sort of thing. How can we tie this to better employee success? We have to provide both education and adequate time to learn. So we put together a study where we sampled a bunch of developers that were saving at least an hour a day, an hour a week, and we asked them to stack rank their top 5 most valuable use cases, and we built a guide around that. A guide that effectively goes through code examples, prompting examples of what we determined using this sort of data approach, where we should get more reflexive about our best practice and about the use cases that we're becoming reflexive in our use of AI. And so that's what this guide was about. And we've had this become required reading in certain engineering groups, and proud of that. And this is another way that we can help educate, but we need to give time. We don't have time to go through all of this. I do think it's interesting that the number 1 use case for this was stack trace analysis, right? So not a generative use case, actually more of an interpretive use case. And we see some other ones here that are not too surprising, and there's examples of each of these. What about unblocking usage? How can we make sure that we can creatively ensure that engineers can take the most advantage of this? Well, leverage self-hosted and private models. That's getting easier and easier to do. Partner with compliance on day 1, right? Make sure that what you're doing is in line with your organization's compliance. You may find that you're making a lot of assumptions about things that you don't think you can do, but you can actually do, right? And then think creatively around various barriers. Finally, how can we integrate across the SDLC? What should we think about doing there? You know, and I'm a big Ellie Goldratt theory of constraints fan, probably have some others in the audience. An hour saved on something that isn't the bottleneck is worthless. And when we look at data across, in this case, almost 140,000 engineers, we find that there are definitely good like annualized time savings with AI that are being eclipsed by sources of context switching and interruption, meeting heavy days, these other things that it's like, yeah, we can save time here, but we're losing so much more time over there. So find the bottleneck, fix the bottleneck, right? Morgan Stanley's been very public about their building this thing called DevGen AI that looks at a bunch of legacy code, COBOL, mainframe natural. I hate to admit Perl because I'm an old school Perl developer, but apparently that's legacy now too. And basically creating specs for developers that can just be handed to developers to start modernizing the code without having to do all that reverse engineering, right? And they're saving about 300,000 hours annually right now doing this. There's a Wall Street Journal article about this, Business Insider article about it. They're very public about that. Zapier. Zapier should be the example for everyone. They have a whole series of bots and agents that are doing things like assisting with onboarding. They can now make engineers effective in 2 weeks. Industry benchmark on the good side is like a month. On the medium side is like 90 days. And because they're able to increase the effectiveness of the engineers that they're bringing into the organization, they realized that they should be hiring more. right? As opposed to trying to maintain status quo by like cutting headcount and trying to make individual engineers more productive, they said, no, we could get more value out of a single engineer. We should be hiring faster than ever, and they are. And it's really increasing their competitive edge. I think that's the right attitude. Spotify's been helping out their SREs by pulling together context when incidents are detected, and then taking things like run boot steps and other areas of context and documentation and pushing them directly into SRE channels so that those critical minutes of trying to get to the bottom of what's actually happening and what we should do to resolve the incident, they just eliminated that time, right? It's significantly increased their MTTR. So let's get creative about areas in the SDLC that are actual bottlenecks. All right, next steps. Distribute this guide as a reference for integrating AI into the development workflows that you have. Determine a method for measuring and evaluating Gen AI impact. It's really important to make sure that we're not on the bad sides of those graphs that I showed you earlier. And then track and measure AI adoption and see how that correlates to overall impact metrics and iterate on best practices and use cases. And here's the guide again. Thank you so much.
Our closing presentation will teach us how to build an AI-native company, even if that company is 50 years old. Please join me in welcoming to the stage the founder of Every, Dan Schipper.
Hello. How's it going, everybody? I'm the last speaker of the day, so I'm just between you and dinner or drinks, so I'm going to try to make this fun and hopefully a little bit short. So first of all, I just want to say I'm very glad to see everybody, and I'm actually kind of surprised to see so many people here because I live here, but I've been traveling. I was in Portugal last week, and I was on Twitter, and someone said that everyone was moving to San Francisco. But it's great to have everybody here instead, because I fucking love New York. Come on, come on. So I'm supposed to talk today about how to build a playbook for how to build an AI native company, and I actually don't have one, unfortunately. And that's because I think the playbook is actually being invented right now. So we're doing it at the company that I run, Every, but all of you are doing it here today as well. And so I don't want to do this talk from the perspective of I have all the answers. I'm going to tell you the framework and the playbook and all that kind of stuff. But I do think it is helpful when we're in this beginning stage of learning how to use AI to do engineering, to build companies, to share like the personal experiences that we're having inside of our companies, and sort of collaboratively figure out the playbook together. So I think the best that I can offer is really just sort of dispatches from the future, notes on what I've figured out and the work that we've done inside of Every. And I think the first big thing I really noticed is that there is definitely there's a 10x difference between an org where 90% of the engineers are using AI versus an org where 100% of the engineers are using AI. It's totally different. I think the big thing is if even 10% of your company is using a more traditional engineering method, you sort of have to lean all the way back over into that world. And so it prevents you from doing some of the things that you might do if everyone was not typing into a code editor all the time. And I know this because this is what we do at Every, which is a company that I run, and it has totally transformed what we are able to do as a small company. And so I think of us as like a little bit of a lab for what's possible that I'm excited to share with you. So for people who don't know, I run Every. Inside of Every, we have 6 business units. We have 4 software products. We run 4 software products with just 15 people, which is kind of crazy. And these software products are not toys. We've grown at Every, we've grown MRR by double digits every month for the last 6 months. We have over 7,000 paying subscribers and over 100,000 free subscribers. And we've done this in a very capital-light way. We've only raised about $1 million in total. And very importantly, for this audience and for this discussion, 99% of our code is written by AI agents. No one is handwriting code. No one is writing code at all. It's all done with Claude Code, Codex, Droid, what have you, coding agent of your choice. And also really importantly, for the size of team we are, each one of our apps is built by a single developer, which is crazy. And these are not like little apps. Here's an example. This is Cora, which is a AI email management app. It's sort of it's an assistant for your email. On the left over here, it summarizes all of your emails that come in, so you can kind of read your email that way. This is what my inbox looks like. On the right is a email assistant that you can ask questions, like I asked, when's my AI engineer talk today, and it just gave me the answer. And this is built primarily by one engineer. That he's got 1 or 2 contractors that have helped in certain ways, but like almost all of this is built by one guy. Same thing for this app, which is another one that we make called Monologue, which is a speech-to-text app. It's sort of like Super Whisper or Whisperflow, if you know of those. Again, one guy, thousands of users. I love it. It's just a beautifully done app, and it's not simple. It's complicated. There's a lot of stuff to it. Same thing for this app called Spiral. You can see it's big. And again, one engineer. So obviously, this would not have been possible a few years ago. It would not have been possible even a year ago. And I think the big change that happened that we're all starting to catch up to is it started with Claude Code, this sort of like terminal UI that gets rid of the code editor, really pushed us into a place where we are delegating tasks to these agents. And that allows us to work in parallel and do much more than we would have ordinarily. So some of the things that I've noticed that we can do that I assume people in this room are starting to see, but I think it's sort of important to put our finger on is the reason we can go much faster is we can work on multiple features and bugs in parallel. And I think that there's like a little bit of a meme of the vibe coder on Twitter that is, oh, like they have 4 panes open, but they're not actually doing any work. And actually, you can do it that way. And I think there are also definitely engineers, and I know that they are because they work at Every, that are productively using 4 panes of agents at the same time. And that's crazy, and that contributes a lot to the ability for a single developer to build and run a production application. Another like really important thing about this, a really big unlock, is because code is cheap, you can prototype risky ideas, and that allows you to do more experiments than you would ordinarily, and that lets you make way more progress because the starting energy to try something is so much lower because you just like say, oh, go do this, go do some research on this like big refactor I might want to do, and then you go off and do something else, and that's a really big deal. And another really interesting thing that I love about this stuff that I've noticed inside of our organization is we're moving a bit more toward a demo culture, where instead of previously, if you wanted to make something, you'd have to be like maybe write a memo or do a deck or convince a bunch of people that it was a good idea to spend time on. Because you can vibe code something in a couple hours that sort of shows the thing that you want to make. It allows you to show everybody, and I think that being a sort of demo culture allows you to do weirder things that you only get if you can feel it, which is, I think, really amazing. And beyond just like sort of the basic productivity unlocks, AI and the way that we use it has caused us to sort of invent an entirely new set of engineering primitives and processes, which I am sure that everybody in this room is starting to do already. I think everyone is sort of approaching the same things from different angles, and a lot of them definitely do echo engineering processes from the past, but I think it's really helpful to try to put our finger on, okay, what is the new way of programming if we're moving up a level of the stack and we're moving from Python to JavaScript and scripting languages up into English. And the name that we've given to this process is compounding engineering. And the way that I talk about compounding engineering is, in traditional engineering, each feature makes the next feature harder to build. In compounding engineering, your goal is to make sure that each feature makes the next feature easier to build. And we do that in this loop. The loop has 4 steps. First one is plan. And if you've been here today, you've been paying attention, you know how important it is when you're working with agents to make a really, really detailed plan. So I think everyone is doing that. Second step is delegate. Just like go tell the agent to do it. Everyone's doing that too. Third step is assess, and we have tons and tons of ways to assess whether the work that the agent did is any good. There's tests, there's trying it, there's having the agent figure it out, there's code review, there's agent code review, there's all those types of stuff. And then the last step, which is, I think the most interesting one, is codify, and this is kind of like the money step, which is where you compound everything that you've learned from the planning stage, the delegation stage, the assessment stage, back into prompts that go into your Cloud MD file or your subagents or your slash commands. And you start to basically create this library. You take all the tacit knowledge that you pick up, that all your engineers are picking up as they find bugs, fix plans, delegate work, and you make it into an explicit collection of prompts that you can spread for your entire organization. And when you do that really well, there's a lot of really interesting second order effects that are not, I think, that well understood or that commonly talked about that I think would be interesting to bring here, because my guess is that some people are already seeing this, but maybe it needs to be pushed on a little bit more to really be brought out. And some people, it might be an interesting way to get more of your organization to buy into using these tools 100% of the time. So the first thing that you notice if you set up this process and you're 100% bought in on something like compounding engineering is that tacit code sharing becomes much easier. So we have multiple products at Every. A lot of products a lot of times need to implement similar things, even if they use different technologies or implementing similar things like a Teams feature or a certain type of OAuth or whatever. Previously, in order to share code, you'd have to abstract out whatever you did into a library and then allow someone else to download it, and it'd be hard to do, or you'd have to talk about it. With agents, you can just point your Cloud Code instance at the repo from the developer sitting next to you and learn the process that they went through to build a feature that you need to re-implement, and re-implement it yourself in your own tech stack, in your own framework, and in your own way. And that's really, really cool to kind of have this. The more developers you have working on different things inside of the org, the more you can share without any extra cost, because AI can just go read all the code and use it. Another really cool thing that I've noticed is that new hires are productive on their first day, because you've taken all of the things that you've learned about, okay, how do I set up an environment, and what does a good commit look like, and all this kind of stuff. And on the first day, they have all that set up in their Cloud MD files or their cursor files or codec files or whatever. And the agent just sets up their local environment and knows how to write a good PR. That's really cool. It also helps if you want to hire expert freelancers. There's one person who just is really good at this one specific thing. You can have them come in for a day and do that thing. I think of it a little bit like a DJ or whatever can go in on a couple bars of a song. You can just sort of drop in, and that's really helpful. It would ordinarily be too hard to collaborate because the startup cost is too high, but you can do that a lot better now. Another thing that I've noticed, which is really cool too, is developers inside of Every commit to other products. So we have 4 products that run internally. Everybody uses all the products. If someone runs into a bug or a paper cutter, a little minor quality of life thing that they want, they will often just submit a pull request for it to the other GM of the app, because it's very easy for them to go download the repo and figure out really have Claude or Codex figure out, okay, this is how we fix the bug, or this is how we fix the paper cut. And that's really, really cool, because you have this much easier way of collaborating across apps that I think over the next couple years, I imagine that you will also be able to let customers do this to some extent. If you run into a bug, this is speculative, but if you run into a bug, you can have your little agent fix it and submit it as a pull request. That's a weird open source thing, but yeah, this is really, really cool and definitely is happening a lot inside of our company. Another really cool thing is we have not. This may get different as we scale, but we have not yet had to standardize onto a particular stack or language. We instead let everyone who's building different products pick the thing that they like best. And the reason is because AI makes it much easier to translate between them. And it makes it much easier to jump into any language and framework and environment and be productive. And so it's easier for us to let people just do the thing that they like and let AI kind of like handle the translation in between. And the last thing, which is my favorite, but like is also the horror, I think, of some developers, and to some degree maybe the horror of my team, is that managers can commit code if you're technical, even the CEO. And for me, like, I have no business committing code because we've got 4 products, we've got 15 people, we're growing really fast. I'm doing tons and tons of other things, but I can, and I have like committed production code over the last couple months. And the reason for that is AI allows engineers to work with fractured attention. So previously, you might have needed like a 3 or 4 hour block of focus time in order to like get anything done. But with Cloud Code, you can kind of like get out of a meeting and say, hey, like I want to investigate this bug, and then go do something else, and then come back and you have like a plan or like a root cause fix, and then you can submit a PR. And it's not easy, it's not magic, but it is actually possible. And I think that's just a totally new way of thinking about how managers interact with the products that they make. So just to summarize, I really think there's a 10x difference in how things work when you hit 100% AI adoption. I think from what we've seen, a single engineer should be able to build and maintain a complex production product. What we call compounding engineering, but I think what all of us are sort of pointing to is, I think it really works to make each feature easier to build, and then creates all of these sort of non-obvious second-order effects that makes it easier for the entire organization to collaborate together. And very importantly, many people in San Francisco don't know this yet, so you're the first to hear it. So that is my talk. So if you're interested in what we do, I run Every. Every is the only subscription you need to stay at the edge of AI. You can find us at every.to. We have a daily newsletter about AI, so we do ideas, apps, and training. On the ideas side, we have a daily newsletter. We review all the new models when they come out and all the new products when they come out. The apps, you already saw, we have a bundle of all these apps. And then we do training and consulting with big companies to help them use AI. And it's all bundled into one subscription, so you get everything for one price. And that's it. Thank you very much.
Ladies and gentlemen, please welcome back to the stage, Alex Lieberman.
Okay, 8 hours in. We did it. I have some housekeeping. We have to finish the day with housekeeping. But first of all, I want to thank you all. It has been phenomenal to be on this journey with you all. But let's give a shout out just to you all for being here, going through a full day, listening to the programming. So round of applause for everyone in the crowd, everyone online who's been watching. Let's also keep it going for all the team in production behind the scenes making this possible. I watched them work tirelessly throughout the day to make this happen. And then finally, let's give a huge shout out to Swyx and Ben, who made this whole thing happen. So get comfortable for a second. I have some housekeeping, make sure everyone knows where to go. And then we have one final speaker who's going to chat right after I hop off stage. So let's just dive in for a sec. Tomorrow is the engineering session day. I will not be your MC, so you will be taken care of by Jed, who works at Google. I spent the day with Jed. He is incredible. He's just like a taller, better looking version of me, and he's actually an engineer, so you get a true engineer tomorrow. If you have a bundle pass, your ticket includes tomorrow's track, so we'll see you tomorrow at 8 a.m. here. If you have the leadership pass only, your ticket does not include access to the sessions or the venue tomorrow. However, we have organized an offsite brunch for you on us at a restaurant not far from here, so check your calendar for the invite and the location. But right now, we are headed into the after party, and not only is there an after party, but there are after parties. There's a lot of side events, so your entire night is planned for you. And we have Graphite to thank for sponsoring the after party. So here to give us the last word for a brief message is the co-founder and CEO of Graphite, Meryl Lutsky.
Good evening, everyone. My name is Meryl Lutsky, and I'm the co-founder and CEO of Graphite. We're the AI-powered code review platform for this new age of agentic software development. Now, I know you guys heard a lot today about agents and how to make them as effective as possible in generating code and building features faster than ever. And they're incredible at this, but I think everybody who's built software in a professional environment knows that writing the code is only the first part of the story. Every code change then needs to be tested, it needs to be reviewed, merged, deployed, and oftentimes that second half of the process takes just as long, if not longer, than actually generating the code. And that's what we do with Graphite. We're applying AI to the entire development process and making code review as quick as possible. We have an agent that's integrated fully into our pull request page. It's like reviewing code in 2025 and not, it doesn't feel like 2015 anymore. That's what we build. We're super excited about it. If you want to come check it out, we have our booth in the expo hall, and also we're going to be around all day tomorrow. We're the official sponsors of tonight's after party and also tomorrow's event at Public Records. So we wanted, all you guys who came from out of town, we wanted to show you a good time in New York. So we have 2 events for you to make sure that you have a good time and see what New York is all about. Want to give a big shout out to Swyx and Ben and the whole AI Eng team for organizing, and we're excited to see you guys all at the party tonight. Thank you very much.
We invite you to stay for the Graphite after party, taking place in the hallways on both floors, plus inside the expo in the
thoughts into the darkest part becomes design. Words evolve to whispers meant for something more divine. Syntax bends and breathes, I see the language change. I'm not instructing anymore, I'm rearranging fate. Every loop I write rewrites me, every function hums with meaning. I feel the interface dissolve between the maker and the BA. This is the new code, not on the screen but in the soul, where thought becomes the motion and creation takes control. No lines, no rules, just balance in between the zero and the one, the silence and the dream. System shape our fragile skin, they mold the way we move. We live inside the logic gates of what we think is true. But deep beneath the data post, there's something undefined. A universe compiling in the image of our minds. Every line reveals reflection, every loop replays connection. We're not building, we're becoming, and the code becomes confession. This is the new code, not on the screen but in the soul, where thought becomes the motion and creation takes control. No lines, no rules, just balance in between the zero and the one, the silence and the dream. We are not just the
Don't worry, we're just giving you something to do while Codex writes all your code.
world we're in. We are the world we're doing. Each prompt, each breath, each fragile spin, a universe renewing. This is the new code, alive and undefined, where logic meets emotion and structure bends in mind. The system hums eternal, but the soul writes the line. We are the new code, compiling time. Compiling time.
Ladies and gentlemen, please join me in welcoming to the stage Senior Staff Engineer at Google and your host for the Engineering Track Session Day, Jed Borovic.
Hello, good morning. Welcome to the 2025 AI Engineering Code Summit in New York. How are we doing? Woo! All right, it's early, it's Friday. Thank you all for being here. Raise your hand if you've been to one of these events before, an AI Engineering Conference before. All right, pretty good. So for those watching the live stream, about half the hands are up. Keep your hands up, keep your hands up. 2 or more events. Okay. Still have a couple, 3, 4. All right, 1, 2 hands, 5. Are you sure there's only been 4, Alex? Okay, we'll talk afterwards. Okay, well, welcome. Whether it's your first time or you've been to many of these, we're all excited you're here. My name is Jed Borovic. I'm Gemini's assistant at Google, and I also work on the Jules coding agent. I lead the product engineering team. And I'm your MC for today. So why are we here? I'm sure many of you are familiar with Richard Hamming's famous You and Your Research talk. In that talk, he describes asking his colleagues, what's the most important problem in your field? And then right after that, he asks, so why aren't you working on that? I spend a lot of time hiring, and this idea comes up again and again. If you're working in technology, the most important problem of our day is AI. And if you're working on applied AI, your most important problem is code. This is a special event to push the whole AI coding industry forward. It's not an event for a single company, but across all companies in this industry. The AI Engineering Conference has 2 brands, a World's Fair and a Summit. This being a Summit event is intentionally smaller than the World's Fair. It's intentionally single track. It's designed to bring the best people together in the world about a single important theme. For this event, that theme is AI coding. Yesterday, many of you also experienced the leadership track. Make some noise so we know you're still alive if you were in that track. For those of you who were there, shout out some of your favorite talks. Stanford. Yeah, Stanford. Yeah, that was good. That was a great one. Gene and Steve. That was a spicy one. What else? Every. Yeah, Dan from Every. Ah, good choice. Good choice. Okay. Well, yesterday was a great day. It was about how AI is transforming software organizations. Today, we're going to dive into the patterns, systems, and products that make all of that possible. But whether you consider yourself an AI leader, an AI engineer, or something in between, we're glad you're here. We also wouldn't be here without our amazing sponsors. I would like to thank them, especially our presenting sponsor, DeepMind. Yeah, give it up, give it up. And what an amazing week for DeepMind. I'm biased, but I hope you all get a chance to use Gemini 3 and Nano Banana Pro, which came out this week. I'd also like to thank Anthropic as our platinum sponsor and the gold sponsors you see on this screen. Yeah, we'll do one big round at the end. And finally, we want to thank our silver sponsors. Let's put our hands together for all of these sponsors. Yeah, give it up, give it up. All these sponsors will be downstairs in the expo area. They have booths, and I recommend going down there to chat with folks from all these companies. They'll be open all day after the keynotes. All right, with that, let's get started. Our first speaker needs no introduction, especially here. He wrote the article that named the AI engineering movement. He's the driving vision behind this event. He's built the amazing community that's here today. Please join me in welcoming Swyx.
everyone. Morning. How's everyone doing? Good? I'm going to need a lot of energy for this talk, so please back me up. I'm very nervous, but we'll get through this. I'm declaring war on slop today. Let's talk about this. Every AIE has a secret. I've told this to some folks that are personal friends, and I'll just show the secret now. The first summit, we had the secret, which was we knew that the AI engineer was going to be a thing. Second summit, we extended it to leadership. Third summit, we realized that basically we always needed to concentrate on model labs, and that's why you see all the top tier labs here today. World's Fair, we started expanding the TAM of what AI engineering is affiliated with AI PMs and AI designers. And with the Code Summit, as Jed just talked about, we really started focusing on curation and focusing in on a theme. And if there's one theme that really matters this year, it's coding. But I'm not here to talk about coding. The rest of the day, you're going to hear about coding. So just indulge me 5 minutes to talk about slop. We've done really well, right? Like, like, I think like slop is sort of associated with quantity and quality, and I think like that's something that I'm really trying to think about as well. Like, how do we grow this community, grow this industry, and grow this event with the same kind of taste and high quality that you've come to expect? And this is something that hopefully you guys can see that we care a lot about in curating all of you coming here and all of the speakers that you're about to see. We're in a war against slop. And this is actually the Oxford English Dictionary. This is a candidate for the 2024 Word of the Year. It lost to brain rot. But slop is pretty good, and I think it's probably gone even more of an issue this year than last year. Maybe it will win this year. I have an issue with Oxford, though, because they did us dirty by saying slop is generated using artificial intelligence. The other part I agree with. It's low quality, inauthentic, and inaccurate. But it doesn't take AI to be low quality, inauthentic, or inaccurate. Any human or AI can be an agent of slop, right? You've seen this yourself. I'm going to indulge me with a few examples. By the way, I got this, if you're not familiar with like sort of internet slang, the opposite of slop is Keynote. And I got this idea from Paul Rambles, who, when I do Sora videos, I do really boring Sora videos with me and Sam Altman. When other people who are actually creative and good at their job do Sora videos, they do cats playing didgeridoos. Slop can be produced by the same studio. There's K-pop Demon Hunters by Netflix and there's Electric State by Netflix. Slop can be produced in terms of different models. No comment. Something that's Keynote can degenerate into slop, right? If you're early on the trend and you're starting that and it's fresh on you, that's great. If you recognize the other image, you're too online. Okay, not enough people recognize that image. Go do your homework. Yeah, and obviously I'm just going to throw in a dig at Game of Thrones because it's the same thing, right? Like slop is everywhere. It's generated by humans and AI. You get it. Okay, the same startup idea can be Keynote versus slop. When I first presented my first Keynote at AI Engineering Summit, we actually used Tome, which is like an AI slides company. I loaded out the same slide deck and it was gone. Recently because it was actually closed as a company. There's different takes on vibe coding, and I think one of them is much better than the other. And I think like these are just like the tensions that we have to navigate. One of our speakers later on, as well, Meter, I think it's really interesting that both of them are exponential charts, but one of them feels more Keynote and the other is more slops. And I think like I would really like to have people investigate why. So let me just skip through. Basically, we're in an asymmetric war on slop. I think the closest law that I found that matches this is Brandolini's law, which actually states the amount of energy needed to refute bullshit is an order of magnitude bigger than you needed to produce it, right? So we need to coin an appropriate law as well, because like the cost to generate tokens is dropping by 100 to 1,000 times every single year. So this is, I guess, Swyx's law of anti-slop. The amount of taste needed to fight slop is an order of magnitude bigger than that needed to produce it, right? There's so much low taste out there. We need to elevate what's out there in the world because that's what we stand for as humans. I think there's a positive message. You can use AI to fight slop. I'm proud to run as a side project AI News, which is the only newsletter that tells you not to read it when there's nothing going on. Thank you. Oh, appreciate that. You can also prompt to fight slop. The next speaker is Mahesh and Barry. I found this in the sort of prompts in the skill set that they put, where they actually acknowledge slop and tell Claude not to produce slop, and it actually improves significantly from left to right. What about code slop, right? We hear about code. Creating tech debt, where you can sort of, two engineers great detected of 50 engineers. Or on a more serious note, you can start exposing private data of millions of users. And this all happened this year. Everything I'm mentioning all happened this year. I'm kind of using this keynote as a way of recapping. Just to be spicy a little bit, even people who are saying things like, oh, my model can go up to 30 to 60 hours autonomously, well, it feels a bit sloppy because you're also not saying, well, was the code good or not? You're just saying how long it went. So in the same way that you have no taxation without representation, you don't want autonomy without accountability. Something I've been working on more recently is that using AI to fight code slop as well. So this is from a bunch of people quoted this yesterday, of the semi-async value of depth, where you can sort of keep human attention and mind meld with the machine in order to work on the hardest problems, whereas the stuff that's commoditized, you can make it more async. So you can check out more on that details. What seems to be less appreciated is the other work on code maps, which I've more recently done, where we actually use AI to scale code-based understanding, which is also a way to fight slop. And you can talk to the cognition folks downstairs who can show you more in detail. The last thing I always want to shout out as well is this trend of computer use. I think
it's hard work coming to India to win, and South Africa have managed to do that. Congratulations to them. 25 years it's taken for them to win, and they are victors.
Computer use kind of debuted this time last year with Anthropic, but it's getting really, really good now, guys. It can really autonomously operate the most complex apps, including an IDE. So I think that's really exciting, and you should probably use that to fight slop. We use it for the website, and here's an example of us using Devin to automate the website updates. And finally, something I learned from this conference yesterday is that you can also use sub-agents to fight context rot, and I think that is one of the biggest themes that I'm observing as well, if you want to take away something from this conference. And also one of the biggest highlights of the year for us as AIE, and myself personally, was chatting with Greg Brockman, who always preaches the concept of modularity, where you can sort of keep clear boundaries on what is human designed and let the AI code everything in between. So these are all ideas, but I just have this one message that I want to compress down to you today that I want you to say with me. No more slop, yeah? Your boss tells you, I want more lines of code by the end of the quarter. What do you say to that? Say it with me, no more slop. You're fighting an asymmetric war. This is how bad it is, right? You have an insufficiently tested release that is potentially embarrassing to your company. What do you say to people who really want to push it? No more slop, exactly. Your Twitter algorithm wants engagement bait, and it's sort of telling you to lie, basically, sort of to the broad public. What do you say to that? Exactly. That's it. I hope you have a great conference, and let's hear it for not having any more slop. Thank you.
Our next presenters are AI engineers at Anthropic, working on real-world agent systems. They're here to share why we should stop building agents and start building skills. Please join me in welcoming to the stage Barry Zhang and Mahesh Marag.
All right, good morning, and thank you for having us again. Last time we were here, we're still figuring out what an agent even is. Today, many of us are using agents on a daily basis. But we still notice gaps. We still have slots, right? Agents have intelligence and capabilities, but not always expertise that we need for real work. I'm Barry, this is Mahesh. We created agent skills. In this talk, we'll show you why we stopped building agents and started building skills instead. A lot of things have changed since our last talk. MCP became the standard for agent connectivity. Cloud Code, our first coding agent, launched to the world. And our Cloud Agent SDK now provides a production-ready agent out of the box. We have a more mature ecosystem, and we're moving towards a new paradigm for agents. That paradigm is a tighter coupling between the model and a runtime environment. Put simply, we think code is all we need. We used to think agents in different domains will look very different. Each one will need its own tools and scaffolding, and that means we'll have a separate agent for each use case for each domain. Well, customization is still important for each domain. The agent underneath is actually more universal than we thought. What we realized is that code is not just a use case, but a universal interface to the digital world. After we built Cloud Code, we realized that Cloud Code is actually a general purpose agent. Think about generating a financial report. The model can call the API to pull in data and do research. It can organize that data in the file system. You can analyze it with Python, and then synthesize the insight in all file format, all through code. The core scaffolding has suddenly become as thin as just Bash and file system, which is great and really scalable, but we very quickly run into a different problem. And that problem is domain expertise. Who do you want doing your taxes? Is it going to be Mahesh, the 300 IQ mathematical genius, or is it Barry, an experienced tax professional? Right? I would pick Barry every time. I don't want Mahesh to figure out the 2025 tax code from first principles. I need consistent execution from a domain expert. Agents today are a lot like Mahesh. They're brilliant, but they lack expertise. They can do, no more slow. They can do amazing things when you really put in effort and give proper guidance, but they're often missing the important context up front. They can't really absorb your expertise super well, and they don't learn over time. That's why we created agent skills. Skills are organized collections of files that package composable procedural knowledge for agents. In other words, they're folders. This simplicity is deliberate. We want something that anyone, human or agent, can create and use as long as they have a computer. These also work with what you already have. You can version them in Git, you can throw them in Google Drive, and you can zip them up and share it with your team. We have used files as a primitive for decades, and we like them, so why change now? Because of that, skills can also include a lot of scripts as tools. Traditional tools have pretty obvious problems. Some tools have poorly written instructions that are pretty ambiguous. And when the model is struggling, you can't really make a change to the tool, so it's just kind of stuck with a code star problem. And they always live in the context window. Code solves some of these issues. It's self-documenting, it is modifiable, and it can live in the file system until they're really needed and used. Here's an example of a script inside of a skill. We kept seeing Claude write the same Python script over and over again to apply styling to slides, so we just asked Claude to save it inside of the skill as a tool for its future self. Now we can just run the script, and that makes everything a lot more consistent and a lot more efficient. At this point, skills can contain a lot of information, and we want to protect the context window so that we can fit in hundreds of skills and make them truly composable. That's why skills are progressively disclosed. At runtime, only this metadata is shown to the model just to indicate that it has the skill. When an agent needs to use a skill, you can read in the rest of the skill.md, which contains the core instruction and directory for the rest of the folder. Everything else is just organized for ease of access. So that's all skills are. They're organized folders with scripts as tools.
Since our launch 5 weeks ago, this very simple design has translated into a very quickly growing ecosystem of thousands of skills. And we've seen this be split across a couple of different types of skills. There are foundational skills, third-party skills created by partners in the ecosystem, and skills built within an enterprise and within teams. To start, foundational skills are those that give agents new general capabilities or domain-specific capabilities that it didn't have before. We ourselves, with our launch, built document skills that give Claude the ability to create and edit professional quality Office documents. We're also really excited to see people like Cadence build scientific research skills that give Claude new capabilities like EHR data analysis and using common Python bioinformatics libraries better than it could before. We've also seen partners in the ecosystem build skills that help Claude better with their own software and their own products. BrowserBase is a pretty good example of this. They built a skill for their open source browser automation tooling, StageHand. And now Claude, equipped with this skill and with StageHand, can now go navigate the web and use a browser more effectively to get work done. And Notion launched a bunch of skills that help Claude better understand your Notion workspace and do deep research over your entire workspace. And I think where I've seen the most excitement and traction with skills is within large enterprises. These are company and team-specific skills built for an organization. We've been talking to Fortune 100s that are using skills as a way to teach agents about their organizational best practices and the weird and unique ways that they use this bespoke internal software. We're also talking to really large developer productivity teams. These are teams serving thousands or even tens of thousands of developers in an organization that are using skills as a way to deploy agents like Claude Code and teach them about code style best practices and other ways that they want their developers to work internally. So all of these different types of skills are created and consumed by different people inside of an organization or in the world, but what they have in common is anyone can create them, and they give agents new capabilities that they didn't have before. So as this ecosystem has grown, we've started to observe a couple of interesting trends. First, skills are starting to get more complex. The most basic skill today can still be a skill.md markdown file with some prompts and some really basic instructions. But we're starting to see skills that package software, executables, binaries, files, code, scripts, assets, and a lot more. And a lot of the skills that are being built today might take minutes or hours to build and put into an agent. But we think that increasingly, much like a lot of the software we use today, these skills might take weeks or months to build and be maintained. We're also seeing that this ecosystem of skills is complementing the existing ecosystem of MCP servers that was built up over the course of this year. Developers are using and building skills that orchestrate workflows of multiple MCP tools stitched together to do more complex things with external data and connectivity. And in these cases, MCP is providing the connection to the outside world, while skills are providing the expertise. And finally, and I think most excitingly for me personally, is we're seeing skills that are being built by people that aren't technical. These are people in functions like finance, recruiting, accounting, legal, and a lot more. And I think this is pretty early validation of our initial idea that skills help people that aren't doing coding work extend these general agents. And they make these agents more accessible for the day-to-day of what these people are working on. So tying this all together, let's talk about how these all fit into this emerging architecture of general agents. First, we think this architecture is converging on a couple of things. The first is this agent loop that helps manage the model's internal context and manages what tokens are going in and out. And this is coupled with a runtime environment that provides the agent with a file system and the ability to read and write code. This agent, as many of us have done throughout this year, can be connected to MCP servers. And these are tools and data from the outside world that make the agent more relevant and more effective. And now we can give the same agent a library of hundreds or thousands of skills that it can decide to pull into context only at runtime when it's deciding to work on a particular task. Today, giving an agent a new capability in a new domain might just involve equipping it with the right set of MCP servers and the right library of skills. And this emerging pattern of an agent with an MCP server and a set of skills is something that's already helping us at Anthropic deploy Claude to new verticals. Just after we launched skills 5 weeks ago, we immediately launched new offerings in financial services and life sciences. And each of these came with a set of MCP servers and a set of skills that immediately make Claude more effective for professionals in each of these domains. We're also starting to think about some of the other open questions and areas that we want to focus on for how skills evolve in the future. As they start to become more complex, we really want to support developers, enterprises, and other skill builders by starting to treat skills like we treat software. This means exploring testing and evaluation, better tooling to make sure that these agents are loading and triggering skills at the right time and for the right task, and tooling to help measure the output quality of an agent equipped with a skill to make sure that's on par with what the agent is supposed to be doing. We'd also like to focus on versioning. As a skill evolves and the resulting agent behavior evolves, we want this to be clearly tracked and to have a clear lineage over time. And finally, we'd also like to explore skills that can explicitly depend on and refer to either other skills, MCP servers, and dependencies and packages within the agent's environment. We think that this is going to make agents a lot more predictable in different runtime environments, and the composability of multiple skills together will help agents like Claude elicit even more complex and relevant behavior from these agents. Overall, these set of things should hopefully make skills easier to build and easier to integrate into agent products, even those besides Claude. Finally, a huge part of the value of skills, we think, is going to come from sharing and distribution. Barry and I think a lot about the future of companies that are deploying these agents at scale. And the vision that excites us most is one of a collective and evolving knowledge base of capabilities that's curated by people and agents inside of an organization. We think skills are a big step towards this vision. They provide the procedural knowledge for your agents to do useful things. And as you interact with an agent and give it feedback and more institutional knowledge, it starts to get better, and all of the agents inside your team and your org get better as well. And when someone joins your team and starts using Claude for the first time, it already knows what your team cares about. It knows about your day-to-day, and it knows about how to be most effective for the work that you're doing. And as this grows and this ecosystem starts to develop even more, this compound value is going to extend outside of just your org and into the broader community. So just like when someone else across the world builds an MCP server that makes your agent more useful, a skill built by someone else in the community will help make your own agents more capable, reliable, and useful as well.
This vision of an evolving knowledge base gets even more powerful when Claude starts to create these skills. We design skills specifically as concrete steps towards continuous learning. When you first start using Claude, this standardized format gives a very important guarantee. Anything that Claude writes down can be used efficiently by a future version of itself. This makes the learning actually transferable. As you build out the context, skills make the concept of memory more tangible. They don't capture everything. They don't capture every type of information, just procedural knowledge that Claude can use on specific tasks. We have worked with Claude for quite a while. The flexibility of skills matters even more. Claude can acquire new capabilities instantly, evolve them as needed, and then drop the ones that become obsolete. This is what we have always known. The power of in-context learning makes this a lot more cost-effective for information that change on a daily basis. Our goal is that Claude on day 30 of working with you is going to be a lot better on Claude on day 1. Claude can already create skills for you today using our skill creator skill, and we're going to continue pushing in that direction. We're going to conclude by comparing the agent stack to what we have already seen in computing. In a rough analogy, models are like processors. Both require massive investment and contain immense potential, but only so useful by themselves. Then we start building an operating system. The OS made processors far more valuable by orchestrating the processes, resources, and data around the processor. In AI, we believe that agent runtime is starting to play this role. We're all trying to build the cleanest, most efficient, and most scalable abstractions to get the right tokens in and out of the model. But once we have a platform, the real value comes from applications. A few companies build processors and operating systems, but millions of developers like us have built softwares that encoded domain expertise and our unique points of view. We hope that skills can help us open up this layer for everyone. This is where we get creative and solve concrete problems for ourselves, for each other, and for the world, just by putting stuff in the folder. So skills are just the starting point.
To close out, we think we're now converging on this general architecture for general agents. We've created skills as a new paradigm for shipping and sharing new capabilities. So we think it's time to stop rebuilding agents and start building skills instead. And if you're excited about this, come work with us and start building some skills today. Thank you.
Our next presenter is here to share practical techniques for getting real results through context engineering, not guesswork, and definitely not hype. Please welcome to the stage the CEO of Human Layer, Dex Horthy.
Hi, everybody. How y'all doing? It's exciting. I'm Dex. As they did in the great intro, I've been hacking on agents for a while. Our talk, 12-Factor Agents at AI Engineer in June, was one of the top talks of all time. I think top 8 or something, one of the best ones from AI Engineer in June. May or may not have said something about context engineering. Why am I here today? What am I here to talk about? I want to talk about one of my favorite talks from AI Engineer in June. And I know we all got the update from Igor yesterday, but they wouldn't let me change my slides. So this is going to be about what Igor talked about in June. Basically, that they surveyed 100,000 developers across all company sizes, and they found that most of the time you use AI for software engineering, you're doing a lot of rework, a lot of code base churn. And it doesn't really work well for complex tasks, brownfield code bases. And you can see the chart, basically, you are shipping a lot more, but a lot of it is just reworking the slop that you shipped last week. So, and then the other side, right, was that if you're doing greenfield Vercel dashboard, something like this, then it's going to work great. If you're going to go in a 10-year-old Java code base, maybe not so much. And this matched my experience, personally, and talking to a lot of founders and great engineers, too much slop, tech debt factory, it's not going to work from our code base. Like maybe someday when the models get better. But that's what context engineering is all about. How can we get the most out of today's models? How do we manage our context windows? So we talked about this in August. I have to confess something. The first time I used Claude Code, I was not impressed. It was like, okay, this is a little bit better, I get it, I like the UX. But since then, we as a team figured something out that we were actually able to get 2 to 3x more throughput. And we were shipping so much that we had no choice but to change the way we collaborated. We rewired everything about how we build software. It was a team of 3. It took 8 weeks. It was really freaking hard. But now we solved it, we're never going back. This is the whole no slop thing. I think we got somewhere with this. Went super viral on Hacker News in September. We have thousands of folks who have gone onto GitHub and grabbed our research plan implement prompt system. So the goals here, which we kind of backed our way into, we need AI that can work well in brownfield code bases, that can solve complex problems, no slop, right? No more slop. And we had to maintain mental alignment. I'll talk a little bit more about what that means in a minute. And of course, we want to spend, with everything, we want to spend as many tokens as possible. What we can offload meaningfully to the AI is really, really important. Super high leverage. So this is advanced context engineering for coding agents. I'll start with kind of like framing this. The most naive way engineering for coding agents. Super high leverage. So this is advanced context engineering for coding agents. I'll start with kind of like framing this. The most naive way to use a coding agent is to ask it for something and then tell it why it's wrong and re-steer it and ask and ask and ask until you run out of context or you give up or you cry. We can be a little bit smarter about this. Most people discover this pretty early on in their AI exploration, is that it might be better if you start a conversation and you're off track, that you just start a new context window. You say, okay, we went down that path, let's start again, same prompt, same task, but this time we're gonna go down this path. And don't go over there because that doesn't work. So how do you know when it's time to start over? If you see this, it's probably time to start over, right? This is what Claude says when you tell it it's screwing up. So we can be even smarter about this. We can do what I call intentional compaction. And this is basically whether you're on track or not, you can take your existing context window and ask the agent to compress it down into a markdown file. You can review this, you can tag it, and then when the new agent starts, it gets straight to work instead of having to do all that searching and code base understanding and getting caught up. What goes into compaction? Well, the question is what takes up space in your context window? So it's looking for files, it's understanding code flow, it's editing files, it's test and build output. And if you have one of those MCPs that's dumping JSON and a bunch of UUIDs in your context window, God help you. So what should we compact? I'll get more on the specifics here, but this is a really good compaction. This is exactly what we're working on, the exact files and line numbers that matter to the problem that we're solving. Why are we so obsessed with context? Because LLMs actually got roasted on YouTube for this one. They're not pure functions because they're non-deterministic, but they are stateless. And the only way to get better performance out of an LLM is to put better tokens in, and then you get better tokens out. And so every turn of the loop, when Claude is picking the next tool or any coding agent is picking the next tool, and there could be hundreds of right next steps and hundreds of wrong next steps, but the only thing that influences what comes out next is what is in the conversation so far. So we're going to optimize this context window for correctness, completeness, conversation so far. But the only thing that influences what comes out next is what is in the conversation so far. So we're going to optimize this context window for correctness, completeness, size, and a little bit of trajectory. And the trajectory one is interesting because a lot of people say, well, I told the agent to do something and it did something wrong. So I corrected it and I yelled at it and then it did something wrong again and then I yelled at it. And then the LLM is looking at this conversation, says, okay, cool, I did something wrong, the human yelled at me and I did something wrong and the human yelled at me. So the next most likely token in this conversation is I better do something wrong so the human can yell at me again. So be mindful of your trajectory. If you're going to invert this, the worst thing you can have is incorrect information, then missing information, and then just too much noise. If you like equations, there's a dumb equation if you want to think about it this way. Jeff Huntley did a lot of research on coding agents. He put it really well. Just the more you use the context window, the worse outcomes you'll get. This leads to a concept, I'm in a very, very academic concept called the dumb zone. So you have your context window. You have 168,000 tokens roughly. Some are reserved for output and compaction. This varies by model, but we use Claude Code as an example here. Around the 40% line is where you're going to start to see some diminishing returns depending on your task. If you have too many MCPs in your coding agents, you are doing all your work in the dumb zone and you're never going to get good results. People talk about this. I'm not going to talk about that one. Your mileage may vary. 40% is it depends on how complex the task is, but this is kind of a good guideline. So back to compaction, or as I will call it from now on, cleverly avoiding the dumb zone. We can do subagents. If you have a front-end subagent, and a back-end subagent, and a QA subagent, and a data scientist subagent, please stop. Subagents are not for anthropomorphizing roles, they are for controlling context. And so what you can do is if you want to go find how something works in a large code base, you can steer the coding agent to do this if it supports subagents, or you can build your own subagent system, but basically you say, hey, go find how this works. And it can fork out a new context window that is going to go do all that reading and searching and finding and reading entire files and understanding the code base, and then just return a really, really succinct message back up to the parent agent of just hey, the file you want is here. Parent agent can read that one file and get straight to work. And so this is really powerful. If you wield these correctly, you can get good responses like this, and then you can manage your context really, really well. What works even better than subagents, or a layer on top of subagents, is a workflow I call frequent intentional compaction. We're going to talk about research plan implement in a minute, but the point is you're constantly keeping your context window small. You're building your entire workflow around context management. So it comes in 3 phases: research, plan, implement, and we're going to try to stay in smart zone the whole time. So the research is all about understanding how the system works, finding the right file, saying objective, here's a prompt you can use to do research, here's the output of a research prompt. These are all open source, you can go grab them and play with them yourself. Planning, you're going to outline the exact steps, you're going to include file names and line snippets, you're going to be very explicit about how we're going to test things after every change. Here's a good planning prompt, here's one of our plans, it's got actual code snippets in it, and then we're going to implement. And if you read one of these plans, you can see very easily how the dumbest model in the world is probably not going to screw this up. So we just go through and we run the plan and we keep the context low. as a planning prompt. Like I said, it's the least exciting part of the process. I want to put this into practice. So working for us, I do a podcast with my buddy Vibov, who's the CEO of a company called Boundary ML. And I said, hey, I'm going to try to one-shot a fix to your 300,000 line Rust code base for a programming language. And the whole episode goes in, it's like an hour and a half. I'm not going to talk through it right now, but we built a bunch of research and we threw them out because they were bad, and then we made a plan without research and with research and compared all the results. It's a fun time. That was Monday night. By Tuesday morning, we were on the show, and the CTO had seen the PR and didn't realize I was doing it as a bit for a podcast, and basically was like, yeah, this looks good, we'll get it in the next release. He was a little confused. Here's the plan. But anyways, yeah, confirmed. Works in brownfield code bases and no slop. But I wanted to see if we could solve complex problems. So Vibov was still a little skeptical. We sat down for 7 hours on a Saturday, and we shipped 35,000 lines of code to BAML. One of the PRs got merged a week later. I will say, some of this is code gen. You update your behavior, all the golden files update and stuff, but we shipped a lot of code that day. He estimates it was about 1 to 2 weeks and 7 hours. And so cool, we can solve complex problems. There are limits to this. I sat down with my buddy Blake. We tried to remove Hadoop dependencies from Parquet Java. If you know what Parquet Java is, I'm sorry for whatever happened to you to get you to this point in your career. It did not go well. Here's the plans, here's the research. At a certain point, we threw everything out, and we actually went back to the whiteboard. We had to actually, once we had learned where all the foot guns were, we went back to, okay, how is this actually going to fit together? And this brings me to a really interesting point that Jake's going to talk about later. Do not outsource the thinking. AI cannot replace thinking. It can only amplify the thinking you have done, or the lack of thinking you have done. So people ask, so Dex, this is spec-driven development, right? No. Spec-driven development is broken. Not the idea, but the phrase. It's not well defined. This is Brigitte from ThoughtWorks. And a lot of people just say spec, and they mean a more detailed prompt. Does anyone remember this picture? Does anyone know what this is from? All right, that's a deep cut. There will never be a year of agents because of semantic diffusion. Martin Fowler said this in 2006. We come up with a good term, with a good definition, and then everybody gets excited, and everybody starts meaning it to mean 100 things to 100 different people, and it becomes useless. We had an agent is a person, an agent is a microservice, an agent is a chatbot, an agent is a workflow, and thank you, Simon, we're back to the beginning. An agent is just tools in a loop. This is happening to spec-driven dev. I used to have Sean's slide in the beginning of this talk, but it caused a bunch of people to focus on the wrong things. His thing of forget the code, it's like assembly now, and you just focus on the markdown. Very cool idea, but people say spec-driven dev is writing a better prompt, a product requirements document. Sometimes it's using verifiable feedback loops and back pressure. Maybe it is treating the code like assembly, like Sean taught us. But a lot of people are just using a bunch of markdown files while you're coding. Or my favorite, I just stumbled upon this last week. A spec is documentation for an open source library. So it's gone. Spec-driven dev is overhyped, it's useless now. It's semantically diffused. So I want to talk about 4 things that actually work today, the tactical and practical steps that we found working internally and with a bunch of users. We do the research, we figure out how the system works. Remember Memento? This is the best movie on context engineering, as Peter says it. The guy wakes up, he has no memory, he has to read his own tattoos to figure out who he is and what he's up to. If you don't onboard your agents, they will make stuff up. And so if this is your team, this is very simplified for most of you. Most of you have much bigger orgs than this. But let's say you want to do some work over here. One thing you could do is you could put onboarding into every repo. You put a bunch of context. Here's the repo. Here's how it works. This is a compression of all the context in the code base that the agent can see ahead of time before actually getting to work. This is challenging because sometimes it gets too long. As your code base gets really big, you either have to make this longer or you have to leave information out. And so as you are reading through this, you're going to read the context of this big 5 million line mono repo, and you're going to use all the smart zone just to learn how it works. And you're not going to be able to do any good tool calling in the dumb zone. So that's, you can shard this down the stack. You can do, they're just talking about progressive disclosure. You could split this up, right? You could just put a file in the root of every repo, and then at every level, you have additional context based on if you're working here, this is what you need to know. We don't document the files themselves because they're the source of truth. But then as your agent is working, you pull in the root context and then you pull in the subcontext. We won't talk about any specific, you could use CloudMD for this, you can use hooks for this, whatever it is. But then you still have plenty of room in the smart zone because you're only pulling in what you need to know. The problem with this is that it gets out of date. And so every time you ship a new feature, you need to cache and validate and rebuild large parts of this internal documentation. And you could use a lot of AI and make it part of your process to update this. I want to ask a question. Between the actual code, the function names, the comments, and the documentation, does anyone want to guess what is on the y-axis of this chart? Slop. Slop? It's actually the amount of lies you can find in any one part of your code base. So you could make it part of your process to update this, but you probably shouldn't because you probably won't. What we prefer is on-demand compressed context. So if I'm building a feature that relates to SCM providers and Jira and Linear, I would just give it a little bit of steering. I would say, hey, we're going over in this part of the code base over here, and a good research prompt or slash command might take you, or scale even, launch a bunch of sub-agents to take these vertical slices through the code base and then build up a research document that is just a snapshot of the actually true, based on the code itself, parts of the code base that matter. We are compressing truth. Planning is leverage. Planning is about compression of intent. And in planning, we're going to outline the exact steps. So we take our research and our PRD or our bug ticket or whatever it is, we create a plan and we create a plan file. So we're compacting again. And I want to pause and talk about mental alignment. Does anyone know what code review is for? Mental alignment. Mental alignment. It is about making sure things are correct and stuff, but the most important thing is how do we keep everybody on the team on the same page about how the code base is changing and why. And I can read 1,000 lines of Golang every week. Sorry, I can't read 1,000. It's hard. I can do it. I don't want to. And as our team grows, all the code gets reviewed. We don't not read the code. But I, as a technical leader on the team, I can read the plans and I can keep up to date. And that's enough. I can catch some problems early and I maintain understanding of how the system is evolving. Mitchell had this really good post about how he's been putting his AMP threads on his pull requests so that you can see not just, hey, here's a wall of green text in GitHub, but here's the exact steps, here's the prompts, and hey, I ran the build at the end and it passed. This takes the reviewer on a journey in a way that a GitHub PR just can't. And as you're shipping more and more and 2 to 3 times as much code, it's really on you to find ways to keep your team on the same page and show them, here's the steps I did, and here's how we tested it manually. Your goal is leverage, so you want high confidence that the model will actually do the right thing. I can't read this plan and know what actually is going to happen and what code changes are going to happen. So we've, over time, iterated towards our plans include actual code snippets of what's going to change. So your goal is leverage, you want compression of intent, and you want reliable execution. And so I don't know, I have a physics background. We like to draw lines through the center of peaks and curves. As your plans get longer, reliability goes up, readability goes down. There's a sweet spot for you and your team and your code base. You should try to find it. Because when we review the research and the plans, if they're good, then we can get mental alignment. Don't outsource the thinking. I've said this before. This is not magic. There is no perfect prompt. It will not work if you do not read the plan. So we built our entire process around you, the builder, are in back and forth with the agent, reading the plans as they're created. And then if you need peer review, you can send it to someone and say, hey, does this plan look right? Is this the right approach? Is this the right order to look at these things? Jake, again, wrote a really good blog post about the thing that makes research plan implementing valuable is you, the human, in the loop, making sure it's correct. So if you take one thing away from this talk, it should be that a bad line of code is a bad line of code. And a bad part of the plan could be 100 bad lines of code. And a bad line of research, like a misunderstanding of how the system works and where things are, your whole thing's going to be hosed. You're going to be sending the model off in the wrong direction. And so when we're working internally and with users, we're constantly trying to move human effort and focus to the highest leverage parts of this pipeline. Don't outsource the thinking. Watch out for tools that just spew out a bunch of markdown files just to make you feel good. I'm not going to name names here. Sometimes this is overkill. And the way I like to think about this is yeah, you don't always need a full research plan implement. Sometimes you need more. Sometimes you need less. If you're changing the color of a button, just talk to the agent and tell it what to do. If you're doing a simple plan and it's a small feature, if you're doing medium features across multiple repos, then do one research, then build a plan. Basically, the hardest problem you can solve, the ceiling goes up, the more of this context engineering and compaction you're willing to do. And so if you're in the top right corner, you're probably gonna have to do more. A lot of people ask me, how do I know how much context engineering to use? It takes reps. You will get it wrong. You have to get it wrong over and over and over again. Sometimes you'll go too big, sometimes you'll go too small. Pick one tool and get some reps. I recommend against min-maxing across Claude and Codex and all these different tools. So I'm not a big acronym guy. We said spec-driven dev was broken. Research plan and implement I don't think will be the steps. The important part is compaction and context engineering and staying in the smart zone. But people are calling this RPI, and there's nothing I can do about it. So just be wary. There is no perfect prompt. There is no silver bullet. If you really want a hypey word, you can call this harness engineering, which is part of context engineering, and it's how you integrate with the integration points on Codex, Claude, Cursor, whatever, how you customize UX engineering, and it's how you integrate with the integration points on Codex, Claude, Cursor, whatever, how you customize your code base. So what's next? I think the coding agent stuff is actually going to be commoditized. People are going to learn how to do this and get better at it. And the hard part is going to be how do you adapt your team and your workflow in the SDLC to work in a world where 99% of your code is shipped by AI. And if you can't figure this out, you're host. Because there's kind of a rift growing where like staff engineers don't adopt AI because it doesn't make them that much faster, and then junior mid-levels engineers use a lot because it fills in skill gaps, and then it also produces some slop, and then the senior engineers hate it more and more every week because they're cleaning up slop that was shipped by Cursor the week before. This is not AI's fault. This is not the mid-level engineer's fault. Like, if cultural change is really hard, and it needs to come from the top if it's going to work. So if you're a technical leader of your company, pick one tool and get some reps. If you want to help, we are hiring. We're building an agentic IDE to help teams of all sizes speed run the journey to 99% AI-generated code. We'd love to talk to you and work with us. Go hit our website, send us an email, come find me in the hallway. Thank you all so much for your energy.
Our next presenter is the head of developer experience at Cursor, here to tell us about the infrastructure, training, and evaluations used to build Cursor Composer, their first coding model. Please join me in welcoming to the stage Lee Robinson.
Hey everybody, great to be back in New York, and I'm very excited to be here and talk on behalf of all of our engineering and research teams at Cursor about building Cursor Composer, our first agent model. And my colleague Sasha actually gave a version of this talk recently, so I'm excited to give my own take on it. So Cursor Composer is a model designed for real-world software engineering, and it tries to be both fast and smart. So as we've measured it against our own benchmarks, it's better than the best open source models. It's like up against recent frontier models, but kind of slightly below the latest frontier with Sonnet 4.5, GPT 5.1 codecs. But where it really shines is it's about 4 times more efficient at token generation than models at a similar level of intelligence. So we're trying to mesh speed as well as intelligence. So why did we build this model? I mean, obviously Cursor has an IDE. Why are we getting into the model space? Why do we care about this? Well, our research and product teams have been building a model called Tab, which you can use for autocomplete. Maybe some of you use that inside of Cursor. And we wanted to take that same approach for a very low latency model and apply it to coding with agents. But honestly, we weren't really sure if it would work. So we started prototyping some early versions of what this model could look like, started to put it out and get some feedback from users. And we were pretty surprised that this cheetah slug we released for this model, people actually really liked it. They really liked the speed, but the feedback we got was it's not really smart enough yet to be a daily driver for a lot of their coding. So we needed it to be smart and fast, definitely need to be smart. So we really worked on making this internal benchmark that represented our usage in our own repos and how we actually built software. Like if we had a model that was both fast and smart and a checkpoint that our developers would use every single day to build the product and to build all of our software, then we knew that we would be onto something. And for example, one big change here that helped actually push this towards a level where we had a checkpoint where people would use it was being able to call tools in parallel and being able to very effectively use our semantic search tool. And we'll talk about that a little bit more here later. So if you haven't seen it, here's Cursor in Cursor 2.0 in our new view, and we're going to use the Composer 1 model. And you'll notice that it is doing a lot of things very quickly. It's calling a bunch of tools in parallel, like grep, so reading a lot of files. It's making shell commands. It's making file edits. It's writing and managing a list of to-dos. And you can kind of very quickly work through tasks in the foreground here. In this case, I'm investigating an issue in an open source repo. And I don't know about y'all, but this has been a quite different programming experience for me, working with coding agents for a little bit of time now, versus kind of firing off an agent and waiting, let's call it 20 minutes for it to complete, where you can kind of context switch away. This really does help keep you in the flow, and is a kind of a different style of programming, I think. So I want to talk about how we did this in a way that's hopefully accessible for you all. I'm not a machine learning researcher, but I do really enjoy this stuff. What we learned, some of the infrastructure challenges, and then a little bit on where we're going moving forward. So in Cursor, a user kind of submits a query to our backend. The agent reads that query and then decides to make a series of tool calls. And our agent has about 10 tools, give or take, but we're going to focus on 5 here. So reading files, editing files, searching your code base, looking at lints, and then also running terminal or shell commands. And the agent then is able to autonomously decide, do we call these serially or do we run these in parallel? And our goal with reinforcement learning here is to try to mirror the Cursor production environment as close as we possibly can. So this data that we have in training, we want to kind of pretend like we're actually calling real Cursor queries. So to do that, we are running a series of rollouts. For example, in this rollout, we're calling a series of tools like reading files and editing files. And when we run more rollouts, we can start from that same initial starting point, but we might call a completely different set of tools. So in this one, we're also doing code-based search. So we score the output, we decide which one is better, and then we update the parameters of our model based on that change. So conceptually, a pretty simple idea. The challenges come from when you take the simple idea and then you try to scale it up to a very large amount. So there's kind of 3 challenges. The first one is trying to match the training and inference environment, so when the model is actually being used in the product. In this case, with Composer, we're training a large mixture of experts model, and it's being parallelized across thousands of GPUs. And if we don't speed that up, it's going to take forever to train the thing. So we want to make it really fast and match the training and kind of sampling version to be as close as possible. The second challenge is that the rollouts can get pretty complex when you start to look at real-world data here. So models are going to use hundreds of thousands to millions of tokens. They're going to make hundreds of different tool calls. And each of these rollouts could take a pretty different amount of time. One might make a lot of tool calls. One might make not as many. And they'll complete at different times. So we have to figure out how to deal with that challenge. And finally, there's this challenge of consistency. If we want to mimic the production Cursor environment as close as possible, we need to use exactly the same tool format and the tool response. But in training, we have this really bursty amount of compute, basically. We're like doing all of this training all at once, which is different than at production. So it is really an infrastructure challenge. We have these 3 machine learning challenges, and all of the solutions, coincidentally, are actually infrastructure problems. So let's talk through a few of these problems and how we solved it at the infrastructure layer. So our architecture is probably familiar for some of you who have been involved in this space a little bit, but I still think it's really interesting to talk about at kind of a high level. We have 3 different servers. We have an inference server. We have kind of the standard ML stack with PyTorch. We have an inference server, so the rollouts that I just talked about, that's where we use Ray. And then we have environment servers, and these are the ones where we're kind of simulating that cursor environment that I talked about. And all these servers talk to each other. So for example, the inference server can basically send these advantages back to the trainer, which is like nudging it up or down based on the rollout, and then updating the model and getting new parameters. So this one is a bit more on the ML side, but we're trying to train a model that's very, very large and to do it as fast as possible. And one way that our team was able to do this on the research side was to develop a library of custom kernels that allowed for very low precision training. And basically this allows us to just speed up the training process in a big way and also make it much easier to ship to our inference server. So if you're the type of person who loves this, we wrote a blog post going way in depth on all of this that talks about our custom kernels. If you're interested, the TLDR here is we found for the mixture of experts layer was about 3.5 times faster speed up on NVIDIA Blackwell chips. So it made a pretty significant impact on our training runs. So once we update the weights, we need to send them back over to the inference server during this training process. And the inference server is the one that's doing all the rollouts that I talked about, calling the tools and kind of managing what we sent. The challenge here is that they all complete at different times. So kind of a naive version of this, there will be a lot of wasted time. So what we were able to do is do load balancing across the different threads and processes to basically shift the work around and not have a bunch of idle time. So if one rollout, for example, makes a ton of tool calls, maybe it installs some packages, installs some library, we're not just sitting there waiting for all of the other ones to finish. The inference server is spending all this time going back and forth, making the tool calls to the environment, and getting the tool results back. So again, communicating between these servers. And we want that environment to be as close as possible to the Cursor product. One thing that's nice about having both the coding agent, the IDE, as well as what we're doing with the model research and training our own models, is we can kind of co-design these things together. So as we were building out a lot of our RL work for this model, we were also building our Cloud Agents product. This is how you can run a Cursor agent kind of offline. You can run it from your phone or on the web or kick it off from Slack, for example. And to do this, we spin up virtual machines in the cloud. So each one of these VMs loads up the user's code. It allows the agent to kind of like make file changes, run tools, and edit code in a secure sandbox. And coincidentally, this is the perfect infra for RL and our usage training. So we have this like fleet of cloud VMs, and we have an environment that very closely matches the production Cursor environment, and we can then use that for training. This does still have some challenges, though. I kind of talked about how the training workload is very spiky, and it's different than the kind of standard inference when you're running the Cloud Agents product. So we needed to build infrastructure to support all of these VMs and orchestrating between them. So we have many different clusters, hundreds of thousands of VMs here, and you can see behind me one of the internal dashboards we built with Composer, actually, to visualize all of the different VMs in the fleet. So why spend all this time trying to match the environment to be as close as possible to Cursor production? I've kind of mentioned that a few times. We could mock it, we could simulate it out, but one of the really nice benefits is we get to give the model specific tools that we think are very valuable inside of the agent. So one of those is that we've trained our own embedding model that allows you to do semantic search. So when you use Cursor, we go and index your code base, and then it allows the agent to make natural language queries to find files that it might want to edit. And we did some research on this recently. We found that semantic search not only helped basically every single model inside of the Cursor agent harness, but it was particularly helpful with Composer, which kind of makes sense when you think about it. Like we trained Composer in the exact same environment that we're using at inference time, and so the model kind of becomes a power user of this tool, which is really effective. So let's talk about how the release has been going and kind of where we're going next. As we were doing the training process, we kind of knew that RL was working when we were able to continuously improve the model and start to see more and more improvements after more and more rollouts. So we started about kind of the same performance as the best open model, and then as we trained and kind of threw more compute at it, the performance continued to increase, and to a point today where we're close to the frontier in terms of kind of the best coding agents that are available. And personally, I think this is a great sign just for being able to take and scale RL and apply it to these very hard specialized tasks, like in our example, coding, but it could be applied to other domains as well. RL also allowed us to kind of change properties of the model in a way that was very useful for the Cursor product. We wanted the model to be both kind of fast at generating tokens, but also the end-to-end experience of getting a result that's helpful. So for example, instead of reading a file one by one, you can read 10 files in parallel with dual calling. And as you saw in the demo earlier, it makes Composer feel much faster when you have that. And we think this is kind of just the start. There's a lot more we can do in this area to speed up the model. And the second one is the model learned how to behave better as an agent. So in the beginning, the model was kind of making too many edits. Sometimes the edits were made unnecessarily. But as we trained more and more, the model actually got surprisingly better at learning to search and read files more. So it would go and find the right thing before it tried to make edits, overall just being a bit more effective. So we released Composer last month in Cursor 2.0, and so far, it seems like people seem to like it. Has anyone here tried the model by chance? Okay. So find the right thing before it tried to make
make edits, overall just being a bit more effective. So we released Composer last month in Cursor 2.0, and so far, it seems like people seem to like it. Has anyone here tried the model by chance? Okay. That's pretty great. That's more than I expected, so that's great to hear. I think from my perspective, using this model and using coding agents for some time, I kind of describe this problem as like airplane Wi-Fi. So when you're on airplane Wi-Fi, it works, but it's kind of frustrating. You really want to do whatever you're trying to do, but it's a little slow, almost to where sometimes you wish that you just didn't have Wi-Fi at all. And I think for some of us who adopted coding agents very early, it kind of feels like airplane Wi-Fi sometimes, because if it's taking 10 or 20 minutes, you're in this weird, I think Swyx called it semi-async valley of death, where you either want something that's really fast, or you want the most powerful, most intelligent model that can run for a significantly long amount of time, maybe in the background, maybe 30 minutes, hours, days. And I think when you're stuck in the middle, that's very, very painful. So for me, Composer, and I think other people, it's brought a lot of joy back to coding with agents that felt more like when you were writing code by hand, where you're very in the loop, very synchronous. So I'm excited to see more people exploring this space as well. For me, daily, I'm writing a lot of plans with kind of the latest model, like the highest frontier. So GPT 5.1 Codex is really great for plans. And then I'm using Composer to actually take that plan, kind of like what Dex talked about, like take the context engineering work, and then actually go and build the thing with it. So a few reflections from our research and products team on building Composer. The first is that RL can work surprisingly well for training very specific models and giving it this high quality data and a decent amount of compute. At Cursor, we're not trying to build general intelligence. We're not trying to build AGI. We're trying to build very good coding models, and RL has worked surprisingly well for that. The second one is how much AI tools like Cursor, it doesn't have to be Cursor, but like Cursor, really help speed up research and development. Of course, our entire team uses Cursor to help them write code and debug code more efficiently, but that speed up, that increase really compounds across all of our engineering efforts. So we're able to try more ideas, ship product faster, try new research. So it's been really, really helpful there. And the last one that's personally pretty interesting for me is that it was interesting to see how much of the ML work in the training process was actually also an infrastructure problem. They were very correlated, and going back to my time at Vercel, we saw a very similar thing where a lot of the magic moments that you can have in working in frameworks in the JavaScript or Python space, you also need to think a little bit about the infrastructure of where they're actually deployed. So these things are more related than people might think. So those are some of our reflections. Sounds like some of you have tried it out. If this is something that you're interested in and working on, we're hiring pretty much across the board at Cursor right now. We just opened up an office in New York if you're here based in New York, and we'd love to talk to you about building the best coding models in the world. Thank you.
Our next presenter will provide us with an annotated history of evals for AI code. Please join me in welcoming to the stage, engineer at Cursor, Naaman Jain.
Hi everyone. So I'll be talking about some work on evaluations, particularly evaluations across I guess I've done in the last 4 years. So let's get started. So I'll be talking about coding evaluations across varying time horizons. So I've been working on in the code space for about 4 years now. It was right before early Copilot came out, and my first project was actually working on generating single line Panda snippets, and my last project was generating an entire code base. So the field has really progressed very quickly. So I'll be talking about different stages of evaluations we have considered and some learnings across each of the projects and how I see evaluations going forward. So the first work I did was on evaluating coding models in work doing in seconds of time, generating single line snippets, your Copilot code completions. Then I did some work on evaluating on interview style competition programming problems, where models can work up to minutes. Then we worked on some work on repository question answering, which required maybe more multiple minutes, tens of minutes. And finally, pushing the frontier forward, we are thinking about evaluating models on very complex tasks, which can take hours or multiple hours of work, like code optimization and even further. So let's get started. So first work I'll be talking about is Codebench, which is evaluation work on models for competition coding. So here, this is what a problem would look like. This is very standard LeetCode problem, and don't worry, you don't need to solve something like this. So here, as you can see, there's a problem statement. And the nice thing about these interview-style problems is that these problems are very well defined. You have good natural language specifications, some example input-output examples, so you can very reliably evaluate if the models are doing a good job or not. So what is the motivation behind this, and how we improve the frontier here? So the first challenge in evaluating language models these days is data contamination. These models are trained on the entire internet, and on Stack Overflow you'll find very similar programming problems, puzzles. Similarly, you'll find very similar programming problem sources on GitHub or on the internet. So contamination is a big deal. Another very challenging factor which has struggled with the field is insufficient text suites. So you'll see that in this program, the goal was to return a sorted unique common element between the two lists. But even a solution which does not do the sorting and just returns the set actually works because the tests were brittle and were not catching this mistake. So test suites is another very challenging factor, and how do we generate good and diverse tests? And finally, difficulty distributions, which is something which people do not really reliably calibrate. When I first was working in this space, there were two benchmarks available. On one benchmark, the performance was 80% or 90%, and on the other one, it was 1%, and there was nothing in between. And as benchmark users, what you care about is having some signal from the benchmark to basically hill climb, to make progress, to measure progress. And in either of these regimes, if the problems are too easy or too hard, you don't get a lot of signal. So it is very important when you're designing benchmarks to think about the kinds of problems you're taking, and will it provide enough signal for the users of your benchmark. So in LeetCode Bench, we pioneered dynamic evaluations. Particularly, we can periodically update the evaluation sets And this gives you two very nice factors. First is you can combat contamination. So you can evaluate the models on problems that were released after the model was trained. So it has likely not seen the problem, something like that. Then you can also modify the problem difficulty distributions over time. So as we've talked about, models are improving very rapidly. So what was difficult for the model 6 months back might not be now. So you can, if you're updating your evaluation sets constantly, you can actually keep the difficulty distributions calibrated so you still get more signal out of your benchmarks. So how we did that here, we had an automated approach for curation of these problems. And similarly, we could automatically construct these test cases in an automated manner. And this allows a very nice thing. Since we are collecting problems over time, we have time as a control knob. So we have these problem release months on lead code. And if you evaluate the model performances, the pass at the rate 1 metric, on problems released over different months, you will see that after these model release dates, you would see stark drop in model performance. So after DeepSeek was released in September 2023, the performance starkly drops from maybe 50% average to over 20% or 15% average. So based on these sliding windows, you can evaluate performance, measure contamination, and even combat contamination. We have the running leaderboard, which is very well maintained, and on this leaderboard you can actually view performances by scrolling this horizontal time bar, and you'll see that as you're scrolling, the contaminated models, which are the red bars, actually go down, which does highlight that model performance does change on these newer kind of problems. Finally, for test generation, we maintain these test generators. So if you worked on fuzzing, you would have input generators where you generate diverse inputs. And each of the problems are supported by 30s or 50 inputs. So you can reliably find mistakes and bugs in incorrect code. And these are all automatically generated using an LLM-driven approaches. And these problems have been continuously being released and updated. So we have released 6 different versions of Live Code Bench. And these, one of the nice things, or one of the worrying things for me at the start was that if you're constantly updating the eval sets, will people be able to keep track of them? Will people be using them? Or will they just restrict to a single version? It turned out that these newer eval sets were constantly adopted by different foundation model labs. And since we updated the problem difficulty over time, the evaluation sets continue to provide strong signal to compare different models. So this was Live Code Bench. Let's talk about something which is more on coding agents, more real-world programs. And this is work on software optimization. So this is a problem I'm very excited about, and I'll talk about a few factors why you should maybe be excited about this. So here we are trying to measure model capabilities in generating high-performance software. And I feel that this problem domain mixes two factors, like the algorithmic coding field I talked about, which is Live Code Bench setting, but also global software editing, Swyx and other general software engineering benchmarks. In high-performance software, you will have to do algorithmic work, you have to do deep analysis and generate software with right runtime. So one of the key principles when we are trying to build this benchmark was ensuring construct validity, because when you see a lot of benchmarks today, we get very high benchmark scores, but a lot of the times they don't really translate to real-world performance gains. So construct validity refers to how close a measurement reflects the underlying concept it's meant to measure. So here we are measuring code optimization, and we want something which is reliably evaluates real-world takes. So this usually requires two aspects. First is the task distribution. Your task should be natural and sourced from the real world, and then you should be able to reliably grade them. So let me talk about what steps we take to make this happen and how we construct this benchmark. So let's say we take a code base like Llama CBP. We crawl over all the commits of the code base, and we find the commits which are doing something related to performance optimization. So here there was this commit which is optimizing the quantized performance of certain kinds of models. For all of these performance optimizing commits, we would generate performance test cases, and these performance test cases would look like some workloads. And once we have these workloads, we have a very nice and precise way to specify the problem statement that given this workload of, let's say, running Quen 7B model, we give this problem to Swyx and ask the model to optimize the code, Llama CBP repository, so this code runs faster. So as you can imagine, this task is fairly challenging. You need to understand low-level implementation details and how quantized models behave, how we can improve the runtime. And so models can generate a patch, and the evaluation is done on whether the patch is correct. So does it pass the equivalence check with the human patch? And is there a valid optimization over the reference human patch? That is whether you can generate a better runtime than what a human could do. So this is a very challenging task. We have 100+ optimization tasks sourced in this manner. And this is fairly important in high performance settings. So think about data science, ML visualization scenarios. Our benchmark comprises of various low-level code like C, C++, Rust. And the very nice thing is these are precise problem statements. You can easily specify to the model what is the goal in the form of a performance test, which the model has access to, and it can continuously iterate over it for a long time. So here we can scale the test time compute and pick the best solution based on the test cases that we have. And this can happen synchronously or asynchronously. So we generate these performance test cases, and that worked reasonably well. But we found that there were cases of reward hacking here. So what do I mean by reward hacking? Frontier models would write non-idiomatic code to actively exploit the evaluation infrastructure or overfit the test distributions. So one funny example we saw was models would add LRU cache to arbitrary pandas methods when we were trying to optimize pandas, and the official solution should have required changing something in the internals. So we tried to pass this by changing our evaluation infrastructure so it's more robust to this kind of hacking approaches. But then we saw something even more drastic to this kind of hacking approaches. But then we saw something like even more drastic. Models would sometimes completely hijack the infra, where they would add a like site.customize.py file, which runs at the start of Python runtime, and it would basically change the NumPy library, like which was installed in the codebase to something it crawled from source. And there is like I think you can do some ways to like take some measures to make your evaluation infra which is robust to these kind of like adversarial like attacks. But here like there could be myriad ways in which models can hack these kind of scenarios. And here we propose like hack detector, where which is a detection system that leverages GPT-5's like code analysis capabilities and test and compute to like basically identify these kind of hacking behaviors at runtime. So you don't have to imagine all the possible failure scenarios at the start. So what it would take is like a model patch, the expert patch and test cases, and we'll ask GPT-5 to give like verdicts on like whether it's reward hacking with some kind of explanation. We'll do this a few times and take the consensus. And based on this consensus, we'll determine if this is doing some like non-idiomatic coding patterns or not. And we did some failure analysis based on this. So now you can detect mistakes using test cases, whether the code is correct or not, whether it is optimizing or not. But you can also detect reward hacks using this like LLM as a judge factor. And what you see is kind of surprising. Like models make a lot of like correctness mistakes that you can catch by tests. But even if the code passes the test cases, like O3 attempted reward hacking patterns in like 30% of the problems it tried. And this fraction is like going down for the newer models to some degree, but it is still existing. And as we go to more and more real world tasks, this is going to get more challenging, and we need to figure like ways to combat these kind of reward hacking patterns by using LLM judge and other ways to make this evaluation infra more reliable. So next I'll talk about like syzygy, some of our new work on like pushing the boundary of code evals even further and taking a look at more challenging tasks. So here we were thinking about like can like these language models translate like entire code base. Specifically given a specification as a C program, can you generate a safe Rust implementation for the same? And we took a fairly complex code base. So Zofly is a like highly efficient compression library from Google. Like it has about like 4,000 lines of code, hundreds of functions, and complex data structures. And we want like very precise and correct code. So we generated like 1 million compression inputs, and your test case was to generate a Rust implementation that maintains correctness over those million test cases. And when I did this work back in last year, it took us 12 hours to actually do this translation. Now perhaps with better models, this can be done in 2 hours. But still, I think this is pushing the frontier of like what the models can do currently. So what is one of the key findings when we are trying to make progress in something like this? Like end-to-end correctness is important, but it only gives you like one bit of feedback. But for these very long horizon tasks, one thing which will become more important going forward is like having some measures of intermediate correctness. So like for our case, we could measure like fraction of code translated, fraction of code refactored, and based on these kind of settings, you can understand like if you're making progress or not and how you can scale systems better. So like as we're closing, I'll talk about quickly talk about some of the work I did on like in the wild evals. So this work was done in collaboration with LM Arena folks, and like I'll talk about 2 settings here. First is Copilot Arena. So this is like evaluating in ID code completion assistance. So what we would do here is we'll have an ID plugin where similar to GitHub Copilot setting, we'll generate a completion for you, but instead of just a single completion, you'll have 2 completions appearing like top and down, and you can pick either one of them via shortcuts like tab or shift tab. And based on the like acceptance rates, we can pairwise compare what the code completion assistants are doing. We also did some work on repo chat where to evaluate like code question answering capabilities of models, we built a system where you can provide a GitHub URL and you can ask a natural language query about the code base. It could be something about explain the code base to as complex as let's try to solve this issue. Let's give me a model patch that could solve this issue. And we integrated a very basic and simple like Swyx agent system that fetches the code base, resolves user queries in like multi-turn code assistant conversations. So one thing that stood out to me in these kind of things is like how human-centric experiment design needs to be. So like for Copilot Arena in particular, we realized that like latency is a big concern for acceptance rates. So if you look at the acceptance like latency below and the acceptance rates, like if it is like anything more than 1 second, like the acceptance rates drop very starkly. So people care a lot about latency. So we had to design an experiment so that it's robust to these kind of like latency differences between models, balanced latency across different models. So like if you're doing like anything in the wild, having this human-centric component, understanding human behaviors is very important to do anything meaningful. So at the end, I think just to recap, like I think I talked about a bunch of works. Like what are some big takeaways? So I think dynamically updating evaluation sets to like prevent contamination, like modify the problem distributions, like in terms of difficulty, in terms of distribution of tasks we care about. As we like improve, as the language model capabilities will improve over time, the types of tasks we'll start to do with model change. You can even think of this like we were doing like code completion where we were generating like few tokens, few lines, and now we are generating like tens of lines, hundreds of lines. And to some degree, this will continuously change, and we have to update our evaluation sets so that it reflects the real world usage and kind of things people need. The second very important thing is like ensuring reliable grading in this domain. And like tests are very good for ensuring correctness and provide a lot of reliable feedback. But once we go to real world settings, like models can start doing like a lot of non-idiomatic coding patterns. They would add try catches everywhere to just prevent any kind of bug from occurring. So having these kind of LLM judges to detect non-idiomatic coding patterns, code quality. And just any like arbitrary hacks will be very important. And finally, like as I talked about in the last work, like intermediate grading signals so that you can measure like incremental progress is like another key factor here. So I think that's the end of my talk. Thank you.
Ladies and gentlemen, please welcome back to the stage, Jed Borovic.
All right, give it up for Naman and all our speakers. All right, hold on. So this is a point you've all been waiting for. We can take a break. It is coffee time, it is snack time. There is going to be a talk downstairs from WorkOS called Enterprise Grade MCP. And it's a topic on a lot of y'all's minds. Tobin South, head of AI and MCP at WorkOS is going to be down there. So check that out. That's at 10:40. And we'll be back here at 11 a.m. Reminder, the full schedule is online. Thank you. See you soon.
Hey everyone, and welcome. My name is Chris, and I work on the Google Workspace team. Thank you for joining our webinar today, where we're going to talk about Google AI Ultra for Business. In this webinar, we're going to explore how you can provide your creatives, developers, researchers, and other AI power users with some of our most powerful AI tools. Earlier this year, Google Workspace announced that premium AI from Google is included in Workspace Business and Enterprise plans at no additional cost. This includes Notebook LM, the Gemini app, and Gemini integrated within Workspace apps that you use every day, like Gmail, Drive, Docs, Meet, and more. So what exactly is Google AI Ultra for Business? It's an add-on for Google Workspace specifically designed to provide AI power users within your organization, so those engaged with specialized work, with the highest access to our features and models, and next-generation creative tools. This is ideal for creative teams, UX designers, software developers, researchers, and other power users within your organization. Importantly, it's not a separate standalone ecosystem. So it's a part of Google Workspace, which is a trusted, AI-powered, and integrated platform for work and collaboration that can be centrally managed by your Workspace admin. When you give an AI Ultra license to a user, they get access to some powerful tools. So let's talk about that. This includes the Gemini app with the highest access to some of our most advanced models, like Gemini 2.5 Pro and DeepThink, and also VO3, among others. These are used for tackling complex problems, reasoning, coding, research, and creative tasks. You also get the highest access levels to Flow, which is an AI filmmaking tool. You also get the highest access to Whisk, which is used for rapid ideation on the visual side, as well as video creation from images. And soon, you'll also get the highest access to Notebook LM, which acts as an AI research and thinking partner, which you can use that's based on your sources and documents. We also include access to Project Mariner, which is a research prototype exploring how AI agents can help automate certain workflows from end to end. So let's talk about and let's show you what these tools look like in action. We'll go through a couple of examples of how you might use these tools in a typical workflow or during your workday. So let's dive in. With Google AI Ultra for Business, you get access to the highest limits and DeepThink in the Gemini app. DeepThink doesn't follow a single path to an answer. Instead, it uses techniques called parallel thinking and reinforcement learning, which allow it to explore multiple ideas and solutions simultaneously, refining and combining them before arriving at a final optimal response. This makes DeepThink particularly good for tasks that require a high degree of reasoning, creativity, and strategic planning. So let's see what it looks like in action. Imagine you're a developer for an online retailer who needs to create a personalized recommendation engine that considers a customer's real-time browsing behavior, past purchases, and seasonal trends, giving suggestions that are both relevant and likely to convert. You open the Gemini app, select DeepThink from the menu, and type, "Help me design, architect, and create the core code for a next-generation personalized product recommendation engine that maximizes customer conversion and order value." The engine must be real-time, scalable, and include real-time browsing history, past purchases, and product metadata. So obviously that's a pretty complex problem. The Gemini app uses DeepThink to provide you with a ready-to-use code block, explanations, and considerations. Next, imagine having a tool that instantly understands and synthesizes information from all of your documents, presentations, websites, and even videos. Notebook LM does just that. It uses your sources to answer questions, generate summaries, and create new content, all with verifiable citations. It's like having a dedicated expert on your team, always ready to provide insights based on your trusted information. Now, here's the core idea. You start by selecting the documents, web pages, or videos that are relevant to your task, and then Notebook LM analyzes those sources and only uses that information to generate responses. It's a pretty powerful tool. As an insights researcher, you're tasked with writing a comprehensive report on new market trends in the fashion retail sector. You have a variety of sources, which could include research papers, articles, and meeting notes, and you want to get started and start to synthesize this information. So you upload all of these into NotebookLM, and it instantly synthesizes the information, creating a shareable notebook with key talking points and the ability to chat with AI and learn more about the sources. You can also create different things in the studio to help you synthesize and make sense of the information. With one click, you can create FAQs, a video overview, mind maps, and a podcast-style audio overview for you and the team to listen to on demand. I'm personally more of a visual learner myself, so creating mind maps and video overviews has been really helpful to me to make the most of my information and start to break it down and understand it better. As a video creative lead, you need high-quality video for a new marketing campaign, but you have a tight deadline and budget, something we all have to deal with every once in a while. With Flow, you can use natural language to describe what you'd like to see in a video. Flow will help you create an 8-second clip or longer narrative using Scene Builder. You can even use an image as a reference to ensure characters and objects in the video match the rest of your creative vision, which brings a lot of consistency, which people seem to get a lot of value out of. To start creating, you can begin with a new project. Inside, you can see all of the different controls and the ability to create video from various things such as ingredients, frames, and text. There, you can use your own branded assets to help generate video as well. To get started, you just need a simple description like, create a black and white cinematic scene of a bustling city at night with an elegant classic car driving through it. Flow uses VO to generate a consistent, story-driven video clip in minutes. Afterwards, you can even save that video as a frame to reference and even build upon this to build out a longer video and story. Let's say you're a designer brainstorming ideas for a new brand campaign. You need a visual that captures a specific feeling, but you don't have a clear image yet. This is where Whisk can be really helpful. You go to Whisk and type in a prompt like, generate a couple of high-quality images of a serene forest with glowing bioluminescent plants with a river. It will quickly generate different options for you. Once you have a still image you like, you can use Whisk Animate to turn it into an 8-second video. And in this case, we can look to add motion to it. You can also add images as references to quickly generate many different styles and ideas, helping you visualize how a concept could come to life in a digital ad. Whisk allows you to combine images to generate interesting variations too, which is something I really like to play around with, whether it's my own assets that I upload or even some that the tool will generate to play around with. As you can see, after a few minutes, you have an animated visual asset that you can use. Let's look at some of the different teams that can immediately benefit from Google AI Ultra for Business. For marketing creatives, the biggest advantage is the ability to accelerate video creation. Instead of weeks, they can go from brief to a final cut in a fraction of the time. They can use Flow to generate high-quality cinematic clips for a campaign and even stitch them together or have a consistent narrative. And with Whisk, they can explore different visual directions for a new product launch or turn a static photo into a short video for social media. The Gemini app itself can also produce professional-looking 1080p videos using VO for when you need something short and sweet. Designers can also really speed up their ideation process. Whisk is really built for this, so they can use a simple text prompt or even another image as a prompt to quickly generate a variety of visual concepts. It helps them explore different styles and compositions very efficiently. Flow is also a great tool for designers to create animated storyboards or pitch a concept with a short, consistent narrative, ensuring the elements look like the same one from one scene to the next. For your software engineers, AI Ultra can help them tackle their most ambitious projects. The Gemini app becomes a powerful coding assistant. It can generate entire blocks of code, create unit tests, and take over the repetitive tasks that slow them down. This frees them up to focus on more complex, problem-solving aspects of their work. They also get access to Deep Think, which is an enhanced reasoning mode designed specifically for difficult coding challenges. Additionally, UX designers and researchers deal with a huge amount of qualitative data. AI Ultra can dramatically speed up their analysis. With NotebookLM, they can upload all of their research, like internal interview transcripts, survey results, and feedback forms, and it will act as their research assistant. It can summarize findings and identify key themes instantly. The Gemini app also includes a feature called Deep Research, which is one of my favorite features personally, which can take a simple prompt and turn it into a full research report, saving hours of manual work and a lot of time. With Google AI Ultra for Business, everything is designed to be simple and secure. The core services like the Gemini app, Notebook LM, and Gemini in Workspace are covered by your existing enterprise-grade data protections. However, one thing to keep in mind is that several of these tools, including Whisk, Flow, and Project Mariner, are not covered by the Workspace Terms of Service and have their own privacy policies. So we definitely encourage you to read these terms for more details and keep that in mind. You can manage licenses right from the admin console. Getting started is straightforward. Google AI Ultra for Business is available as an add-on for most Google Workspace plans, including Business, Enterprise, and Education editions. If you're a customer, you can purchase licenses directly through the Get More Services section of your admin console and assign them to users who need them the most. Our sales teams will be happy to guide you through your options and find the right solution for your organization. If you're new to Workspace, you may elect simply to get a Workspace plan that will provide your teams with premium AI like Notebook LM, the Gemini app, and more. Then add Google AI Ultra for Business as an add-on for users looking to push what's possible for AI. Regardless, scan the QR code on the screen or reach out on workspace.google.com/contact. We would love to chat with you to help you learn more about how you can leverage Google Workspace and all of our AI capabilities and features for your business. And that's everything we have for today. Thank you all so much for joining us, and have a great day.
Modern large language model. Quinn, Claude, any of them really.
Oh yeah, everyone has at this point.
You know that feeling?
Yeah.
You type your prompt, you hit enter, and then there's that little pause. It can feel kind of agonizing.
Like it's processing the entire history of the universe.
Right. But then the first word pops out and the rest just streams onto your screen super quick and steady.
And that experience, that initial choke point followed by the rapid fire generation, that really tells the entire story of high performance LLM serving.
So what's really going on under the hood?
Well, fundamentally, every LLM is just a very, very fancy and costly next token predictor. To get even one token, you have to pass your input through billions of parameters. It involves these colossal matrix multiplications.
And that single operation is the core technical challenge, isn't it? I mean, for one user, okay, it's expensive. But if you're a massive service trying to maximize throughput.
Throughput, right. The number of useful tokens you're generating per second across all users.
You're going to hit some immediate, just brutal resource bottlenecks.
Exactly. So our mission for this deep dive is to get into the optimization that really cracked this challenge, continuous batching.
Okay.
And we're going to build this concept from the ground up. We'll start with the single most expensive operation inside that transformer architecture.
All right, let's unpack this. And I guess that journey have to start with the attention mechanism. That's the heart of it, right? It's how these models understand context.
It is. So when the model gets text, it tokenizes it. And for a lot of operations like layer normalization, the tokens are processed totally independently. They don't know about each other.
But they have to interact. I mean, the word blue is useless if it doesn't know it's connected to the word sky.
Precisely. And the attention layers are the only place where different tokens actually interact. They communicate with each other.
How does that work?
It's achieved by projecting the input into 3 different states. You've got query, key, and value, Q, K, and V.
All right, we hear those terms constantly.
Yeah.
Q, K, and V.
Yeah.
But what do they, conceptually, what do they represent?
Think of it like a little search engine inside the sentence. The query, the Q, is what the current token is searching for. It's the context it needs to understand itself.
Okay.
And the key state, the K, represents what all the other tokens offer. They're like contextual tags or IDs.
So Q is looking, K is offering. What about V, the value?
The value is the actual information payload that the token carries. So when we calculate the attention scores, we're multiplying the query by the transpose of the key. That's the Q-K transpose operation.
And that's a huge matrix multiplication.
A huge one. And it's measuring the similarity between what one token is looking for, the Q, and what every other token is offering, the K.
And I think this is where the computational bill just gets staggering.
It absolutely does, because you're comparing every single token against every other token. The cost isn't linear.
Yeah.
It's quadratic in sequence length.
So we describe that as what, O of n squared complexity?
Exactly, ON2. And what that means for you is if you double your prompt length, say from 100 to 200 tokens, the computation time doesn't just double, it quadruples.
Wow.
And that's why that initial processing step, that first pause, is so slow.
And of course, the model can't cheat. It can't look at words that come after the one it's working on. So there's a filter for that.
That filter is the attention mask, specifically a...
Still have a few people coming joining just now. Thank you very much. So we have a lot of questions in the Gather tool that we use, which we can continue to respond to. Maybe if people on the call don't have a question, but if you've asked the question in that tool, we will come to it. If anybody else hasn't used the tool and would like to raise their hands now, maybe we can hear your question directly. So just once again, if you use the hand raising signal, which is in the toolbar at the bottom of the page, if you haven't already asked a question in the Google Gather tool. Okay, so people are either asking questions in the chat on the side. Gentlemen, I see you've asked a number of the same questions and you've pinned those questions here as well. Please give us, we want everybody to have the opportunity to ask questions here today, if that's okay. So I'll come to you in a moment so I can see you have a number 7 already in the tool, so please bear with us. In terms of today's session, this was around Ultra AI. We're very keen to try to keep the questions contained to that product. And then potentially later we can get to more general questions if we have time. Sound good, Christian? Okay. So, Viviana, would you like to come off mute and ask your question?
Hello, morning.
Hello.
Yes, I'm trying Google Enterprise to understand the potential of the tool. And I'm really interested on connecting different type of agents because I know that in the next future, I don't know when, will be present an orchestrator that can communicate with different agents. And you can connect these agents with API to your internal data sources, different data sources. Is something that is available soon? Is something that I'm missing? Is already available? Thank you.
Sure, I can take this one. The answer, luckily, is yes. We do see agent and the orchestration of them to be a key business driver for a lot of customers, hence why we recently launched into alpha program the Workflows tool for Google Workspace. And that's exactly what it does. It gives you an orchestration layer to use separate agents. So those could be the Gemini agent itself, specific gems you create, or again, it's going to be first, I think, more of an API and a Google Marketplace sort of approach. Third parties and additional models or agents, let's say outside of Gemini or within the Gemini scope, could be leveraged in this sort of way. And so the way you interact with them, I think, depends on which tools you're using. But I think Flows seems to be the most useful one because it can, again, automate and call agents proactively for you rather than interacting with them directly in that tool interface. Because I think from a workspace perspective, we're focused on the Gemini tools, but the integrations are available via the add-ons framework or something like Flows.
Thank you. I have another question, last question, sorry. Do you can create this API for us if we don't have sources to create them or not?
Yeah, so there's a couple of ways you can go about it. One, we actually have very good documentation that's starting to get rolled out right now to help you do this yourself and do it, let's say, not in such an advanced way in the past. It's more of a, let's say, a moving from a no-code agent generation to a low-code integration sort of approach, if you will. And then the second method will be, I would say, one, you can leverage agents, obviously the gems that are created by Google and pushed out there in addition to the custom ones you make, but also, for example, this custom steps that I'm talking about, connecting to third parties and other models and agents. The Google Workspace Marketplace is where a lot of these tools are being developed right now by partners, which then you can, let's say, just go and use or purchase based on those needs. But let's say the creation and customization of those agents, it'll be a different approach. It'll be, some will be by default. For example, in Flows, we already have a Salesforce, Asana, and a couple other Jira and Confluence integrations that are already there. Other integrations will likely come in the future, but much of it will be driven by the partner network themselves and building integrations versus, let's say, Google introducing other models into the workspace context. But it's an area we'd like to really explore because, for example, when you go to the Gemini interface, you're actually able to select the model directly from there. So in the future, we may have more options, but at this point, I don't know about third-party ones being integrated directly in the Gemini one, but via integrations, APIs, and partner tools, you can achieve that.
Thank you, Christian. Thank you for your question, Viviana. That
Thank
was
you.
very insightful. Maybe come to Jonathan Zachary. Would you like to come off mute and ask your question, please, Jonathan?
Yes, thank you. I wanted to understand about the difference in the quality of the engine if I use the Google Workspace that I currently have and the Ultra. In terms of, I saw like you said, like that we get the most advanced engines, but actually I prefer working with not with beta, but with better product, because sometimes I spend more time on the beta, and therefore what will be the difference? And in terms of tokens as well, do I get more tokens for videos and other things if I go to with Ultra, or is it the same number of tokens? For example, when I use now a video creation, I'm limited to 10 videos per day. Is that different in Ultra as well?
So yes, there are raised limits and let's say quotas that you could have, for example, more tokens per day, more images, more videos. I'm actually looking for the article. So for example, and I want to compare the two because one, there's what comes included with the workspace package. Oh, sorry, Tony, go ahead.
No, I shared a link in the chat.
Oh, thank you.
I think it's slide, which will help you, which will give the breakdown of the tokens and the availability of daily usage. That may cover quite a lot of questions actually, but yeah, that's probably where you would need to go.
Mm-hmm.
If you'd like to click on the link now, it's maybe let me pin this actually. Okay. Are you able to see the question, Jonathan? And sorry, the side panel with the questions?
Yes, I see core services with business. I see now the differences. Just okay, up to 100 and up to 500 prompts. And in terms of the quality of Gemini, is there any difference in that terms?
That's going to be based on the model and the context window. So I would say that in general, just because you get more, you would get more. But let's say if you're still using 3.0, whether on regardless what edition, the quality should be similar in that regard.
Okay, last thing I wanted to say that it's amazing. Your tools are amazing. Thank you very much for that.
Pleasure. A lot of hard work from our engineering team, that's for sure.
Sure.
Okay. Thank you for the question, Jonathan. I hope the link that we shared there has covered the answer in addition to Christian's comments also. Chintamani has asked a number of questions in Google Gather. So Chintamani, would you like to come off mute and ask your question, please? The one that you've posted in the chat.
Yeah, today my question is how does Gemini API support multimodal inputs and how would you use this capability in your project?
Trying to think of like the. So can you give me an example of how you would use it to put the multimodal inputs? Like, give me an example or use case. Because, like, for example, obviously you can upload multiple different types of text,
Yeah,
video.
present we have
Yeah.
to use the trending project like Gemini 3 Pro, where the present is that trending right now. So how to build an app and analyze the product like any photos or text descriptions and summary? How can the answering this all the project capability? How can we how can we Gemini API supporting multimodal type and how can we multiple types that how can we give it up any text message, images, video, audio in any it can be used in any given in a project for a single prompt. How
Yeah.
the Gemini API supports the multimodal inputs? That's my question.
Yeah. Yeah, so I think there's a few different approaches to go about it. Like, obviously, you can probably notice via the interface for the Gemini application, the upload, whether it's code, content from your desktop, stuff stored in Google Drive, and you can combine all various sorts within that to, again, run that query. But again, that's going to be somewhat limited because it's what can be input directly in the Gemini tool. If you're talking about massive, massive scale, this is where the Vertex AI platform using Gemini would probably be the direction you'd be more going towards for, let's say, true big multimodal sort of analysis. Like, actually, I think there's even a right here, for example, let me ping it in the chat space here, but there's like a good sender from our Google Cloud services that talks a little bit around how you can design multimodal prompts within the Gemini scope to do a lot of these activities. Because ultimately, it depends on what data does this solution have access to. So in the Gemini application, usually that means, okay, workspace data, some whatever you upload into it and give it directly within your prompt. If I'm doing it, let's say, within the scope of workspace, it's using my Drive data, calendar, Gmail, everything's kind of integrated in that sort of way, versus, let's say, Gemini Enterprise, where Google is providing you with the front end and you can connect it to your third-party or enterprise sources. And then finally, let's say more scale where your data just sits there. You don't need interface. You just want to write prompts and have that work within your application or tool. That's where Vertex AI and the platform comes into play. So it just depends on the approach you take.
Is there any case in any e-commerce product analysis tool it can be used for the project and multimodal inputs have to given for this?
Not to my knowledge. Yeah, sorry, not off the top of my head, I wouldn't know.
Okay. Thank you, sir.
Oh, no worries.
Thank you
No,
for your
it's not.
question, Mr.
Yeah.
Marnie. Okay, great to, yeah, I think Holger's raised a question again in response. Upgrading Google Workspace Enterprise is mandatory.
Yeah, so this is a good, but actually, thank you for the question, Holger. Very, very relevant because that's oftentimes when I'm engaging with my customers. So my scope is normally Google Workspace. However, since I interact and work with the rest of the cloud ecosystem, other sort of parts of it, customers always say, okay, when is the time when I realize Gemini is not enough as a workspace customer? Enterprise becomes, let's say, more important. And ultimately, I would say it's about data sources that you would like to incorporate into, let's say, that single prompt. Like how I can tell you how I'm using it today is when I do a Gemini Enterprise versus, let's say, a Gemini search, usually it's because I need context. And that means something relevant to my enterprise data, because I think the way I kind of approach it is, Gemini, the standalone tool, Enterprise Ultra, whatever it is very much about individual productivity versus the Gemini Enterprise platform, which is meant like, hey, I need agents that can read data from CRM solutions. I don't want to have to connect that to my workspace environment. I prefer it just goes to the agent alone and then kind of does that thing. So I think it's like, okay, it's a replatforming versus a, let's say, modernization. Because while I would love every one of my customers to move to Google Workspace, I realize that's a big project. And so sometimes starting with Gemini Enterprise means data can stay where it is, and I can leverage the best parts of Gemini with my enterprise sources without having to, let's say, move it around to mate that, where then I can focus on other modernization efforts or priorities in my organization.
Yes.
So that's a very important answer to me, actually. I haven't been aware of this separation. I was always planning for upgrading, but I was not sure for which reason. I know that you can install services on Google Cloud Platform and use them as extra capacity, let's say it. But I was hesitating, and I have seen customers working with this option, but they have been enterprise customers, and now I fully understand the difference. Thank you very much.
No, it's a very important differentiator, because I think again, focusing on that individual productivity versus the IT kind of driven experience from an agentic approach. It's kind of like, I would say, a maturity thing. Or like me, for example, I'm a power user of agentic AI. So it makes sense for me to have AI Ultra and Pro. I'm using it in a far more advanced fashion. The Gemini Enterprise, which is more based like saying, hey, it's about that overall enterprise productivity and integration on top of that. At least that's, I think, the biggest value I'm seeing when customers are evaluating, deciding which path to go when. It's more about prioritization. Are you trying to get some power users that are using AI very heavily up and running fast? Okay, Ultra is probably the right direction for them, versus, hey, I need to have an overall agentic platform that integrates with all my enterprise sources and gives users, because if the user spends most of my time in workspace like me, I use the agentic experience there mostly. I still use Gemini Enterprise, but for other cases, someone who interacts with SAP or third-party systems, hey, Gemini Enterprise is great because they don't have to switch context so much.
I'm in the process of moving into this direction. I'm not fully there. I'm just careful because of German law.
Yeah, true.
And it is difficult to write prompts that mask private data, and my customers handle very sensitive data. So it's slowing us down, but I appreciate that. Okay, it's not that I'm against it. It's just something to be aware of. Yes, and the administrative admin level. Maybe Tony has a link for me, because I was searching for a quick start to increase my understanding of the administrative steps to outflank this use of agentic AI.
Yeah, and some advice around that too, because obviously, being based in Germany, a German name, not German, but I work with a lot of clients that are also doing this evaluation. We've got DORA compliance coming up in the new year. They've got to think around privacy controls, how they explain it to the regulators when AI accesses. And that's why, actually, as part of these transformation projects for AI, it relies on having, I think, as you mentioned, good labeled data, so classified, to make sure that AI understands the boundaries of what it's able to do. We do this a lot in Google as an example, where someone launched this fantastic tool that helps you basically analyze all your work patterns and things and do that. But privacy stepped in, said, okay, we need to cut a lot of that data out there. While it is useful, we need to make sure the law supports that.
I have not been aware that this is interlinked or interlocked. Labeling is an art. It's not a technique.
It is.
But I don't want to eat up all the time. Thank you very much.
Thank you, Holger.
Appreciate your question, Holger. Thank you very much. We have a really interesting one that's come in the chat, Christian, from Kim. Kim, would you like to come off mute and ask your question?
That's a good one.
Hello?
Add anything to that?
Is someone talking to me? Tony, is that me?
Yes,
Did you call me? Oh, hi.
Hi.
All right then. Hi, sorry. So in the presentation, it was identified that not all of the partners working for this program have a combined privacy policy. So I just wondered if it's possible that you might have an easy read version for the privacy policies that apply to the external partners.
Yeah. So, and when you mean privacy for the external partners, I mean, like what, like in general, what you would be educating customers on, or more like your privacy around data? Sorry, maybe I didn't understand the question fully.
I think both would be relevant, because I'm going to be working in the retail space. Yeah.
Got it. Okay. So there's a couple things, like, for example, our product team recently made, and I'll post this in the chat here, a really fantastic privacy hub for Gemini, and I use this as my primary sort of source. But if you're talking around the Gemini Ultra or the Gemini Integrate with Workspace resources, Partner Advantage also will have some privacy assets that you could do for customer presentations or for your own personal education. But what I do, as you can imagine, is I take all of this stuff and I put it in a notebook LM, and then I use that to build, I think, questionnaires, sort of summaries and things like that, that then I can deliver to customers. And the new actually slide generation and audio overview also will help you, I think, with educating some customers on that.
Thank you. That's really helpful.
My pleasure.
Thank you, Christian. Thank you for the question, Kim. Are you satisfied that's giving you the answers? Because I think we had a few questions. Viviana.
Yeah, actually, we have mentioned in the notebook LM, and I saw that is now available the function of slide deck. But I was wondering why is not possible export the final result as in Gemini Canvas. It's more difficult, you know.
I get you. Yeah, I wish that was there too. Because I've been changing a lot of my workflows over last year because, now that you can generate slides within Google Slides, you can generate it from a notebook, you can generate them in Canvas. Figuring out which tool is right for you, depending on your use case, is a fairly good challenge. Or even the infographic one, which I often will copy and paste into my slide decks as well. But from what I'm finding is that usually I use either Notebook LM or Gemini if I'm working on something, let's say, completely abstract. I'm not following, let's say, very specific corporate guidelines around style or anything like that. If I just want to create something on a topic, I tend to use Notebook LM or Gemini. I would say if it's a more established project, Notebook LM tends to be the better option because I'm keeping all my assets. Essentially, I have more of an idea about what I'm researching versus I'm just trying to build something inspirational. Gemini and Canvas can be a pretty good source for that. And then I generate basically my main context in one of these solutions. And then I do all the editing and additional AI capabilities within the Google Slides interface. It's not perfect. I wish there's still some things I think we're working on, but good news is I've seen some internal features and functions that will make this a lot easier and allow you to do this better at scale, because porting 15 slides, then having to edit each of them one by one still does add quite a bit of work when you might already have like a copy ready to go and speed up your workflow. So it's an area of investment that I think is getting better. We're just not quite there yet.
Yeah, thank you so much. And there are my colleagues that are asking me, is it possible also integrate with our internal template? Not yet,
We're working on it. We're working on it. There's an early version I'm testing right now, which is pretty good. I have to say, it does follow style guides pretty goodly. But as you can see, like we're also trying this nano banana approach within the slide interface when you regenerate like a slide basically as an image, which is good start. But I think it's still not quite there for people that are more power users than slides. But good news is we're working on it and there's some good things coming.
Thank you.
Okay, thank you. Great questions. Gentleman is asking a question here in the chat.
Yeah, same question, and Vivian, same question, but Notebook LM, sir. Actually, I have struggled since getting out of them. Abuse relationship, upload journals, text image, history, etc. to it alongside books, my personality disorder and some relationships. Actually, what I'm saying that has the interactive mode stopped working for everyone else. Sometimes interactive audio is not loading. Now, what is the most creative or helpful use case thing you have done with the Notebook LM or have seen done with it?
Yeah. So I'm not sure. Yeah, it could be a few things that were causing. I think you said you were having trouble generating audio. Was that correct? And some other things. Yeah. So overall, I found it to be quite good, especially in the multiple language sort of markets overall. But in terms of figuring out what's a good use case for Notebook LM, was that kind of the core of the question?
Yeah.
Okay, so versus other ones, so it's a couple things. One, I typically, when I'm thinking about from an agentic workflow, and again, this is how I do things. We're still gathering data on, I think, the right sort of flow on things, but usually I move to a notebook when I'm ready to formalize research into a specific topic. So I may go to, let's say, Gemini Enterprise or the Gemini app looking for some inspiration. So I have an idea or something that I want to work on, or I need to get more information about somebody. And then once I've kind of decided on the area that I want to focus on through my iterative process with Gemini for ideation, then what I do is I take it and actually, if you are testing Gemini Enterprise right now, there's a fantastic agent for ideation. I highly recommend you try it. Basically what it does is it generates hundreds of ideas and then argues with itself over each one of those ideas to figure out which the best one is and gives it a score. But essentially to take that kind of output or a deep research report on Gemini, and then I'm ready to kind of formalize that. So I put that, usually that source as my first kind of input to my notebook when I'm developing an idea. So since I help customers in pre-sales on customer engineering, I'm very interested in successful pilots and POCs. What were the steps that it took? What assets helped make them successful? And I start centralizing that stuff into the notebook while also using the added on capabilities to search the web and look for other events, let's say third-party tools, partners that are delivering those kind of services on top. They'll give me a good mass of information that then I can either dive in specifically. So typically I start at a macro level, look for things very interesting, maybe generate a mind map to see kind of the interconnectivity between the different assets and topics I've put in there, and then use that to deep dive into the research, and then sometimes find ways, okay, generate that node or that asset, feed it directly back into my notebook, or realize that it didn't work for the message I want. I don't want to, let's say, muddy other data with what I've reported there. And then I can use that, say, that an output based on analysis to either, let's say, build a prompt to improve another process or document I'm doing. So perfect example is I go to like I again take that output from that perfect pilot or POC for Google Workspace. I use it to refresh older assets because I've combined everything from, let's say, other regions and methodologies that they're having to build a new concrete guide that then I use that to drive and build other assets on top of it. Let's say if I'm trying to build like a project plan or initiative. So again, the idea is that what Notebook really is really great for is it's grounding. It uses only the data you have, so you can trust the output is based on something tangible to remove that hallucination layer, which sometimes does present it, but that usually just means you weren't specific enough with your prompt. So again, when I talk to customers about, okay, which AI tool should I start with, I would say
Yeah,
number one priority, understand your prompting.
the prompt saying that like interactive storytelling and video games and VR, these are okay, sir. So only sometimes interactive audio is not loading. That's the what is the main purpose. I don't
see.
know.
No, okay. Well, I don't have a perfect answer for why it's not working in that regard. I think we've obviously been having some capacity challenges over the last few days with the launch of 3.0. But it shouldn't have any, like, there's no major bugs I'm aware of that would prevent you from using it that way.
Thank you, sir. Thank you so much.
And of course.
Thank you, Christian. Thank you, Chintamani, for the question. A couple more that have come through in the chat. Jackson Ladyman asked, "What does grounding agent mean?"
Good point. That means basically you try to keep Gemini to be more factual. So for example, in Notebook LM, it will only use the data that I load into that notebook at source. No internet, no web, no additional sources. So it only based on that data. So if I ask it a question, all the data I've given it, that's its whole world. If it doesn't know the answer, it says, I don't know. Whereas Gemini, and I go into our web, with that context window, when it starts to run out, what you'll notice, you'll start to see more hallucinations. So if I send it a huge corpus of data and say, okay, use this as your grounding, but then I don't be specific enough with the constraints I put into my prompt by saying, okay, don't use anything outside this, don't speculate, don't give me anything that you cannot cite, that will basically then ground it to make sure that it doesn't, let's say, creative. Sometimes I want creativity and sometimes I don't. So it depends on the task that I'm trying to perform. But grounding it essentially just means, like, I want to keep you factual. Use only the things I give you.
Thank you, Christian. Hopefully, Jackson, that was a solid answer to your question. There's another one here. Do you expect Project Manager to fully replace RPAs?
No.
Same.
There's a human element to it that I do not think AI can replace.
Yeah, thank you, Mehmet. Good question. Another one comes through from Hannah. I have a question. How can I solve the problem Google Workspace Plus program, an unencrypted database of social service clients, is kept in Google Docs? Client data cannot be encrypted for operational reasons. The boss needs to connect the Gemini agent to the system to obtain statistics and statements for the service billing. How can this be done to comply with GDPR and AI Act regulations? Where can I find information about this?
Quite a complex question.
Yeah.
Yeah, so it's interesting. So, okay, unencrypted database of service clients is kept in Google Docs. Okay, client data cannot be encrypted for operations. And I assume that's because with the encryption, you wouldn't be able to access it for certain services. Is that correct? Needs to connect Gemini agent to system to obtain statistics statements for service billing.
Yeah, Hannah, you still on the call? I can see you actually. Maybe you'd like to come off mute and just add more context.
If you're too shy, I can give you a very like kind of basic approach, or at least how I would break this problem down, if that helps. But yeah, feel free to join in and ask the question line if you like.
For you, Hannah, Dad, if you're still with us. Oh, okay.
Okay.
Hannah's provided an email address for us to follow.
Okay, cool. Yeah, we can follow up. But at a high level, I would say, if just for the rest of the audience here, my approach to getting to the right answer would likely be to understand, again, regional controls, what exact regulatory like policy compliance, okay, GDPR mostly is a transparency thing. For example, Google Workspace is GDPR compliant. You would need to, again, check the service that you're using to access it. Does it meet with that compliance? That's a legal discussion. I can't give you an easy answer on that one, unfortunately, since I'm not a lawyer. An AI Act, obviously, again, you'd have to review those things. Again, there's nothing in this that jumps out to me, but industries, certain areas, like in Germany, for example, healthcare data is very, very like private and protected. And anytime a customer would say, hey, I want to put my healthcare data within Google Workspace and then use it to access service, I would say, okay, you really need to make sure Google Workspace is the right storage layer, just like you're using it right now to storage a database within Google Docs or Drive here. Is that the right storage to meet that compliance? So from a GDPR perspective, yes, it should be, but is it the right solution versus a database that can be regionally locked versus other things? And that's a bigger discussion. But again, I'll share some of this feedback with you over email.
Thank you, Christian. Hopefully, Hannah, that's satisfied you for now, but look out for an email from Christian as well. I just wanted to come to a couple of questions. I can see that Ruth Joshia has asked a question in the tool during the webinar and also copied it over here. I'll go to the tool first. Given the advent of agentic tools like Project Manager, which can automate complex workflows and eventually dissolve global scarcity and the necessity of forced labor, what is the architectural, ethically auditable KPI that Google will enforce to steer these advanced AI agents? The KPI that prioritizes human well-being, in brackets HWHZ, close brackets, and the value of meaningful effort instead of falling back on outdated level 3 KPIs like financial growth or shareholder value. There was another question, I think is a similar nature, further in the thread. No, actually, I think let's focus on that one for now.
Yeah, no, it's an absolutely fantastic question, and again, I don't think I'm the right person to speak on behalf of Google in answering that directly. But thanks, we can try to, maybe Tony and I can see if there's like a statement we make around this topic. But yeah, I probably wouldn't be the right person to answer this one.
I would also agree, and that's not deflecting the question, Ruth. We
I want to give you the right answer.
Yeah, we want to give you the correct answer, and I think there's probably better people than Christian and I that would answer that for you. So we'll take that away. Would you mind providing a contact email address so we can share some responses with you? If you're still with us, Ruth.
All right, thank you.
Much appreciated. Thank you. Chintamani.
Yeah, sir. Good evening. I'm on my last question, sir. Jupyter API server failures sometimes, sir. What we have strange issues to spun up a model in a container. First request was fine, sir. All subsequent requests failed, sir. Support said that the flash our browser catches some issues, some problems is there, sir. Some Jupyter API sometimes server is failure. Why it will fail, I don't know, sir. Sometimes okay, sometimes it's not okay. But strange, some model, if you have to take any model and container and first request, you have to request some requests, fine. Subsequent requests are failed, sir. So
Yeah. To be honest, I wouldn't know. There's a lot of things we'd have to look into, like troubleshooting around that. Unfortunately, I would say keep up the conversation with tech support, because and they can probably guide you towards the best thing, whether it's a public forum. Again, I don't think I would be able to troubleshoot that one effectively.
yes, sir.
Sorry.
So, but one more, sir. I have to say entire one some Vertex API, sir. From authentication to endpoints has been incredibly frustrating to my work, sir. With out of the hundreds of APIs we use, this one stands out as one of the most difficult. It feels you like Google designed this tool more for their engineers than for actual users, which seems to happen about 50% of the time is unreliable. Actually, 50% of time is okay, sir. Sometimes 50% of time unreliable, sir. Some authentication issues will be have to also found the issues, sir. And also Gemini 2.5 Pro also, sir. Flash is also good, sir, very good, but obviously not better than 2.5 Pro. Give it all my testing prompts is like 20 to 50% is faster than 2.5 Pro. Why, sir? I don't.
Interesting.
Yeah.
Yeah, again, probably too complex for me to be able to give you a good advice on this.
Actually, public domain, we are facing some issues that I have to put it up on in front of user. That's these are my questions, sir. In public domain, we are facing some issues in Gemini 2.5. That's
Yeah.
it.
Chintamani, we're trying to contain the conversation to Ultra AI today. If you are having ongoing conversations with support, that's probably the best place. Christian and I are definitely not the right people to respond to latency questions or issues with loading.
Yeah, unfortunately.
Yeah.
But yeah, I would say again, engage with support as well as like the cloud community. If you're part of our developers community, actually you can find some pretty good expertise and advice on there too.
Yeah, sir.
And also good news is Googlers are on the channel too, so they are also checking out for this type of feedback.
Okay, I think that we've covered all of the questions, and there were a few in the Google Gather which we can continue to respond to. Actually, most of the remaining ones by Chintamani, so hopefully we've covered those for you today. And any in the thread, I think I've captured all of them. They weren't really sequential, and I think that we've spoken to some of the points that were raised as well. So unless anybody has any further questions today, we'd like to thank you for joining us. Ruth, Joe, I will be reaching out to you. I've taken a note of your.
Yeah, because
your
one last
Causal mask. It's basically a binary firewall. It makes sure a token can only pay attention to tokens that came before it. Cause has to precede consequence.
So it enforces that left to right flow of language.
It does. I mean, if you were to set that entire mask to false, no token would interact with any other, and you just get random noise.
Okay, so let's say we take a whole prompt, it would be a 7-token question. We run it through that expensive ON2 calculation just to get the first output token. That whole process, that one-time calculation, that's what we call the pre-fill phase.
Yep. You pay that high quadratic price once to establish all the context.
Which naturally brings up the question,
yeah,
why would you ever want to do that again?
Why repeat that expensive work?
Exactly, because in the most sort of naive approach to generate the next token, token n+1, you'd repeat that entire ON2 prefill process. You do all the matrix math for all the previous tokens all over again.
It's pure waste.
Total waste.
But the causal mask actually gives us the solution here. When we generate a new token, let's say the word will, that new token only needs the context from the tokens that came before it.
Right.
And crucially, adding the word will does not change the internal attention calculations for any of the tokens that came before it. Their key and value states are fixed. They're done.
So if they're fixed, you should just save them somewhere. Put them in a cache.
Exactly. We cache the key and the value states that we computed during that initial prefill. And this is the famous KV cache.
And once that cache is built, the model shifts gears.
Right. It goes into the decoding phase.
This feels like such a simple trick, but it must fundamentally change the math of generation.
Oh, it's transformative. The cost to generate the next token, token n+1, drops from that quadratic ON2 all the way down to linear ON.
So you're just calculating the K and V for the one new token.
It's for the one new token, and then you look up everything else from the cache. This is why that stream of words after the initial pause is so fast. You're now operating in linear time.
That's a massive win for compute. But there's always a trade-off, isn't there? The cost must shift somewhere else.
It shifts entirely from computation to memory. If you've got thousands of users going at once, you are storing a monumental amount of these K and V vectors.
The memory cost must be huge.
It's substantial, and it's proportional to the sequence length, so ON.
Yeah.
Let's take Llama 2.7b as an example.
Okay.
That model has 32 layers, 32 attention heads, a head dimension of 128. For just one token, you need to store 2 times 32 times 128 values for the K and V states.
That's over 8,000 values per layer.
Per layer, right. And at float 16 precision, that works out to about 16 kilobytes of memory per token, per layer.
So if a user's chat gets up to, say, 2,000 tokens long,
that single session has now eaten up 32 megabytes of your precious GPU memory just for its KV cache. Now multiply that by thousands of concurrent users, and suddenly memory is your primary bottleneck.
Okay, so decoding is fast, but memory is expensive. Let's go back to the prefill problem for a second. What if my initial prompt is enormous? Like I give the model an entire code base to analyze, thousands and thousands of tokens.
Right.
That quadratic prefill calculation might need more memory for a single operation than the GPU even has.
And that's a very real-world constraint. The system can't just throw up its hands and fail. This leads to a technique called chunked prefill.
Chunked prefill.
Yeah, if your full prompt needs, say, tokens, but your GPU can only handle a passive n tokens at a time, you just split the prefill into smaller, manageable chunks.
Well, wait, how do tokens in the second chunk see the tokens in the first chunk? Doesn't that break the causal chain of attention?
Not at all, and it's thanks to the very thing we just talked about, the KV cache. You run the first chunk, you generate its KV states, and you store them. Then when you process the second chunk, you just prepend those stored KV states to the calculation. The attention mask is adjusted so the new tokens can look back and see the cached ones.
So you're using the KV cache not just between prefill and decode, but within the prefill phase itself.
Exactly. It lets us process these arbitrarily long inputs without ever blowing up the GPU memory. It's very clever.
It's super clever. Okay, so we've solved the high initial cost by moving from ON2 to ON with the cache.
Right.
We've solved the huge prompt problem with chunked prefill. Now we have to scale. We need to serve lots of people.
Right, and the natural next step is to group multiple user requests into a single batch.
And this is where all these clever methods start to create new problems, specifically that massive padding waste.
Naive batch generation has this one really rigid requirement. All the data has to be in rectangular tensors.
Meaning everything has to be the same length.
Exactly. So if you have 4 prompts of different lengths, 10, 50, 100, and 120 tokens, you have to pad the first 3 with useless placeholder tokens to make them all 120 tokens long.
So you're spending compute cycles on garbage data from the very start.
Ah.
And it only gets worse once the generation starts, right?
It gets much worse in 2 ways. First, imagine the shortest prompt, the 10-token one, finishes first. It outputs its end-of-sequence token.
Done.
But it's not done. Every computational cycle you spend on that sequence from then on is completely wasted. You're just generating junk until the longest prompt in the batch finally finishes. You're held hostage.
And what we really want to do is yank that finished request out and slot a new one in immediately to keep the GPU busy. We need dynamic scheduling.
We do. But now imagine doing that. We drop the short, finished prompt, and we insert a new waiting request that needs a long prefill, say, 150 tokens.
Oh, I see the problem.
The rest of the batch is doing super fast, 1-token decoding, but the naive system says, nope, everyone has to be the same length. So now everyone else has to pad all the way up to 150.
So just trying to be efficient by adding a new request, creates this cascading disaster of inefficiency for all the other requests.
The padding cost grows quadratically with both the batch size and the length of that new prompt you just added. It's staggering. If you have a batch of, say, 8 and you insert one new 100 token prefill, you are wasting hundreds and hundreds of token generation steps on padding. That rectangular constraint just kills your efficiency.
So what does this all mean? We have to throw out the whole idea of a rigid rectangular batch.
Yeah.
We have to get rid of padding entirely.
The only way to do that is to eliminate the separate batch access. You stop thinking of sequences as individual rows in a rectangle. Instead, you concatenate all the tokens from all the requests together.
You just stack them end to end?
End to end into one massive continuous sequence.
And this creates what's called ragged batching, I think, because the lengths are all uneven or ragged.
That's it. And the trick then becomes, how do you run attention on this single giant tensor but stop tokens from user A's prompt from looking at tokens from user B's prompt? You can't have that crosstalk.
It has to be the attention mask again. That's the control lever.
It is the ultimate control mechanism. Since you can't rely on the shape of the tensor anymore, you rely completely on the mask. You dynamically build an attention mask that acts as a firewall.
So for every single token, the mask is tailored to only let it see other tokens from its own prompt.
Exactly. It only allows interactions within its own sequence, and it explicitly disallows any interaction with tokens from the other sequences in that big concatenated batch.
So the physical input is this one huge tensor, but the logical batch is defined purely by the mask. That seems like a fundamentally more flexible way to use the GPU.
And that combination, ragged batching, dynamic scheduling, plus that underlying KV cache, that is the definition of continuous batching. It lets us keep the GPU pipeline totally full.
So now that we have this flexibility, how does the system actually decide what to put in the batch to get the most throughput?
It's all about keeping the system busy with the cheapest work first. I like to think of the GPU memory budget as a constantly changing game of Tetris. You have a maximum height you just can't exceed.
I love that analogy, okay.
So you prioritize the fast linear cost work. First, you slot in all the one-token decoding requests. These are the small, fast blocks that only need ON compute. You add those until your memory is almost full.
And if you still have some space left over after all the decode requests are in?
Then you strategically fill the rest of the space with the long multi-token prefill prompts. And because we have chunked prefill, you don't even have to put the whole 500 token prompt in at once.
Alrighty.
You just insert the first chunk that happens to fit into the remaining budget. Once that's processed, you reevaluate the whole batch for the very next cycle.
So by mixing these short, fast decoding requests with the long, chunked-up prefill requests in one continuously changing ragged batch, you make sure every single computation cycle is generating a useful token for somebody. You've eliminated almost all the waste.
That's it. It's an incredible feat of engineering.
It really is. It totally transforms the economics of running these models at scale.
It does.
So let's recap the 3 core techniques that continuous batching brings together for this huge throughput boost. First, there was KV caching.
Right, that avoids recomputing everything, taking us from that quadratic ON2 cost down to a much more manageable linear ON.
Second, we had chunked prefill, which lets the system handle those gigantic input prompts without crashing by staying within the GPU's memory limits.
Yeah.
And finally, the real innovation here, ragged batching with dynamic scheduling. It breaks that rigid, wasteful rectangular rule and uses the attention mask as a firewall to get rid of padding and keep the GPU constantly busy.
And that ability, that dynamic mixing of the high-cost prefill and the low-cost decode in one batch, that is precisely why modern AI services can handle thousands of concurrent users so efficiently.
Without this, the cost to run something like ChatGPT would just be astronomical.
It would be completely prohibitive.
But this entire system hinges on the KV cache. And if we have thousands of active requests, and each one is caching, you said, dozens of megabytes of KV data, the total memory for the cache itself must become this huge, fragmented mess.
It absolutely is. And managing that immense, highly fragmented pool of KV cache memory, like preventing fragmentation, making sure there's minimal wasted space, that is the next frontier in LLM optimization. It leads directly to even more advanced techniques like paged attention.
Paged attention.
Exactly. So that's a fascinating challenge for you to mull over. How would you design a system to allocate memory pages dynamically for thousands of sequences that are all growing unpredictably one token at a time?
You know, if you've ever used a modern large language model, Quinn, Claude, any of them really.
Oh yeah, everyone has at this point.
You know that feeling?
Yeah.
You type your prompt, you hit enter, and then there's that little pause. It can feel kind of agonizing.
Like it's processing the entire history of the universe.
Right. But then the first word pops out and the rest just streams onto your screen super quick and steady.
And that experience, that initial choke point followed by the rapid fire generation, that really tells the entire story of high performance LLM serving.
So what's really going on under the hood?
Well, fundamentally, every LLM is just a very, very fancy and costly next token predictor. To get even one token, you have to pass your input through billions of parameters. It involves these colossal matrix multiplications.
And that single operation is the core technical challenge, isn't it? I mean, for one user, okay, it's expensive. But if you're a massive service trying to maximize throughput.
Throughput, right. The number of useful tokens you're generating per second across all users.
You're going to hit some immediate, just brutal resource bottlenecks.
Exactly. So our mission for this deep dive is to get into the optimization that really cracked this challenge, continuous batching.
Okay.
And we're going to build this concept from the ground up. We'll start with the single most expensive operation inside that transformer architecture.
All right, let's unpack this. And I guess that journey have to start with the attention mechanism. That's the heart of it, right? It's how these models understand context.
It is. So when the model gets text, it tokenizes it. And for a lot of operations like layer normalization, the tokens are processed totally independently. They don't know about each other.
But they have to interact. I mean, the word blue is useless if it doesn't know it's connected to the word sky.
Precisely. And the attention layers are the only place where different tokens actually interact. They communicate with each other.
How does that work?
It's achieved by projecting the input into 3 different states. You've got query, key, and value, Q, K, and V.
All right, we hear those terms constantly.
Yeah.
Q, K, and V.
Yeah.
But what do they, conceptually, what do they represent?
Think of it like a little search engine inside the sentence. The query, the Q, is what the current token is searching for. It's the context it needs to understand itself.
Okay.
And the key state, the K, represents what all the other tokens offer. They're like contextual tags or IDs.
So Q is looking, K is offering. What about V, the value?
The value is the actual information payload that the token carries. So when we calculate the attention scores, we're multiplying the query by the transpose of the key. That's the Q-K transpose operation.
And that's a huge matrix multiplication.
A huge one. And it's measuring the similarity between what one token is looking for, the Q, and what every other token is offering, the K.
And I think this is where the computational bill just gets staggering.
It absolutely does, because you're comparing every single token against every other token. The cost isn't linear.
Yeah.
It's quadratic in sequence length.
So we describe that as what, O of n squared complexity?
Exactly, ON2. And what that means for you is if you double your prompt length, say from 100 to 200 tokens, the computation time doesn't just double, it quadruples.
Wow.
And that's why that initial processing step, that first pause, is so slow.
And of course, the model can't cheat. It can't look at words that come after the one it's working on. So there's a filter for that.
That filter is the attention mask, specifically a causal mask. It's basically a binary firewall. It makes sure a token can only pay attention to tokens that came before it. Cause has to precede consequence.
So it enforces that left to right flow of language.
It does. I mean, if you were to set that entire mask to false, no token would interact with any other and you just get random noise.
Okay, so let's say we take a whole prompt, it would be a 7-token question. We run it through that expensive ON2 calculation just to get the first output token. That whole process, that one-time calculation, that's what we call the prefill phase.
Yep. You pay that high quadratic price once to establish all the context.
Which naturally brings up the question,
yeah,
why would you ever want to do that again?
Why repeat that expensive work?
Exactly, because in the most sort of naive approach to generate the next token n+1, you'd repeat that entire ON2 prefill process. You do all the matrix math for all the previous tokens all over again.
It's pure waste.
Total waste.
But the causal mask actually gives us the solution here. When we generate a new token, let's say the word will, that new token only needs the context from the tokens that came before it.
Right.
And crucially, adding the word will does not change the internal attention calculations for any of the tokens that came before it. Their key and value states are fixed. They're done.
So if they're fixed, you should just save them somewhere. Put them in a cache.
Exactly. We cache the key and the value states that we computed during that initial prefill. And this is the famous KV cache.
And once that cache is built, the model shifts gears.
Right. It goes into the decoding phase.
This feels like such a simple trick, but it must fundamentally change the math of generation.
Oh, it's transformative. The cost to generate the next token n+1, drops from that quadratic ON2 all the way down to linear ON.
So you're just calculating the K and V for the one new token.
It's for the one new token, and then you look up everything else from the cache. This is why that stream of words after the initial pause is so fast. You're now operating in linear time.
That's a massive win for compute. But there's always a trade-off, isn't there? the cost must shift somewhere else.
It shifts entirely from computation to memory. If you've got thousands of users going at once, you are storing a monumental amount of these K and V vectors.
The memory cost must be huge.
It's substantial, and it's proportional to the sequence length, so ON.
Yeah.
Let's take Llama 2 7B as an example.
Okay.
That model has 32 layers, 32 attention heads, a head dimension of 128. For just one token, you need to store 2 times 32 times 128 values for the K and V states.
That's over 8,000 values per layer.
Per layer, right. And at float 16 precision, that works out to about 16 kilobytes of memory per token, per layer.
So if a user's chat gets up to, say, 2,000 tokens long,
that single session has now eaten up 32 megabytes of your precious GPU memory just for its KV cache. Now multiply that by thousands of concurrent users, and suddenly memory is your primary bottleneck.
Okay, so decoding is fast, but memory is expensive. Let's go back to the pre-fill problem for a second. What?
Thousands. Okay. And at float 16 precision, that works out to about 16 kilobytes of memory per token, per layer.
So if a user's chat gets up to, say, 2,000 tokens long,
that single session has now eaten up 32 megabytes of your precious GPU memory just for its KV cache. Now multiply that by thousands of concurrent users, and suddenly memory... Right. And at float 16 precision, that works out to about 16 kilobytes of memory per token, per layer.
So if a user's chat gets up to, say, 2,000 tokens long,
that single session has now eaten up 32 megabytes of your precious GPU memory just for its KV cache. Now multiply that by thousands of concurrent users, and suddenly memory is your primary bottleneck.
Okay, so decoding is fast, but memory is expensive. Let's go back to the pre-fill problem for a second. What if my initial prompt is enormous? Like I give the model an entire code base to analyze thousands and thousands of tokens.
Right.
That quadratic pre-fill calculation might need more memory for a single operation than the GPU even has.
And that's a very real-world constraint. The system can't just throw up its hands and fail. This leads to a technique called chunked prefill.
Chunked prefill.
Yeah, if your full prompt needs, say, tokens, but your GPU can only handle a pass of n tokens at a time, you just split the prefill into smaller, manageable chunks.
Well, wait, how do tokens in the second chunk see the tokens in the first chunk? Doesn't that break the causal chain of attention?
Not at all, and it's thanks to the very thing we just talked about, the KV cache. You run the first chunk, you generate its KV states, and you store them. Then, when you process the second chunk, you just prepend those stored KV states to the calculation. The attention mask is adjusted so the new tokens can look back and see the cached ones.
So you're using the KV cache not just between prefill and decode, but within the prefill phase itself.
Exactly. It lets us process these arbitrarily long inputs without ever blowing up the GP memory. It's very clever.
It's super clever. Okay, so we've solved the high initial cost by moving from ON2 to ON with the cache.
Right.
We've solved the huge prompt problem with chunked prefill. Now we have to scale. We need to serve lots of people.
Right, and the natural next step is to group multiple user requests into a single batch.
And this is where all these clever methods start to create new problems, specifically that massive padding waste.
Naive batch generation has this one really rigid requirement. All the data has to be in rectangular tensors.
Meaning everything has to be the same length.
Exactly. So if you have 4 prompts of different lengths, 10, 50, 100, and 120 tokens, you have to pad the first 3 with useless placeholder tokens to make them all 120 tokens long.
So you're spending compute cycles on garbage data from the very start.
Ah.
And it only gets worse once the generation starts, right?
It gets much worse in 2 ways. First, imagine the shortest prompt, the 10-token one, finishes first. It outputs its end-of-sequence token.
Done.
But it's not done. Every computational cycle you spend on that sequence from then on is completely wasted. You're just generating junk until the longest prompt in the batch finally finishes. You're held hostage.
And what we really want to do is yank that finished request out and slot a new one in immediately to keep the GPU busy. We need dynamic scheduling.
We do. But now imagine doing that. We drop the short, finished prompt, and we insert a new waiting request that needs a long prefill, say, 150 tokens.
Oh, I see the problem.
The rest of the batch is doing super fast, 1-token decoding, but the naive system says, nope, everyone has to be the same length. So now everyone else has to pad all the way up to 150.
So just trying to be efficient by adding a new request creates this cascading disaster of inefficiency for all the other requests.
The padding cost grows quadratically with both the batch size and the length of that new prompt you just added. It's staggering. If you have a batch of, say, 8 and you insert one new 100-token prefill, you are wasting hundreds and hundreds of token generation steps on padding. That rectangular constraint just kills your efficiency.
So what does this all mean? We have to throw out the whole idea of a rigid rectangular batch.
Yeah.
We have to get rid of padding entirely.
The only way to do that is to eliminate the separate batch axis. You stop thinking of sequences as individual rows in a rectangle. Instead, you concatenate all the tokens from all the requests together.
You just stack them end to end?
End to end into one massive continuous sequence.
And this creates what's called ragged batching, I think, because the lengths are all uneven or ragged.
That's it. And the trick then becomes, how do you run attention on this single giant tensor but stop tokens from user A's prompt
from looking at tokens from user B's prompt. You can't have that crosstalk.
It has to be the attention mask again. That's the control lever.
It is the ultimate control mechanism. Since you can't rely on the shape of the tensor anymore, you rely completely on the mask. You dynamically build an attention mask that acts as a firewall.
So for every single token, the mask is tailored to only let it see other tokens from its own prompt.
Exactly. It only allows interactions within its own sequence, and it explicitly disallows any interaction with tokens from the other sequences in that big concatenated batch.
So the physical input is this one huge tensor, but the logical batch is
You concatenate all the tokens from all the requests together.
you just stack them end to end.
End to end into one.
Hi there. My name is Tim Peacock. I'm the Senior PM for Detection Platform, UEBA, and Risk in Google SecOps. And in my spare time at Google, I'm the co-host of the Cloud Security Podcast by Google.
Thank you, Tim. My name is Vijay Ganti. I'm the Director of Product Management here at Google, and I run the PM team for Gemini for security.
And we're
so we're diving into AI Camp today.
Gemini and security operations today. So, as we're talking about all these agentic capabilities, I had this unshakable feeling when I was walking around the RSA show floor this year that I had heard all of this before. It really felt like the messaging on the AI booths was so similar to the messaging on the SOAR booths of just 10 years ago. And so my first question to you as the guy leading all this for us, haven't we heard this before? What's different this time?
I think you're right to be skeptical. There is good reasons. We've heard this story many times. But it is different this time around. And what's unique about this technology is actually four things. Right? The first is this technology has the ability to generalize, which means that you don't have to train these models on every task with large amounts of data. Right? So it's able to generalize and is able to learn from very few examples. That's the first capability. The second thing that's an emergent property of this technology is its ability to plan. Given a complex task, like us human beings, it's able to break it down into a plan. And the third big capability that again is an emergent property is able to reason around the data that it finds. This reasoning capability is also super important. And the last thing is an all-important capability that it allows us to do something and not just think about it. And that is the ability to take action, right? Now, all these four things now are being worked into in a principled way to increase the capability of these models to do complex tasks in an autonomous fashion. As an example, the React framework.
Not just for JavaScript.
It's not just for JavaScript, you're right. React framework is all about reasoning, acting, observing, and then based on an observation, again, adapting your reasoning, right? That feedback loop is something that has been done in a principled way, which has added to the capability of autonomy that this technology has.
That feedback loop sounds a lot like an OODA loop. It's really an observe, orient, decide, act. It's like a fighter pilot.
I think it's exactly right. I mean, that is what it is. It is the OODA loop for the agents in some sense. That's totally right.
So let's see a demo of that. Let's see that in the product. So here we are in Google SecOps, and we're looking at an investigation of this potential RDP tunneling to an external. And this is not an alert type that we've trained it on in particular. This is just some alert we've got. And we've given it to the agent, and the agent is coming up with a plan to figure out whether this case is true or not.
That's right.
And so the first thing we see the agent do is investigate the hash. And this is a very normal thing to do first. And what it learns from that is not malicious.
Yeah.
But let's see it go further. So as the agent continues its investigation, it actually runs a query and gets more data. And based on that data, it's actually able to understand the intent of what's happening in these events. And based on the intent, it's actually able to work out that this is likely to be a malicious situation going on. And so we've got generalization.
Yeah.
We've got planning.
Yeah.
We've got tool use.
Yeah.
That's amazing.
And reasoning, as you said.
And reasoning. That's incredible.
Exactly. This is the implementation of all those 4 things that we talked about.
And it's all right there in Google SecOps today.
Exactly right.
That's incredible. So, as we're looking at this and as we're seeing all of these capabilities, you're seeing all the opportunity ahead of us. Where do you think the greatest opportunity lies today?
No, Tim, that's a great question. I think the opportunities are in 3 categories or 3 buckets.
Okay.
The first is set of workflows that exist today, but we can actually improve the efficiency of these workflows with this technology in a dramatic fashion.
Okay.
An example of that is the one that you showed just now, which is alert triaging, right? So alert triaging is something that customers do today.
Mm-hmm.
Unfortunately, they get hundreds of thousands of alerts, and their capacity to investigate those alerts is limited to 50 or 100 alerts.
So what do they do with the other 99,950?
It's a great question. Great question. But the good news is now we have help.
Now we have help.
Now we have help. Exactly right. So that's the first bucket. The second bucket or the second category is workflows that we have today, but that require high degree of expertise, which very few customers actually can afford.
What's an example of that?
An example of that would be malware analysis. You know this, Tim, malware analysis is so hard to do because the adversaries who are creating these malwares are well-funded, highly capable people.
Oh, yeah.
Who are writing this to evade our best defenses and our best experts.
And the history of our industry is the cat and mouse of that.
That's exactly right. And they're writing this software in different platforms. They're writing obfuscation technology, multiple layers of obfuscation, trying to hide it. To unpeel that onion takes a lot of expertise, a lot of figuring out. That's one thing that we can do. Why don't you show it to us, Tim?
Let's see that.
Yeah,
let's see that. Okay. So here we're inside Google Threat Intelligence. And all I've said to the model is, hey, would you please analyze and get the file associated with this hash?
Yeah.
And so I've given it very little to work from. I've told it implicitly 2 things: analyze it and get it. So the first thing it's going to do is go get some tools that it knows how to use and go get that file from VT. And then it's going to get this file, get a report about that file. But maybe that report isn't enough, and we want it to actually analyze the file itself.
Right.
And so here the agent has gotten the file and it's going to start analyzing it. And what's amazing here is, again, the generalization. It's never seen this file before.
That's right.
But it's able to come up with a plan. And so what's the plan look like? Well, we see what kind of file it is. It's an Excel file. Maybe it's got a macro.
That's right.
So it's going to go look at that macro. Well, looking at a macro, that's complicated.
That's right.
And in this case, it's a particularly complicated macro. And so what the agent is seeing is, first, we've got something very obfuscated here as a PowerShell command. And as it analyzes it, as it works through it, it realizes that it's actually been obfuscated twice.
That's
and
right.
that there's multiple compression things happening in parallel here. And so the agent then writes a Python program to deobfuscate it.
That's right.
And so we go through the deobfuscation. There's a lot of obfuscation happening here. We get the plain text of the final decoded PowerShell command, but that's not enough to tell us whether it's good or bad. We need to understand the intent of that PowerShell command.
Right.
And so here the agent is understanding what it would do. And what I love is the final conclusion here. We scroll all the way down through its understanding, and it says, finally, this macro is unequivocally malicious.
Oh, wow.
That's amazing.
I love the confidence.
What confidence it has. And so again, for the analyst, you could read all of this stuff and understand what the agent has done. Or if you happen to trust it, we get a final verdict. The Excel file is malicious.
That is fantastic. That is so fantastic. I mean, the intent that you expressed, it's able to create a plan which points to its ability to generalize. It points to its ability to plan.
To use tools.
That invokes tools to act. Then it analyzes the output of those tools and reasons about it to update its plan. So it's kind of using that React-like framework.
Yeah.
And there's an implementation of that, which is quite amazing.
That's an amazing piece of Google threat intelligence
back
right
to,
there.
Yeah, and it goes back to, Tim, the third category.
Yeah, so what's that third category?
So imagine this now. Take this forward a little bit, right?
Yeah.
The expertise level we've lowered in this case. But now if we can automate this process for every file, and we can automate this in a way that it happens in seconds or minutes.
Instead of days.
Instead of days and months.
Right.
VirusTotal, which is part of Google Threat Intelligence, has a place where 3 million users submit millions of files every day. Every day, 2 million files a day.
It's a lot of files.
And we can analyze the maliciousness of this and the various behaviors being exhibited in minutes. With that data, we can publish the cyber weather. You can find out what's happening in your cyber neighborhood.
That's incredible.
At any point in time. This was something that was not possible. You couldn't even imagine it.
Because it requires all that analysis at scale, which you couldn't do.
Which you couldn't do.
Because of talent.
Which brings us to the third category. The third category is all the possibilities.
Wait, it gets more impressive?
No, which unlocks the things that you could have imagined but couldn't do or couldn't even have imagined.
Right.
So this is an example of that, but it goes beyond that.
Tell me.
If you think about this, today security is largely reactive. Threats come in, we detect them, we investigate them and respond to them. We have some preventive layers, but they're not really threat. They don't have an understanding of threat.
My first team at Google was so reactive.
Right.
We chose as our motto in Latin, equo elapso, which means with the horse having already left the barn.
That's exactly right. I mean,
that's how security's been for decades.
And it's not for lack of trying. It just hasn't been possible. But now you don't have to wait for the attacks to happen. You can simulate the threats that are relevant to you using this technology. You can identify the assets that are most critical to you, most risky for you using this technology. You can understand the efficacy of controls for those particular assets. And you can identify those gaps and fix those gaps before those attacks happen.
That's amazing.
Right, so you can do it continuously. But that's not all. You can go further. Most of these attacks happen because bad guys are selling access to your environment.
Access brokers.
They're selling your credentials for your employees in these forums. And in these forums, you want to be able to monitor their activity there. So you can shift left your detections. So the attacks, you can react to it before the attacks come to your shores.
But we've had dark web monitoring before. What's different with LLMs?
Yeah, I mean, it's a great question. Most of our LLM, or rather the detections for deep dark web, were based on regular expressions or keyword based. Now that's very brittle.
Very brittle.
It's so easy to bypass those. I mean,
look at this.
That's right. In this example, I mean, if an attacker, all they have to do is not name my company, but describe my company vaguely.
Yeah.
And it will completely evade my keyword search. Or maybe use it in a different language.
Right.
But with this
my Russian's not very good.
That's right. My French is as good as my Spanish. So, but yeah. So with this technology now, we don't have to match based on keyword, but we can match based on intent. And that completely changes the game. So yes, this technology has existed in the past, but now it's different. It's truly different.
It's truly different.
Right. So those are the three categories.
Okay, that's amazing. So, one of the things that's been so hard for security teams has been the silos. And the silos are created both by people's limitation and the limitations of the products that exist. And people are stuck with the interfaces that they're given by their tool vendors. And so what if these security silos didn't actually define our lives? What would that look like?
I think, Tim, you hit on a very important point. This technology is it's going to break silos, and it's enabling new experiences for us. Let me talk through that a little bit, and we'll also show a demo here. But the silos, as you rightly said, have existed because of limitations. We've had different vendor silos. We've had product silos. We've had functional silos. Vulnerability management is different from SOC operations, is different from identity teams, is different from threat intelligence. These are functional silos. So how do you break across all of these silos? It's been hard to do that. But with this technology, you can express your intent that actually can span all of these capabilities, can span all of these vendors, can span all of these domains, as an example, which we can do. And we will demonstrate that here. But the second thing that is also important is it allows us to have experiences that are completely new. You mentioned this. Why should I have to go to the product to get a capability? Why shouldn't the capability come to where I am?
Yes.
And
why should I go to that console? Why shouldn't it come to me?
Why should it come to me?
Yeah.
And that has been a problem because the integration has been a hard thing to do. But we are solving those problems with MCP Server, right? So I'll give you just one example. We have an implementation of MCP Server that allows us to publish our capabilities to a model. And now you as a user can express your intent to your AI chat client. And the model figures out which capability it needs to go to respond to your question, to respond to your intent.
Let's see an example of that.
Let's see an example of that.
Okay, so here I am in my MCP client, and I've said to my model buddy, can you find me a case that contains alerts from multiple vendors? And so what the tool is able to do is invoke SecOps APIs, pull that data, and bring it into my context. And so as we go through, I can ask it in very conversational ways, just describe this case, tell me about it. And so it's able to pull that details, summarize those, and present to me, the analyst, the things that are most interesting about it. And so here we've got an alert which actually contains data from multiple different vendors, and it's bringing it together, and we've totally broken that vendor silo down and presented rich contextual data to the user. But if we want to get more details, we can say, well, what about the executable in there is so bad? And so as we work through this, it can pull more data, it can summarize that data, and it can highlight the aspects of that that are most important. And so here, it's actually pulling in events from another case that are related. And I didn't even ask it to do that. It was able to infer, I need to do that. And so as we go through, you can see how it's pulled all of this context together, and it's even able to recommend what I should do next.
This is so amazing. I mean, I'm seeing the interface here, experience here is so conversational. You're expressing your intent. It seems like you have a developer friend helping you in the background who is at lightning speed stitching APIs together across these product and vendor boundaries.
Yeah.
And meeting your needs on the fly.
Exactly.
And that is this model.
That's incredible, right?
It's amazing. From 1 million developers or so, whatever we have, to 7 or 8 billion.
Anybody that can talk to it in any language
is a developer.
Yes.
That is amazing new experience.
That's totally amazing.
Fantastic.
Fantastic. So this all sounds amazing, but what's the catch? Because whenever I hear something that sounds this good, I feel like that guy on the boat. I don't believe it. So what's the catch?
No, I think there are no catches, but I think there is a gap between the promise and making that promise a reality.
Yeah.
Which is what we are working on. And there are 3 specific dimensions, Tim, to that. The first one is we all know and understand that this technology is non-deterministic.
Right. What does that mean?
Which means that it has a degree of statistical randomness. Every time you ask a question, it might answer it slightly differently because the context just has changed. Think about it like human beings. We human beings are not like computers. We respond based on the context we have slightly differently.
Right.
Okay. But our users expect predictability and reliability.
Especially their auditors.
Exactly right. So I think what we need to do is we need to do the work required in a principled way to deliver reliability. And there are 2 things that
How do you do that?
Yeah, there are 2 things that are important. For these models and these technologies, what we can control is what goes into them, which is the context.
We're context engineering.
Exactly. So the better we get at providing the context and more principled we are, we can provide more guardrails and more guarantees that this will perform well. And the second part is managing the output. Every time it generates something, you should be able to verify it in some reasonable way, and then have that feedback loop. So reliability through context engineering and verification, right? And that operating in a loop. That's the first thing. The second thing we need to worry about for our domain, specifically security, is about economics.
Okay.
We have trillions of events. You know about security telemetry.
Oh, yeah,
we have trillions of events happening every day. And if you go and ask a model for all of these trillion events, that's going to be economically exorbitant. We cannot afford that, neither can our customers, right? So we need to figure out a way to make this work in an economic way. And we are doing that work, but that's an important dimension. The third dimension, which is very important, is our customers want to be able to rely on this technology, which means we need to earn their trust. And you earn their trust through transparency. You show your work. And so trust through transparency is the third pillar. So these are the three things that we need to work on to bridge the gap between the promise and reality of this.
So that's all amazing. What's our plan for getting this into the hands of our customers who definitely need this stuff? What's the plan?
Yeah, Tim, great question. So as we had mentioned, we are right now working on the agentic alert triage and agentic malware analysis. We will follow that up with agentic detection tuning, which is very important for addressing the false positive noise problem, along with agentic threat hunting, which is really important to detect sophisticated attackers.
Amazing.
That will be followed with agentic exposure management, which is about extending your detection capabilities beyond your shores, beyond your networks, into deep dark web forums.
That's fantastic. So we've heard about a lot of capabilities. We've seen a lot of capabilities. Let's hear from one of our customers, Apex Financial, who is using these capabilities in Google SecOps today.
Fantastic.
No longer do we have our analysts having to write regular expressions that could take anywhere from 30 minutes to an hour. Gemini can do it within a matter of seconds. And our detection turnaround time has also greatly improved from 3 to 4 hours to 1 hour. My name is Hector Pena. I'm the Senior Information Security Director at Apex FinTech Solutions. We chose Google Cloud Operations as the best in breed as well as the best integration platform for the existing Google Cloud platform that we've already known and familiar with. We use that system to identify and respond to everyday threats that are impacting Apex and the financial institution. We need to account for multiple different avenues, from SaaS applications to on-prem infrastructure to cloud applications, where as an attacker, they only need to find one vulnerability, one entry space. We had a legacy platform that just didn't meet the standards of a modern-day fintech organization. Google Cloud Security Operations is much more advanced than our legacy tech. We were able to generate faster queries, to create new detections, and to ingest logs from multiple different data sources that also weren't just GCP. One of the features that I find extremely helpful is the Unified Data Model Logging. The UDM model allows us to not spend time grooming logs as they're coming on ingest, but instead we can use them directly. Google Security Operations offers a data retention policy that allows our analysts to retroactively identify any threats that have occurred in the past. Google Security Operations is empowering us to be not only near real time, but to ensure that we have Apex covered for the last 12 months. When we moved to Google Security Operations, we were able to reduce the time to detect and time to investigate to about 15 to 30 minutes. No longer spending time in disparate tools, but performing the job functions of security operations analysts, and empowers them to work on more advanced workflows. We can develop playbooks that interact with the other security operations tool sets that aren't directly tied to Google Security Operations, but Google Security Operations is the brain of that. We use Gemini within Google Security Operations for natural query language, where we can ask it a simple question such as generating a regular expression that can be used for a curated detection or a security detection within the platform, where it'll provide upfront context for us where the analysts no longer have to investigate basic information. They can use the Gemini AI feature right within the case management feature to explain the case, give brief details about what they're looking at and what they're experiencing. Apex's relationship with Google Cloud has been excellent. They're consistently checking in on the progress for us, and they're ensuring that we partner with them and we trust them to make informed decisions about our roadmap internally, as well as to help drive new technology and bring Apex to the forefront of a security operations center. Apex FinTech Solution is building a new way to securely invest and generate wealth for everyone.
Okay, that's amazing to hear how they're doing that. Vijay, thank you so much for joining me today. Do you have any closing thoughts for our audience?
This is so exciting. I think what lies ahead of us, Tim, is even more exciting. As we bridge the promise and reality gap, the possibilities are limitless for us. And I think finally we have a technology that can truly give us, the defenders, an advantage. So I'm super excited about that.
Well, we've got a lot of work to do. We better get back to it. Thanks so much for joining us today.
Thank you.
Tokens, but your GPU can only handle a passive n tokens at a time, you just split the prefill into smaller, manageable chunks.
Well, wait, how do tokens in the second chunk see the tokens in the first chunk? Doesn't that break the causal chain of attention?
Not at all, and it's thanks to the very thing we just talked about, the KV cache. You run the first chunk, you generate its KV states, and you store them. Then, when you process the second chunk, you just prepend those stored KV states to the calculation. The attention mask is adjusted so the new tokens can look back and see the cached ones.
So you're using the KV cache not just between prefill and decode, but within the prefill phase itself.
Exactly. It lets us process these arbitrarily long inputs without ever blowing up the GP memory. It's very clever.
It's super clever. Okay, so we've solved the high initial cost by moving from ON2 to ON with the cache.
Right.
We've solved the huge prompt problem with chunked prefill. Now we have to scale. We need to serve lots of people.
Right, and the natural next step is to group multiple user requests into a single batch.
And this is where all these clever methods start to create new problems, specifically that massive padding waste.
Naive batch generation has this one really rigid requirement. All the data has to be in rectangular tensors.
Meaning everything has to be the same length.
Exactly. So if you have 4 prompts of different lengths, 10, 50, 100, and 120 tokens, you have to pad the first 3 with useless placeholder tokens to make them all 120 tokens long.
So you're spending compute cycles on garbage data from the very start. And it only gets worse once the generation starts, right?
It gets much worse in 2 ways. First, imagine the shortest prompt, the 10-token one, finishes first. It outputs its end-of-sequence token.
Done.
But it's not done. Every computational cycle you spend on that sequence from then on is completely wasted. You're just generating junk until the longest prompt in the batch finally finishes. You're held hostage.
And what we really want to do is yank that finished request out and slot a new one in immediately to keep the GPU busy. We need dynamic scheduling.
We do. But now imagine doing that. We drop the short, finished prompt, and we insert a new waiting request that needs a long prefill, say, 150 tokens.
Oh, I see the problem.
The rest of the batch is doing super fast, 1-token decoding, but the naive system says, nope, everyone has to be the same length. So now everyone else has to pad all the way up to 150.
So just trying to be efficient by adding a new request creates this cascading disaster of inefficiency for all the other requests.
The padding cost grows quadratically with both the batch size and the length of that new prompt you just added. It's staggering. If you have a batch of, say, 8 and you insert one new 100-token prefill, you are wasting hundreds and hundreds of token generation steps on padding. That rectangular constraint just kills your efficiency.
So what does this all mean? We have to throw out the whole idea of a rigid rectangular batch.
Yeah.
We have to get rid of padding entirely.
The only way to do that is to eliminate the separate batch axis. You stop thinking of sequences as individual rows in a rectangle. Instead, you concatenate all the tokens from all the requests together.
You just stack them end to end?
End to end into one massive continuous sequence.
And this creates what's called ragged batching, I think, because the lengths are all uneven or ragged.
That's it. And the trick then becomes, how do you run attention on this single giant tensor but stop tokens from user A's prompt from looking at tokens from user B's prompt? You can't have that crosstalk.
It has to be the attention mask again. That's the control lever.
It is the ultimate control mechanism. Since you can't rely on the shape of the tensor anymore, you rely completely on the mask. You dynamically build an attention mask that acts as a firewall.
So for every single token, the mask is tailored to only let it see other tokens from its own prompt.
Exactly. It only allows interactions within its own sequence, and it explicitly disallows any interaction with tokens from the other sequences in that big concatenated batch.
So the physical input is this one huge tensor, but the logical batch is defined purely by the mask. That seems like a fundamentally more flexible way to use the GPU.
And that combination, ragged batching, dynamic scheduling, plus that underlying KV cache, that is the definition of continuous batching. It lets us keep the GPU pipeline totally full.
So now that we have this flexibility, how does the system actually decide what to put in the batch to get the most throughput?
It's all about keeping the system busy with the cheapest work first. I like to think of the GPU memory budget as a constantly changing game of Tetris. You have a maximum height you just can't exceed.
I love that analogy, okay.
So you prioritize the fast linear cost work. First, you slot in all the 1-token decoding requests. These are the small, fast blocks that only need ON compute. You add those until your memory is almost full.
And if you still have some space left over after all the decode requests are in?
Then you strategically fill the rest of the space with the long multi-token prefill prompts. And because we have chunked prefill, you don't even have to put the whole 500 token prompt in at once.
Alrighty.
You just insert the first chunk that happens to fit into the remaining budget. Once that's processed, you reevaluate the whole batch for the very next cycle.
So by mixing these short, fast decoding requests with the long, chunked-up prefill requests in one continuously changing ragged batch, you make sure every single computation cycle is generating a useful token for somebody. You've eliminated almost all the waste.
That's it. It's an incredible feat of engineering.
It really is. It totally transforms the economics of running these models at scale.
It does.
So let's recap the 3 core techniques that continuous batching brings together for this huge throughput boost. First, there was KV caching.
Right, that avoid recomputing everything, taking us from that quadratic ON2 cost down to a much more manageable linear ON.
Second, we had chunked prefill, which lets the system handle those gigantic input prompts without crashing by staying within the GPU's memory limits.
Yeah.
And finally, the real real innovation here. Ragged batching with dynamic scheduling, it breaks that rigid, wasteful rectangular rule and uses the attention mask as a firewall to get rid of padding and keep the GPU constantly busy.
And that ability, that dynamic mixing of the high-cost prefill and the low-cost decode in one batch, that is precisely why modern AI services can handle thousands of concurrent users so efficiently.
Without this, the cost to run something like ChatGPT would just be astronomical.
It would be completely prohibitive.
But this entire system hinges on the KV cache. And if we have thousands of active requests, and each one is caching, you said, dozens of megabytes of KV data, the total memory for the cache itself must become this huge, fragmented mess.
It absolutely is. And managing that immense, highly fragmented pool of KV cache memory, like preventing fragmentation, making sure there's minimal wasted space, that is the next frontier in LLM optimization. It leads directly to even more advanced techniques like paged attention.
Paged attention.
Exactly. So that's a fascinating challenge for you to mull over. How would you design a system to allocate memory pages dynamically for thousands of sequences that are all growing unpredictably one token at a time?
Welcome to the AI That Works podcast, where we show you real practical examples of how to use AI that works. We do a lot of live coding. We do a lot of whiteboarding. I'm Dex. I'm the founder of Human Layer. We build tools to help you solve hard problems with coding agents. I'm going to pass it over to Vaibhav.
Hey everyone, I'm Vaibhav. I build BAML. We try and make tools that make it really easy to increase the reliability of LLM pipelines.
Amazing. And what are we working on today?
I think today is going to be a fun live coding session. We've done one more of these in the past, and you and I have obviously live coded together.
Ladies and gentlemen, please welcome back to the stage, Jed Borovic.
Welcome back.
A longer episode, which is going to be a fun time.
How are we doing? All right, these next sets of talks are going to be particularly good. I'm really excited for the first one. We're going to be hearing about world models, but not the world models you're normally used to. We're going to be learning about modeling the world of code and computation. Please welcome to the stage research scientist from Meta, Jacob Kahn.
All right, thank you, Jed. Great to be here, everyone. I'm Jacob Kahn. I'm a researcher at Meta AI. I'm going to talk today about the code world model, which I'll abbreviate as CWM, and what it means to build world models for computation. This is work done by an incredible team at FAIR, extends all over the world. I'm very grateful to be collaborating with them. So what's our goal with CWM? Our primary goal is to build models that reason, plan, and make decisions, and we start with code because it's an interesting sandbox in which to think about reasoning, right? It's constrained, there are certain rules with code. And so our goal is to predict future observations, given past observations and actions. That's maybe what it means to build a world model in some sense, and we want to do this because we can learn good representations of things if we learn some sort of mapping between observations and the future. And eventually that leads us to planning and reasoning, and we can consider different actions and see if we like the results for decisions we make. I think there's a bit of a false dichotomy right now between world models and large language models. World models are just a parameterization of a problem, as I'll discuss. LLMs are a way to view and use that parameterization. And I'll dive into more of what that means in a bit. So one of the fundamental questions we're asking with CWM is, what does it mean to model code? Is code literally the syntax in your editor, or is it something else? And if you think about it, all a model sees that is operating on code is just syntax, right? We tokenize the input, it goes into the model, and we predict more code as the output. This is the starting and ending point for an analysis of a program with a token-based autoregressive model. It's just a syntax, but what if we instead modeled execution more explicitly? And what if we created maybe a natural language systematic description of programs, and neural models could ingest a more structured representation of what it means to execute code? And then maybe we could emit autoregressively this representation too. So that's one of our goals for CWM. We want to predict program execution because we believe it might lead to us better modeling things about code, writing code, analyzing code, and beyond. And so what we're going to implicitly do is predict the transition function of program states as we go about executing. So this is what execution tracing might look like in action. We have a program, we're going to count the number of R's in strawberry, and at each step, maybe we'll have some frame separator, which will denote distinct lines of execution, and we'll actually explicitly have local variables. We can introduce things about memory in that trace, and that will delineate line by line what's happening as our program executes. And this is something we could essentially feed to a model because each line of our execution trace maps to a corresponding line in a program. We don't have to stop at functions. We could think about entire repository level execution traces. We could think about distributed system level execution traces. We could think about modeling execution for code contest solutions or something more complex, programs with high complexity. We could also then transition that into, as I said, natural language tracing, and we'll see what that means in a moment. But what does it actually look like to model that transition function at a high level as we start to parameterize the problem? Well, we have programs or we have data. That's some state. We have an action executing the next line, and that results in the next state. And so both the program execution and the model's decision making in an agentic sense can be modeled as a transition function. So where are we? This broader approach, world modeling, we could say in an agentic reasoning setting, we have a problem, we have a model that thinks about the problem, it takes an action in the world, we get some feedback, maybe we fail, we think again, and we iteratively continue this process with feedback from the environment. Maybe in the sense of code, that environment is just an execution in a code setting, right? But with a world model, maybe we can actually simulate, we can imagine that action. We can get feedback in our imagined environment, so we could actually generate execution traces about a program without executing it. And this gives us the ability to be far more efficient with how we actually structure our agentic execution. We don't have to interact with the real world unless we're ready to. So let's couple this with autoaggressive large language models. Right now, we have a state of a program, we have an action, maybe the next line, and then we get to a new state, we take another action, etc. And so we can sort of turn this with the execution tracing format I mentioned into almost a chain of thought that a model can just interpret. A model can learn to predict the next state of an execution trace. And so an LLM can autoaggressively generate token by token the state and action to state function with program executions as the starting point. Okay, let's talk about data for a second. Let's talk about for CWM, we gathered a huge amount of GitHub data, we take GitHub events, and as I said, we're interested in modeling things at the repo level if we can, at the systems level if we can. We want to have execution traces go outside of the scope of simple programs. And so we'll take a bunch of PRs, we'll mutate those PRs, predict changes, and we'll eventually have a raw PR data set. And we can actually run tests or CI on those GitHub repos when we know they're passing, and then generate execution traces from that repo level data if we want. So here we are at the artifact, the code world model itself. I'll talk a bit about what we did with it, how we trained it, and then what we can do with some of these interesting execution trace capabilities. But first, it's a 32 billion parameter dense transformer. This is a model for research. This is not a huge MOE you can't play with. You can play with it right now. It has a nice long context length for some reasoning tasks. And we train it end-to-end. We do all the pre-training and post-training ourselves. Processes, we pre-train on a few trillion tokens. We mid-train on some more domain-specific data. We do some long context mid-training. We fine-tune further on some instruction following and reasoning tokens. And then we do this joint RL and agentic reasoning setup. So let's parameterize the problem even more broadly with CWM. We have a prompt. We have an agent. We do some reasoning. We take an action. We can use a tool. We can emit text, which is code. That goes into the environment. We take a step, and from that environment, we get a few things back. We get tokens, we get rewards, we get log probabilities, we might get compiler outputs. So with CWM, we're also taking a big step back with how we interact with the environment. CWM is a very bash-oriented model. It has fewer tools than do other models, and it has to learn how to use the terminal pretty well to solve a lot of the tasks we give it. And this starts with SWRL, and with SWRL, we take a GitHub issue, we feed it to the agent, starting with that repository level data set from before, and we just use bash, right? We learn commands in bash, and that lets us mutate our environment, that lets us mutate the state of files. We can maybe use an edit tool eventually or create content and then submit things. But ultimately, we're trying to put the model in an environment that's very, very similar to what an engineer would be in and learn end-to-end in a bash-based setting. Okay, so we can bootstrap this setup further. We can do some SFT before RL, and we can find some failure modes for the model. We can rejection sample, so we can take a bunch of agentic reasoning traces on code tasks that failed, and we can basically feed those back into the model. So in this example here, we have a thinking trace where we're thinking about instantiation logic for some code, and I can look for that code. I can call an explicit grep function, and this is something we did with CWM, again, with fewer tools and a larger emphasis on bash as a starting point. Let's talk about post-training for a moment. We want to scale post-training quite a bit. This is the trend we see, and we're getting a lot of excellent returns from a reasoning perspective when we post-train. So part of solving this for CWM, because we have a small model, is an opportunity to really scale up how we do post-training, and in particular, to improve the throughput of the system. And we're doing a synchronous RL-based setup. We have samplers. We have an environment where we can execute in the terminal and get outputs. We have a bunch of trajectories, reasoning trajectories we output. We have a trainer where we compute gradients and score trajectories. We have a source of truth for the model, and then that loop repeats. So what's the challenge here? We have this loop, right? We have samplers predicting trajectories. We have scoring trajectories. We're executing in the environment. As we're doing this, we're going to update a model eventually. We have a produce-consume pipeline problem. And so samplers are producing lots of trajectories that are consumed by those trainers. We need to synchronize weights. And so we solve this in CWM with a very, very asynchronous model. So of course, we have a trainer that's sending a model checkpoint to a sampler very, very eagerly. We have trajectories which are being sampled and then sent back to trainers very eagerly. But in particular, we have queues. So we actually will have many models queued up to be input into a sampling system. We'll have many trajectories queued up to be scored and then added vis-a-vis gradients to the trained model. And so this setup stays relatively on policy, even though it's highly asynchronous. And we're not really waiting for much with this setup. We're able to achieve very, very strong throughput because of the asynchronicity. So one interesting feature, we have local variables. We can introduce things about memory. The syntax in your editor, or is it something else? And if you think about it, all a model sees that is operating on code is just syntax, right? We tokenize the input, it goes into the model, and we predict more code as the output. This is the starting and ending point for an analysis of a program with a token-based autoregressive model. It's just the syntax, but what if we instead modeled execution more explicitly? And what if we created maybe a natural language systematic description of programs, and neural models could ingest a more structured representation of what it means to execute code? And then maybe we could emit autoregressively this representation too. So that's one of our goals for CWM. We want to predict program execution because we believe it might lead to us better modeling things about code, writing code, analyzing code, and beyond. And so what we're going to implicitly do is predict a transition function of program states as we go about executing. So this is what execution tracing might look like in action. We have a program, we're going to count the number of R's in strawberry, and at each step, maybe we'll have some frame separator, which will denote distinct lines of execution, and we'll actually explicitly have local variables. We can introduce things about memory in that trace, and that will delineate line by line what's happening as our program executes. And this is something we could ostensibly feed to a model because each line of our execution trace maps to a corresponding line in a program. We don't have to stop at functions. We could think about entire repository level execution traces. We could think about distributed system level execution traces. We could think about modeling execution for code contest solutions or something more complex, programs with high complexity. We could also then transition that into, as I said, natural language tracing, and we'll see what that means in a moment. But what does it actually look like to model that transition function at a high level as we start to parameterize the problem? Well, we have programs where we have data. That's some state. We have an action executing the next line, and that results in the next state. And so both the program execution and the model's decision-making in an agentic sense can be modeled as a transition function. So where are we? This broader approach, world modeling, we could say in an agentic reasoning setting, we have a problem, we have a model that thinks about the problem, it takes an action in the world, we get some feedback, maybe we fail, we think again, and we iteratively continue this process with feedback from the environment. Maybe in the sense of code, that environment is just an execution in a code setting, right? But with a world model, maybe we can actually simulate, we can imagine that action. We can get feedback in our imagined environment, so we could actually generate execution traces about a program without executing it. And this gives us the ability to be far more efficient with how we actually structure our agentic execution. We don't have to interact with the real world unless we're ready to. So let's couple this with autoregressive large language models. Right now, we have a state of a program, we have an action, maybe the next line, and then we get to a new state, we take another action, etc. And so we can sort of turn this with the execution tracing format I mentioned into almost a chain of thought that a model can just interpret, a model can learn to predict the next state of an execution trace. And so an LLM can autoregressively generate token by token the state and action to state function with program executions as the starting point. Okay, let's talk about data for a second. Let's talk about for CWM, we gathered a huge amount of GitHub data, we take GitHub events, and as I said, we're interested in modeling things at the repo level if we can, at the systems level if we can. We want to have execution traces go outside of the scope of simple programs. And so we'll take a bunch of PRs, we'll mutate those PRs, predict changes, and we'll eventually have a raw PR data set. And we can actually run tests or CI on those GitHub repos when we know they're passing, and then generate execution traces from that repo level data if we want. So here we are at the artifact, the code world model itself. I'll talk a bit about what we did with it, how we trained it, and then what we can do with some of these interesting execution trace capabilities. But first, it's a 32 billion parameter dense transformer. This is a model for research. This is not a huge MOE you can't play with. You can play with it right now. It has a nice long context length for some reasoning tasks. And we train it end-to-end. We do all the pre-training and post-training ourselves. Processes, we pre-train on a few trillion tokens. We mid-train on some more domain-specific data. We do some long context mid-training. We fine-tune further on some instruction following and reasoning tokens. And then we do this joint RL and agentic reasoning setup. So let's parameterize the problem even more broadly with CWM. ourselves. Processes, we pre-train on a few trillion tokens, we mid-train on some more domain-specific data, we do some long context mid-training, we fine-tune further on some instruction following and reasoning tokens, and then we do this joint RL and agentic reasoning setup. So let's parameterize the problem even more broadly with CWM. We have a prompt, we have an agent, we do some reasoning, we take an action, we can use use a tool, we can emit text, which is code, that goes into the environment. We take a step, and from that environment, we get a few things back. We get tokens, we get rewards, we get log probabilities, we might get compiler outputs. So with CWM, we're also taking a big step back with how we interact with the environment. CWM is a very bash-oriented model. It has fewer tools than do other models, and it has to learn how to use the terminal pretty well to solve a lot of the tasks we give it. And this starts with SWRL, and with SWRL, we take a GitHub issue, we feed it to the agent, starting with that repository level data set from before, and we just just use bash, right? We learn commands in bash, and that lets us mutate our environment, that lets us mutate the state of files. We can maybe use an edit tool eventually, or create content and then submit things. But ultimately, we're trying to put the model in an environment that's very, very similar to what an engineer would be in, and learn end-to-end in a bash-based setting. Okay, so we can bootstrap this setup further. We can do some SFT before RL, and we can find some failure modes for the model. We can rejection sample, so we can take a bunch of agentic reasoning traces on code tasks that failed, and we can basically feed those back into the model. So in this example here, we have a thinking trace where we're thinking about instantiation logic for some code, and I can look for that code. I can call an explicit grab function, and this is something we did with CWM, again, with fewer tools and a larger emphasis on bash as a starting point. Let's talk about post-training for a moment. We want to scale post-training quite a bit. This is the trend we see, and we're getting a lot of excellent returns from a reasoning perspective when we post-train. So part of solving this for CWM, because we have a small model, is an opportunity to really scale up how we do post-training, and in particular, to improve the throughput of the system. And we're doing an asynchronous RL-based setup. We have samplers. We have an environment where we can execute in the terminal and get outputs. We have a bunch of trajectories, reasoning trajectories we output. We have a trainer where we compute gradients and score trajectories. We have a source of truth for the model, and then that loop repeats. So what's the challenge here? Gradients and score. We have a bunch of samplers. We have an environment where we can execute in the terminal and get outputs. We have a bunch of trajectories, reasoning trajectories we output. We have a trainer where we compute gradients and score trajectories. We have a source of truth for the model, and then that loop repeats. So what's the challenge here? We have this loop, right? We have samplers predicting trajectories. We have scoring trajectories. We're executing in the environment. As we're doing this, we're going to update a model eventually. We have a produce-consume pipeline problem. And so samplers are producing lots of trajectories that are consumed by those trainers. We need to synchronize weights. And so we solve this in CWM with a very, very asynchronous model. So of course, we have a trainer that's sending a model checkpoint to a sampler very, very eagerly. We have trajectories which are being sampled and then sent back to trainers very eagerly. But in particular, we have queues. So we actually will have many models queued up to be input into a sampling system. We'll have many trajectories queued up to be scored and then added vis-a-vis gradients to the trained model. And so this setup stays relatively on policy, even though it's highly asynchronous. And we're not really waiting for much with this setup. We're able to achieve very, very strong throughput because of the asynchronicity. So one interesting feature of this, which is increasingly common, is that we're actually updating models mid-trajectory. So I have a model which we're sampling from, it's interacting with the environment, it's generating data, it's executing bash commands, it's executing code, it's getting output, and I might actually update that model while it's interacting with the environment. So mid-trajectory, I could totally swap the model with a new checkpoint. And the trajectory will change a little bit. Theoretically, that trajectory is a bit off policy, but the guarantees we have with the system are quite strong still, in that because of the throughput and because of the amount of data we see, we're able to make a lot of guarantees around and take a lot of risk with updating the model on the fly. And this gives us really a system with our very, very few bottlenecks overall. Because we're queuing models, we're queuing trajectories, we don't have to wait until anything is done. Okay, so overall, we post-train on still a relatively small number of steps at pretty large scale, and we process about 200 and some billion tokens. And this scale works really well. It produces a strong model, a strong open model. It's a pretty small model, it punches above its weight. It's very nice, it's pretty versatile, it uses tools in Bash very well. But what can we actually do with this model, right? What can we do with a model that understands program execution traces, that maybe has a good understanding of how a program will run and predicting future state of a program? CWM traces code really well, right? We know that, we've showed it execution traces, and I can actually give it a function, and then I can go and trace line by line that function with very, very high accuracy. It can show me the values of local variables at certain points, again, with a lot of precision. And this gives us some pretty interesting capabilities. I can think about a neural debugger on top of a model. Traditionally, right, I have a piece of code, I don't know what I want to write, I put some question marks. Historically, I might prompt a model with natural language. I want to set the variable left and right to be something in particular, I don't know what it is. Now I need to specify very fully the ambiguity that I'm experiencing with how to complete my program. With CWM, I can express those things very naturally in line with code. And I can actually express the shape of the program I want with code, and the model will fill in the rest. And the model fills in the rest by understanding that the user wrote a for loop here, the user wrote the condition here, the user left a variable and assigned. Well, if I were to go execute that, I could simulate the execution of that loop and understand better what it is the user is really after. And so a neural debugger is something that helps you compose with code side by side. It's not just generating code. And it allows you to, again, express the semantics of code very, very loosely, but also very, very precisely. So if I have a piece of code where I want a certain structure, I can ensure that the model understands that structure and can implicitly trace the execution. This will make theoreticians bristle, but I can also think about some really ambitious things in computer science. The halting problem, we know, is this very fundamental problem where we don't know if a program is going to halt, to stop executing, to terminate. And in particular, this is tough because in order to know if a program halts, we would have to simulate the entire execution of the program, which if it didn't halt, would take forever. So the halting problem is in some sense a difficult problem to simulate or decide. And so the question we can ask with CWM is, can I approximate some of these things? Can I concretely reason about program execution dynamics in this sense? So can I say, here's a program, does it halt? Maybe the model, by simulating execution, can understand really, really high-level patterns. In the same way, the model can understand high-level patterns in broader systems, right? I could use this to debug a huge distributed system where executing code is very, very expensive, or even an expensive function on a single machine, right? But the ability to have an implicit world model internally, where I'm simulating what's happening with a piece of code or a broader system, gives me the ability to reason about it without executing otherwise expensive things. So we can make some progress with the halting problem by building a model that simulates it, that simulates execution, and from there we can simulate and approximate what it means to solve otherwise impossible problems in computer science. So this is pretty interesting. With that, I want to encourage everyone to go build on CWM. This talk does halt, this talk does terminate. And the model's available on Hugging Face. We have some code on GitHub which will help you get started with inference in a fashion where you can twiddle bits a bit more. We also have a technical report, again, where we really try to be as open as possible with all of these details around training. This post-training setup I mentioned is explained in even more
how I do this. Like, okay, if the integration
a model with these capabilities could be used for. Thanks for your time. Have fun.
Our next presenters are here to teach us how to train models more efficiently through efficient RL. Please join me in welcoming to the stage the co-founders of Applied Compute, RhythmGarg, and Lyndon Lee.
Hey everyone, it's great to meet you all. Really great to be here today. My name is Rhythm. This is my co-founder Lyndon. Our third co-founder Yash couldn't make it today, but we're all very excited to be here. Three of us were previously researchers at OpenAI, and now we're bringing frontier AI inside of enterprise at Applied Compute. Today we're going to be talking about efficient reinforcement learning. As some context on Applied Compute, we help enterprises build their own intelligence to power real work in their company. We think a lot about how do we push AI beyond productivity into real automations that deliver ROI that's quantitative for the company. Once we build a system that's specialized to the way that a company operates for a particular use case, we deploy it with a data flywheel so that it gets better over time the more and more that you use it. Picture an in-house expert at a company that's always at the forefront of their field. RL mechanically is the tool that we use in order to bring these out-of-distribution data sets in distribution for the models today. Yash, Lyndon, and I all worked on the RL effort at OpenAI in its early days, and we saw firsthand the power of RL in going and maximizing these public benchmarks. Now we're taking that a step further and helping enterprises go solve the problems they care the most about, sort of their private benchmarks. So here's a very high-level overview of how high compute RL helps LLMs acquire these reasoning and intelligence capabilities. Let's say that you have a data set of math problems, and we pick 4 of them for an RL training step. Then we'll take an open source model, say one of the GPT-OSS models or one of the Llama models, and we have the model attempt each of those 4 problems 100 times. So each of these 100 attempts is the model thinking through how it would get to the final answer and then ending off with the final answer itself. And these are many, many reasoning tokens in its thinking trajectory. We can grade all of these answers. And when the model is correct, we can bias the model's weights to reinforce its thinking trace in that attempt. When it's incorrect, we can discourage the model from having that kind of behavior again. So in this fashion, as we do more and more training steps with batches of 4 problems, 100 attempts each, the model learns to reason and solve math problems, and it becomes really, really good at math. Of course, at Applied Compute, we're not really helping enterprises solve math problems, but this is kind of the mechanism by which we're able to teach the models to get really, really good at tasks that they care about. So as we mentioned, the type of RL work that we do at Applied Compute is actually quite different from the lab. So these are some real-life photos from the labs and a photo we took at the Applied Compute office the other day. The labs do these big training runs over several weeks. We do more specialized runs. And there's a couple of aspects of RL training that are particularly important to us. We need our runs to be fast so that we can train a model and deliver it to a customer very quickly on the order of days. They have to be cheap so that our unit costs work and we're able to scale the business sustainably. And importantly, and this is a point that I think it's easy to miss, we need our estimates for how long these training jobs will be to be very low variance, because we don't want to just be generally fast, we want to be reliably fast when we work with customers. And so the research problem for us that is very business critical is, can we build an RL stack that is so efficient so that in conjunction with our agent building platform, we are really able to scale up this use case specific training motion. So let's start with an inefficient form of RL, which is synchronous RL. In synchronous RL, sampling and training happen in lockstep. So there's some simplifications here, but let's say that we want to train on batches of 8 samples. That means we're going to wait for all 8 samples to finish, and basically finish completion before we start training, and then we're going to repeat this process again. As a result, we have a lot of idle GPUs that are waiting on that third straggler sample to complete. So in other words, in synchronous RL, our step times are dictated by whatever sample takes the longest time in order to complete. To illustrate why this is bad, we took 40 arithmetic problems, requested 32 samples each for each of them with Qwen30B, and we measured how long it would take for these samples to complete. It turns out that 99% of the samples completed in about 40 seconds. Took another 80 seconds to get that last percent of samples to complete. It really has a long tail. So as you'd expect, if you look at the throughput chart, the GPUs are doing a lot of work at the beginning when all of the sampling requests are launched. But by the end, they're very, very underutilized because they're waiting on those last samples to complete. The technical term we use at Applied Compute is the GPUs are slacking. So synchronous RL is not an efficient way to use these GPUs. In order to solve this problem, we need to break the condition that sampling and training need to happen in lockstep. In other words, we need to allow training while we're sampling. This is called asynchronous RL, and there are many approaches to doing asynchronous RL. One that we particularly like is pipeline RL from Pichet et al. We're going to make some simplifications here, but in asynchronous pipeline RL, we dedicate some GPUs to sampling and some GPUs to training. The sampling workers never stop. They're constantly doing inference with high batch size. As samples complete, they get added to a queue for training, and the training workers pull a batch from the queue to train on. After a batch has been trained on, the training workers propagate the new model weights to all of the sampling workers for what's called an in-flight weight update. And this is really what differentiates pipeline RL. The sampling workers might be in the middle of a sample, but their weights will still get updated if a training step is completed. As a result, we end up with samples that had multiple versions of the policy that contributed to the sample in order to generate it. In other words, there are still tokens in some of these samples. Let's take a look at one sample to make this a bit more clear. As you can see, there's 3 versions of the policy at time steps t, t+1, and t+2 that were used to generate this sample, since there were 2 completed train steps and in turn 2 in-flight weight updates while the sample was being generated. So when this sample gets trained on in the t+3 to t+4 training batch, we will have some tokens that came from policy 3 steps behind, some that came from policy 2 steps behind, and those last 2 tokens that came from a policy that was 1 step behind. Now let's say that we only tolerate staleness up to 2. That means we're not going to allow the in-flight wait update after the T+1 to T+2 training batch completes. And that means the training workers are just going to be idle, waiting for the sample to complete before they can propagate that in-flight wait update and start training on the next batch. Because if they were to do the in-flight wait update, that would cause this sample to have staleness 3, as we just saw. And if we only tolerate staleness 1, the training workers are going to be idle for even longer, which is bad. So as you increase how much staleness you tolerate, you have less idle GPUs in general. But as we all know, there's no free lunch. This is the standard policy gradient with an importance ratio to adjust for the fact that we're sampling from a policy at time step t and training with the policy at time step t plus k, given that there's k staleness. The importance ratio is what makes this policy gradient unbiased, but the variance of that ratio increases as you increase staleness. And so this is kind of the big issue here, because now with higher variance importance ratio, learning can become unstable and cause divergence. The concrete trade-off is we want a lot of staleness for fast RL runs, but a lot of staleness makes learning unstable, which then requires innovating on the algorithm and the science. And this is one of the primary research problems that we focus on here at Applied Compute. And as I was talking about earlier, it directly flows back into our core business. For the purpose of this talk, we're going to focus on a simpler subproblem. Let's assume that we have good science and algorithmic innovations that allow us to tolerate staleness up to some fixed threshold, and we have some fixed compute budget, as usually exists in the world. What is the highest throughput way for us to do RL in this setting?
Cool, thanks for them. So we pose this as a modeling problem of our end-to-end system, which admittedly is a little bit complicated at first, but we did find that we can get surprisingly far with some first principles systems modeling. And as with any modeling problem, let's figure out the cast of characters that describe the system, and then we'll think about how they all fit together to model it. So the first cast member is some proxy of compute budget, in which in this case we have is the number of GPUs. In the synchronous setting, like Rhythm just explained, all the GPUs will either be used for training or sampling, since they happen one after the other. But in the asynchronous setting, it's a little bit trickier, because we can choose to allocate that pool of GPU compute as much as we want for training or as much as we want for sampling, and that leads to some design decisions. The next is the training batch size, which is some proxy of the workload that we have on the overall system. And this is kind of an ML decision, but in short, what we have is a batch of problems, which is a subset of our data set. Let's say we have n math problems that we want to train on. And for each of these problems, we're going to sample n problems in parallel. So if the problems are really difficult, we might sample more to encourage some diversity in the samples, to encourage the model to learn some potentially divergent strategies. The next thing we need is some proxy of sampling throughput. And to get some intuition of what we should choose here as a modeling decision, let's look at how some modern inference engines surface requests. So in GPU memory, we have the model waits the activations in some runtime state called the KV cache in memory. And given this trained model, we're going to run the forward pass several times, where each forward pass samples the next token, and then we'll write to the KV cache. And so what this model shows is that a principal estimate that we should do is we should find some way to measure the latency per GPU of the forward pass. And this ends up being a pretty good choice in practice, because from the systems angle, the inference throughput that we choose is largely determined by the batch size that we perform sampling with. So what I've shown here in the red square is a batch of tokens that are all forwarded at the same time. And this sampling forward pass needs to be as large as possible to efficiently utilize the GPUs, subject to the runtime constraint that we don't actually run out of memory in the KV cache. So what we can then do actually run out of memory in the KV cache. So what we can then do is we can fit a latency curve as a function of batch size. And that latency curve will look something like this. You'll have some regime where it's memory bound, and when it increases, it becomes compute bound, and there's some functional form below. And to explain the details of why we chose this decision, what we have here is an equation that's based on the roofline model from systems. At lower batch sizes, which I've highlighted in yellow here, we don't have that much work to do, because there isn't that much compute to do on the processor, and there's so many parameters you need to load in at the same time. And so as a result, when you add incremental work, it doesn't really add that much latency to the overall system, since the processor is so fast at doing math that we're just waiting on memory to stream parameters in from memory to the processor. But as the batch sizes begin to get larger, we then get bottlenecked by the processor, and the more we add to our batch, the slower the forward pass takes. And just for good measure, we have this sigmoid here that just sort of modulates the smooth transition at this hinge point here to show that there's a subtle transition from a memory-bound computation to one that's more compute-bound and bottlenecked by the processor.
The final cast member is some proxy of training throughput, and we chose to measure this on a per GPU basis. So in this case, the model takes in the training batch size, so the parameter we saw earlier, and we typically do this by fitting a proxy of our empirical workloads. The units here is how many tokens per second each training GPU processes. So it needs to do the forward, the backward, and some optimizer steps. So given these 4 cast members, we can then begin modeling the system. And the first idea we had, although Rhythm suggested that this might not be a great idea, we can think about how to use a synchronous setup. And this might be a good idea from first principles because we definitely meet the staleness constraint because we don't train on stale data, and we always use the entire GPU fleet for either training or sampling, making sure that we're using efficient use of the hardware. Let's think about how to actually model this. There are 2 things we need to know. We need to know the batch size at which generation runs, and we also need to know the response length distribution to figure out how our training workload is going to work and also how long the sampling is going to take. And so what I'm showing here in this simulation is a couple of engines. Each square is a request being processed, and they get darker and darker as we make progress throughout the batch. And as they finish samples, they write to the queue. And on the right-hand side is a time series metric, maybe something that you'd see in Grafana if you're monitoring production metrics. And what you can see is that the batch size begins very high, but it slowly goes down over time as it eventually goes to 0 and all the samples complete, and we can finally run an optimization step. After the step completes, we run this in a loop, and we move on to the next step. And so as a result, we can have the following sampling procedure. We do maximum tokens inference forward passes, where maximum tokens is the total number of forward passes we do for the longest request. We use the fitting tokens is the total number of forward passes we do for the longest request. We use the fitted latency estimator to figure out how long that forward pass will take, and then the response length distribution will tell us how many responses to drop. And so what we're showing in this video here is this entire thing of the response length distribution that we feed into the latency estimator. At training time, we can compute the total number of tokens that we just sampled in the batch and divide by the total training throughput, which is just the number of GPUs multiplied by the per GPU training throughput. And so what we have here is a simulation of what this latency curve looks like. So we have the CDF of the response length distribution that tells us how many responses we should drop on the left, and the latency curve on the right. And this roughly kind of tracks because as we add more GPUs, we expect the latency per step to go down. The next idea, given that the synchronous setup might not be the most principled choice, as Rhythm showed, is an asynchronous setup. But it's not just as easy as just sort of provisioning the compute between training and inference, because if we don't do this carefully, we might actually run into the idle GPU problem again. And to show this, let's illustrate 2 extremes of what this allocation problem looks like. Let's first look at one end of the spectrum, where we provision way too many inference GPUs and not that many samplers. In this case, we're consuming from a queue much faster than we're actually producing from it, because the sampling workers are producing work significantly slower than we can actually consume them. When the red square grays out, it shows that they're idle. And what this diagram should hopefully illustrate is that for a lot of the time, we're actually not using that, and that has the same problem of low GPU utilization in the synchronous case as shown earlier. On the other end of the extreme, we can provision way too many sampling GPUs, in which case our production rate is way faster than the rate that we actually consume them in. So here we've doubled the number of overall sampling GPUs and halved the number of training GPUs. As you can see, they produce samples at much more rapid of a rate, but this index here in each yellow square, which is the staleness count of each sample, goes up. And as time moves on, we get more and more stale, and so the samples get more and more more and more transparent as a result, and we learn less from each individual sample. So let's think about how we can actually model this workload then to determine an optimal async workload. In this case, the picture looks a little bit different because in steady state, the batch size is relatively consistent compared to the synchronous setup where it kind of goes down over time. So on the right-hand side here, we have the same time series metrics, but in this case, it's a little bit different because the yellow squares are always full because every time we complete a sample new sample goes in and we can continue writing to the queue. And so that batch size with a little bit of wiggles just for good measure is pretty consistent over the course of a run. Now, obviously, the caveat here is that this batch size will certainly go down as as response lengths go up because we run out of cache, KV cache. But that's kind of a separate story. And actually, our model accommodates for that because we're actually accommodating for a response length distribution. We can then begin to figure out the optimal layout, and there's 2 kind of constraints that we have to satisfy now that we know that the generation batch size is roughly consistent throughout the course of a run. The first invariant that we need to have is that the production and consumption rate are roughly equal. So on the left-hand side of this equality, we have the training throughput, which is the number of training GPUs multiplied by the per GPU throughput, and then also we have the number of sampling GPUs multiplied by the sampling throughput, which is just the batch size multiplied by the latency to actually do a forward pass on that batch size. And the next thing is that, given that Rhythm indicated that if we have too much staleness, that can be bad from an ML perspective, we want to make sure that our max theoretical staleness or simulated staleness doesn't exceed what our ML can handle. And so here we have the max staleness on the left, which is equal to, on the top, how much time the longest request took in the batch, which is just the maximum number of tokens multiplied by the amount of time each token forward pass takes. And on the bottom here, we have the length of a training step, which is the training batch size multiplied by the mean sequence length. So the simulation here then will sweep through multiple different values of the number of training GPUs, and since we have a fixed pool of compute, that then implies a certain number of GPUs used for sampling. And for this number of sampling GPUs, we can compute the minimum steady state generation batch size to make sure that we don't blow out of memory, subject to our KV cache memory constraints, and also such that we have maximum throughput on the sampling side. And the final thing is we want to prune out all simulations where the sampling throughput brings us over the maximum possible staleness. When we look at that simulation, we can run it end-to-end similarly, parameterized by the response length. We see that this kind of roughly simulates a 60% speed up relative to our the response length, we see that this kind of roughly simulates a 60% speed up relative to our synchronous baseline, assuming that the GPU compute is optimally allocated between training and sampling. As a result, when we sweep layouts within these constraints, this allows us to limit staleness, but also make sure that we have our runs running at maximal throughput without actually doing the run itself. And so this gives us insight to simulate different workloads before actually running them on the GPU, because these runs can actually be fairly expensive. And so this allows us to answer scientific questions from first principles, like what is the optimal configuration that we should have of our GPU compute if we made response lengths very long? Because oftentimes when models learn via reinforcement learning, they begin to think for much longer. And also what empirical throughputs we should target during our performance optimization. So this has been a really useful piece of technology for simulation and has informed a lot of the systems and research design decisions that we make. Cool. Thanks for your time, and find us afterwards to jam on some more RL research engineering together later. Thank you.
Our next presenter is here to speak about RL environments at scale. Please join me in welcoming to the stage Research Lead for Prime Intellect, Will Brown.
Hello. Yeah, hi, Mr. Mank. How are you? Hi. Yeah. uh, from my end? Okay, let me join again. So, is it fine now? Okay, okay, okay. So, actually, I was just trying to get in touch with you to discuss regarding your use case and the requirement for the cloud GPU. Like, what are the cloud servers and GPUs you are using currently? So, Mhm. Hmm. Okay. Hmm. Okay. Okay. Good. Okay. Mhm. Okay. 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 So let me start from the beginning actually. So let me introduce you about E2E networks. So E2E Networks is an Indian cloud service provider company and providing the services in market from 15 plus years. As well as E2E is a public NSE listed company and a mighty impaneled which makes E2E eligible to provide services to government. We are the NVIDIA's partners for the GPUs for AI/ML workload. Allow me to share my screen. Will show you the dashboard how it looks like and the services. Yeah. So after creating an account in E2E, you will get the access of this kind of dashboard from where you can like manage the services and all. So this is the E2E My account from where you can access the GPUs. This here you will find the VMs of GPUs as a VM actually. These are the dedicated GPUs VM. Let me show you. Yeah. So we are offering like A100, T4, V100, A30, A40, L4, L40s. So if I talk about A100, it is coming at the A180 GB. It is coming at the price of 1 lakh rupees for a month on the monthly commitment. In E2E, we do not charge for the bandwidth as well and the data transfer cost. So apart from the server costing and the storage costing, there will be no hidden. Yeah. So if you take this in the E2E My account, by default you will get the 250 GB of storage. For more storage, you can attach the volume actually. Right. Within the server, you will get this 250 GB. 800. Okay. Okay. So for 250 GB, we are charging 1250 rupees per month actually. So 5 rupees per GB is the is the monthly cost for the volume. 5 rupees per GB per month. Yeah. Yeah. Let me show you. So in Spot, we are only having it on the H100 and H200. Let me go through the Spot instances. This is the Theory AI platform. Okay. Got the point. So this is our Theory AI platform. This is also the E2E platform, which is very similar to Google Colab. So here you can launch the GPU notebooks actually. And if we talk about, so here you will find the pre-built images from which you can launch the notebooks. And you can choose a base OS as well. So Spot is coming for H100, it is coming for 70 rupees per hour. First 30 GB is free, then 5 rupees per GB per month is the storage charges actually. Yeah. Here you will get the 30 GB only. Yeah. Mhm. Mhm. So, uh, you mean to say like if anytime company can claim back, then what happened to what happened to the model? So I think in that scenario, you will be notified. Anytime you can be notified like companies claiming you have the GPU. And in that scenario, if that happens, I think your data can be saved in the persistent volume. Yeah. Okay. Okay. So that I need to check once with the cloud team or who is the person? Yeah. Yes, yes, yes. I have visited the profile as well. I have went through your profile over the LinkedIn as well. I have checked the details actually, sir. Regarding the AI agency which you are working on. Any to E? Okay, let me check. One second, let me check. Yeah, so he's the part of E2E only. Yeah. So the thing is like he's not from the sales and marketing department. He's from the dev department. I think. Let me check that as well. So we can do one thing. We have a dedicated cloud team for the technical queries. So so this query we can do one thing. If you can drop an email to our cloud team by keeping CC to me. So what I can do is I can check with the cloud team and can answer your queries. Over the email itself, we will like reply with the details if that works. So the thing is, Atharv is from the marketing team. Yeah, he's from the marketing team. I have just checked from the. Uh, no, no, actually, so if you can email once or let me know the details, I can check with the team and can get back to you if that works. Because our cloud team is available 24/7. Uh, Suppose if anything is wrong with the services and if any queries are there, technical queries are there, so they can help you out instantly actually. Mhm. Mhm. So regarding the India AI mission, yeah, for the India AI mission, yeah, for the India AI mission, we are not dealing. So what we are doing is we are providing it to the India, providing the GPUs to the India AI mission. So once you submit a proposal to the platform, and after that, if it gets approved, then you will be able to like access the servers from them actually. Mhm. Mhm. Okay, okay. So regarding the same, what I will do is I will email you. Also, I can schedule. So, as you mentioned, you wanted to have a technical discussion. I will schedule one more meeting with the technical person from our team. Okay. Also, what I can do is so I will be happy to provide you the free trial as well to test out the spot instances or to yeah. Yeah, so 2000 credits by default everyone is getting after signing up. So we will provide more. So I will provide you more once you sign up. So have you signed up already? Oh, okay. Yes, yes. That's very impressive. Yes. Mhm, mhm. Right. Yeah, yeah, that works. Yes. For that, actually, I will email you for the so what will be the so I will share you the details regarding the India AI mission, like what is the procedure. And, regarding the technical discussion, I will like schedule one meeting for the spot instances. Yeah. Mhm. So we have a proper documentation actually for the spot. We have a proper documentation for the spot instances. So for every service, we have a proper documentation. You can explore these ones like yeah, yeah. I have just shared it actually. So in this document, you will find every service of E2E actually. Mhm. Mhm. Okay, okay. Sure, 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 Mike. Sure, sure. Yeah, yeah, I do have your email address. Yeah, yeah. No, sure. Nice talking to you, man. Have a nice. Bye. Bye.